Oh, Selva Padian.
Sir, very good morning, sir. How are you, sir?
Which sound வைங்க.
கேக்குதுங்களா சார்?
கேக்குதுங்க. கொஞ்சம் சவுண்ட் வைங்க.
டாக்டர் செல்வ பாண்டியன். குட் மார்னிங்.
குட் மார்னிங் சார். குட் மார்னிங் சார்.
குட் மார்னிங். குட் மார்னிங்.
நல்லா இருக்கீங்களா சார்?
ரொம்ப நல்லா இருக்கீங்க.
Thank you சார்.
ப்ரொஃபசர் எம்என் பொன்னுசாமி சார் கரெக்டா வந்துட்டாருங்க.
கரெக்டா டைம் கொண்டார் சார். மகிழ்ச்சிங்க சார். இப்போ கரெக்டா ஷார்ப்பா 10 o'clock ஆரம்பிச்சிடுறீங்களா சார்?
10 மணிக்கு சார். 10 மணிக்கு.
சரி சார்.
Good morning to everyone, sir.
Good morning,
this
sir.
Is Jay Shankar.
Good morning, sir. Very good morning, sir. Good morning, sir. So,
good morning, sir.
வணக்கம்.
எப்படி இருக்கீங்க சார்? நல்லா இருக்கீங்களா சார்?
நல்லா இருக்கேன் சார்.
மகிழ்ச்சி.
இந்த கான்ஃபரன்ஸ் கூட நல்லா சக்சஸ்ஃபுல் ஆகணும்.
sir, definitely, sir. With all your blessings.
All our blessings.
Sir. And your son and daughter-in-law, they went to abroad, sir, after marriage.
Already left, sir. 15th marriage, 20th they flight back to Germany.
Okay, sir. Nice.
So unfortunately, I could not extend personal invitation.
Yeah, sir.
But it went on due to COVID, this and that.
Sir.
I don't want to give risk to others. I don't want to take risk myself.
Because of the pandemic period, so this is the best way.
Yeah.
Professor M.N. Punusami, sir. Professor M.N. Punusami, sir. Professor ஜெய்சங்கருடைய சன்னுக்கு மேரேஜ் முடிஞ்சது.
கொஞ்சம் சவுண்ட் வைங்க.
Professor ஜெய்சங்கர் சார் அவருடைய சன்னுக்கு மேரேஜ் முடிச்சா ரீசெண்டா. டியூ டு பேண்டமிக் பீரியட் ஒண்ணும் பிளான் பண்ண முடியல சார். அதான்
இல்ல இது இப்ப இருக்கிற சூழ்நிலையில வெரி டிஃபிகல்ட் டு பிளான்.
ஆமா சார்.
இப்ப ரொம்ப கஷ்டம் இப்போ.
சார்
இப்போ மேக்ஸிமம் வந்து 20 or 30 people can invite முடியும்.
Yes, sir.
செல்வவாணியன் பொடினா
சார் அவர் ஜூனியர் சார்.
ஜூனியர் சயின்டிஸ்ட்.
பெரிய ஆளாயிட்டாரு.
திருவண்ணாமலையில பாக்கும்போது 6 month பேபி சார். கிட்டத்தட்ட 5 years ஆயிடுச்சுங்க சார்.
Sir, good morning, sir. Ispa, sir, good morning, sir.
Good morning, Selvi.
Very good morning, Dr. IVCPEMM, convener.
Sir, good morning.
Good morning, sir. Good morning, sir.
Good morning to.
Good morning, sir.
Good morning.
Good morning, sir. Good morning. Welcome. And congrats, being appointed as a principal.
Good morning to all.
Sir.
Secretary, sir.
Secretary, sir. Good morning, sir.
Good morning.
Good morning, Raji,
sir.
Good morning, sir.
Sir, good morning, sir.
Very good morning. Good morning.
Professor Jaisankar, sir, good morning, sir.
Good morning.
She is convener of the conference, sir. Dr.
Yeah.
Yes, sir.
I used to get mail from her only.
Yeah.
And I wish this should be grand success.
Yes, sir.
And the recorded program may be kept in YouTube so that people can see relaxedly totally later on.
Yeah. YouTube,
Now
sir.
itself,
Yeah.
we are telecast to YouTube, sir. Sir, shall I start, sir? Shall we start,
Sir? Okay.
Our students are
YouTube, sir.
Again?
Sir, students YouTube la watch பண்ணிட்டு இருக்காங்க sir. YouTube link.
Beginningல எங்க
ஸ்டார்ட் பண்ணலாங்களா? அவர் இது வந்துட்டாருமா நம்ம?
போலாமா சார்?
ஸ்டார்ட் பண்ணலாங்க.
ஓகே.
Every morning.
Sir, ஆரம்பிச்சிட்டாங்க sir.
Every morning, start a new page in our story and let's make a great one today. Good morning, one and all. PG and Research Department of Physics, Sri Vidya Mandir Arts and Science College, Uttankurai, and Indian Petrophysics Association ISPA, in commemoration of National Science Day, extend a glowing welcome to the dignitaries on and off the dais and delegates to this International Conference on Physics of Emerging Materials and Molecules, IVCPEMM 2021. Success seems to be connected with action. Let's join hands to make this international conference a great success and begin the program with Tamil Thai Vazhuttu. Thank you. The empowered woman is powerful beyond measure and beautiful beyond description. I request the superwoman of the conference, Dr. R. Arivaselvi, convener of the conference of Sri Vidya Mandir Arts and Science College, Uttankurai, to welcome the dignitaries and the August gathering.
Smile is the electricity and life is a battery. Whenever you smile, the battery gets charged and a beautiful day is activated. Have a smile day with us in this International Conference 2021. Most respected and beloved, our founder of our institution, dynamic conference president, the excellence awardees, the secretary and additional secretary, the principal and vice principal, resource persons of two-day international conference, HODs of various departments, faculty members of our college and other college, non-teaching staff members, and dear students participants. A very pleasant good morning to all. International Virtual Conference on Physics of Emerging Materials and Molecules, IVCPEMM 2021 was planned and organized on account of National Science Day. With this highly prestigious movement at the beginning, it is my great pleasure and privilege to welcome our founder, V. Chandrasekharan sir, who is always with us in all our positive progressive steps by means of providing constant encouragement, advice, suggestions, blessing, etc. I welcome you, sir. Then it is a great honor and privilege to welcome Dr. S. Gunasekharan sir, Dean Research and Development, St. Peter's University, Chennai, and founder president of ISPA, who is a sort of great inspiration in all of our events. I welcome you, sir. I find immense pleasure and extremely proud to welcome Honorable Vice Chancellor, sir, Dr. P. Dhananjayan, sir, St. Peter's University, Chennai. We are really thankful to you, sir, for taking time out of his busy schedule. I welcome you, sir. Dr. Yaman Ponnasamy, sir, Emeritus Professor, Department of Crystallography and Biophysics, University of Madras, Chennai, who is a voracious scholar and indeed rending his fullest dedication for the uplifting of science. I welcome you wholeheartedly, sir. A background of our college, with due respect, I welcome Thiru R.P. Raji, sir, the secretary of the college. I welcome you, sir. The great honor and privilege to welcome Thiru P. Venkatachalam, sir, who is with us in all our positive steps. I welcome you, sir. It is also my due privilege to welcome our most respected principal, Dr. T. Balasubramaniam sir, who is being the greatest strength of all of us, whose guidance moves us towards success. I welcome you, sir. I invite our most respected vice principal, Dr. N. Gunasegaran sir, who is always supporting us to organize this kind of events. I welcome you, sir. Really, I feel immense pleasure to welcome Dr. K. Sendil Kannan sir, Professor, GS Pillai Arts and Science College, Nagapattinam, and today ISPA Dr. S. Gunasegaran Awardee. I welcome you, sir. It is my honor and more than great pleasure to welcome such noble personalities of the two-day international conference. They are Dr. R. Jaivel sir, Professor, Crystal Growth Center, Coordinator, Center of Nanotechnology, Anna University, Chennai. Dr. C.K. Jayasankar sir, UGC BSR Faculty Fellow, Department of Physics, Sri Venkateshwara University, Tirupati. Dr. Jiban Podar sir, Professor of Physics, Bangladesh University of Engineering and Technology, Bangladesh. Dr. S. Kalainathan sir, Professor, Center for Nanotechnology and Research, VIT University, Vellore. Dr. C. Segar sir, Professor and Head, Department of Bioelectronics and Biosensors, Alagappa University, Karaikudi. Dr. P.M. Anbarasan sir, Professor, Department of Physics, Periyar University, Salem. Dr. V.M. Reddy sir, Hydrocubic Institute of Research, CWTSE, Hydrocubic, Montreal, Canada. Welcome you, sir. Dr. S. Suresh Sahadevan sir, Senior Research Fellow, Nanotechnology and Catalyzed Research Center, University of Malaya, Malaysia. Welcome you, sir. Dr. Venkatrama Reddy sir, Head Department of Physics.
I'm starting to charge.
Express my warm welcome to the members of ISPA, heads and teaching faculty members of various departments, organizing committee members of this international conference, teaching faculty members of other college, energetic students, participants from our college and other college, press and media persons, and special welcome to Dr. P. Janani ma'am for her marvelous comparing. Finally, I thank the organizing committee for this international virtual conference for providing this wonderful opportunity to offer welcome address ahead of this grand gathering. Thank you, one and all. Thank you.
Thank you, ma'am. What is the secret to success? It is a fanatical focus on completing a goal. Collective work is the secret behind the goal of the conference. Now, I request Dr. Suresh, Organizing Secretary of the conference, to deliver the focal theme of the conference.
Most respected dignitaries, organizing committee members, and participants, a pleasant good morning to one and all. It's my great privilege and honor to be a part of a member of this international virtual conference on physics of emerging materials and molecules. Today, we have witnessed an emergence of large number of materials with unique physical, chemical, and biological properties. For instance, we can take the materials from carbonaceous objects such as graphene, carbon nanotubes, etc., that have proficient applications in diverse scientific and technological areas. In this context, when we go through the lectures from eminent speakers and the research findings of the participants of this conference, we can see that this conference is going to discuss about novel synthesis techniques, properties identification of several materials, novel materials in terms of physical, chemical, and theoretical aspects, and their potential applications in the most thrust areas of this 21st century, such as energy conversion and environmental pollution mitigation. I am highly certain that this conference will be an ideal virtual platform for gathering ideas towards the promising research endeavor of the participants. I thank for giving this valuable opportunities to the organizing committee members of this conference. Thank you.
Thank you, sir. Positive leaders empower people to accomplish their goals. On behalf of Sri Vidya Mandir Arts and Science College and Indian Spectrophysics Association, we feel proud to say a few words about our Honorable Chief Patron of the conference, a positive leader, Thiru Chandrasekharan, founder of Sri Vidya Mandir Group of Institutions, who serves the perfect key for leading the institution in a vibrant spectrum of colors and have bolstered the institution as a successful one. A big heartfelt thanks to him for the continuous encouragement and support for providing quality and research in output in our education institution that makes us stand before you what we are today during this pandemic period. Thank you so much, sir. The rainbow, the bridge of the gods, proved to be the bridge to our understanding of light. National Science Day is celebrated every year on 28th February to commemorate the invention of the Raman effect in India by the Indian physicist Nobel Prize laureate Chandrasekhara Venkata Raman. We all know him by the name Sir C.V. Raman. We are going to honor our Indian physicist who carried out groundbreaking work in the field of light scattering that earned him the Nobel Prize for the physics in the year 1930. Every National Science Day has a theme. The theme for this National Science Day 2021 is the future of science, technology and innovation and its impact on education, skills and work. I feel immense pleasure to invite the Honorable Chief Patron of the conference, Sir V. Chandrasekharan, founder of Sri Vidya Mandir Group of Institutions, to unveil the portrait of Sir C.V. Raman. I request the dignitaries on the dais and off the dais to join our honorable founder. Thank you. Lighthouse do not fire cannons to call attention to the shining. They just shine. Dr. S. Gunashegaran, Doctor of Science, a spectrophysicist, Tansa Awadi, Dean Research and Development of St. Peter's Institute of Higher Education and Research, Chennai, has a credit of founding an association called Indian Spectrophysics Association with the acronym ISPA. Dr. Gunashegaran has successfully guided 78 candidates in the field of material science, medical physics, environmental science, and molecular dynamics, and has to his credit more than 400 publications in reputed journals and has H-index of about 36 and item index of 40 with 5,900 citations. He is bestowed with 26 different awards from different prestigious organizations that include the most prestigious Tamil Nadu Scientist Award, the field of physical sciences from Government of Tamil Nadu in the year 2013. I request our leader of excellence, conference president, founder, president of ISPA, Professor S. Gunashegaran, to deliver the inaugural address.
இல்ல சார் பார்த்து
So mute la irukku.
Honorable founder, Thiru V. Chandrasekharan Ayya, founder of this great institution, Sri Vidya Mandir Arts and Science College, Uttangai. My elder brother, eminent scientist in the field of biophysics and crystallography, Professor Dr. M.N. Ponusamy, keynote speaker of this 2 days inaugural session of 2-day international conference on international conference on physics of emerging materials and molecules. Eminent scientist from Tirupati Venkateswara University, Dr. Jai Shankar, Professor Reddy from Canada, Honorable Vice Chancellor of the great St. Peter's Institute of Higher Education Research, Professor Dr. P. Dhananjayan, ISPA Lifetime Achievement Awardee for the year 2020, Dr. K. Senthil Kannan, my beloved students, ISPA Dr. Gunasekaran Awardee for the year 2020. My good friend, my younger brother, Dr. R. Jayavir. Honorable Secretary of this esteemed institution, Mr. R.P. Raji. Additional Secretary, respected P. Venkatachalam. Esteemed Principal of this esteemed institution, Dr. T. Balasubramanian. Respected Vice Principal of this college, Dr. N. Gunasekaran. Dynamic convener of this two-day international conference, Dr. R. Arivichelvi. Organizing secretary of this conference, Dr. Suresh. My good friend, Dr. M. Selva Pandian, Dr. S. Kumaresan, professors from various institutions, various departments, dear members of Indian Spectrophysics Association, young budding scientists who are gathered here, dear members of press and media. Vanakkam, Vantanam, Namaste, Namaskar, Suswagatam, and good morning to one and all. I deem it a great pleasure to have involved myself as one among you with this two-day international webinar, international conference, virtual conference on physics of emerging materials and molecules, organized by the Department of Physics of Sri Vidya Mandir Arts and Science College in collaboration with the Indian Spectrophysics Association. It is my pleasant privilege and proud duty to express my heartfelt thanks to the organizers, founder of the institution, principal, vice principal, and the convener of this conference, Dr. Arivichelvi, for having given me an excellent opportunity to stand before you and address the inaugural address for this two-day international conference. My dear friends, we know the difficulties involved in the organization of a conference during the pandemic period. Even though the organizers have made a sustained effort to organize this two-day international webinar with the eminent personalities all over the world. As you know, there is a word in English, preparation. Preparation is not an English word, to my opinion. This is a word of human thought. Because preparation is equal to planning, planning plus principle, principle plus practice, practice plus patience. So these are all the four factors involved under the word preparation. At the beginning of this organization of this international virtual conference, planning, principle, practice, and patience may be bitter roots for the organizers. I know these four factors may be the bitter roots for the organizers, but they should know how to make these bitter roots as butter roots. They know how to make that butter roots into better roots. They know the knack how to make all these four roots, bitter roots, into better roots. That's why they have succeeded in this endeavor today. So roots of any event are bitter, but the fruits will be very sweet. This is a well-known factor. Fruit means the inaugural sessions, validity sessions, all technical sessions, including oral presentation. So these are all the fruits of the tree. Roots of the tree is bitter, but the fruits will be very sweet. My dear friends, you know the spider web. You should know the secret to the spider's ability to spin a web. Spider does this by pulling the spider silk through its spinner silk secretion organs. This science actually. But here organizers, Dr. R. Arvichelvi, with the cooperation of faculty members, with the coordination of the organizing secretary, Mr. Suresh, with the able leadership of our founder, V. Chandrasekharan, with the able guidance of the principal and the vice principal, he is able to pull the admin ability, the academic ability, and organization skill from the faculty members of the department. That's why she is able to build a beautiful spider web today. This is a beautiful spider web. To pluck the rose from the rose plant, because I should congratulate the whole team of workers. Now, they are able to bring a number of stalwarts from a different organization. To pluck the rose from the rose plant, one should be ready to bear the prick of thorns. Dr. Arvichelvi has made painful effort with the help of our principal and vice principal, with the leadership of our founder, Mr. V. Chandrasekharan. And the outcome of those efforts today is in the form of International Conference on Physics of Emerging Materials and Molecules. This is not a single color rose. This is a multicolor rose, which seems to be very beautiful today and having very sweet aroma. On behalf of a Spectrophysics Association and my own self, I should congratulate Dr. Arvichelvi and the whole team of workers for having organized an excellent program with this esteemed institution. Congratulations to one and all. I am sure that this international conference will definitely give a great boon to this higher education institution, Sri Vidya Mandir Arts and Science College. In fact, they have chosen a fantastic title for the conference. International Conference on Physics of Emerging Materials and Molecules. Materials. What are the materials? New materials, advanced materials, biomaterials, biological materials, pharmaceutical materials, diamond-based materials, electronic materials, ferroelectric materials, fluorescence material, functional materials, luminance materials, magnetic materials, superconducting materials, materials for defense applications, materials for solar applications, energy storing devices, NNO materials, photonic materials, smart materials, and nano materials. A to Z materials. My dear friends, synthesize, material synthesis, material characterization, and their application. Quality, quantity, and utility. That is called concept development for inspiring innovations to bind science and society. So, synthesize, characterization, application. That is a real research. That is a research excellence. Outcome of the research should be useful to the community, to the common man. That is societal application. That is called the research excellence. The Department of Physics always, the Department of Physics of this SVMASC, Sri Vidya Mandir Arts and Science College, Uttangarai. So the department always a team effort in propelling the young researchers to achieve research excellence. So continuously, without any break for each and every academic area, by way of conducting this kind of conferences. I know in the YouTube, in the audience of the auditorium. So there are a number of young researchers are present. You are all young researchers. You are all young philosophers. I used to give the explanation for philosophy. You know, 2 degrees, Master of Philosophy, MPhil, Doctor of Philosophy, PhD. Master of Philosophy, philosophy, Doctor of Philosophy, philosophy. What is the actual meaning for this philosophy? There are 2 words from Latin language. One is phlos, another word is Sophia. Phlos plus Sophia combined together, we are getting a single word, philosophy. So phlos means knowledge, Sophia means love. That is in Tamil, phlos means arivu, Sophia means nesipadu. Arivai nesipadil, MPhil scholars, you are all master of philosophy. You are all masters. Arivai nesipadil, Doctor of Philosophy, PhD scholars, you are all doctors. This is the actual meaning for philosophy. Master of Philosophy, Doctor of Philosophy. So all young budding scientists, all young philosophers we are present here, you are all the pillars of the nation. You are the builders of the society. The healthy and effective functioning of the sphere of higher education lies in the hands of young budding scientists who are gathered here. Dear philosophers, dear young budding scientists, you may be aware of that science and technology workforce in our higher education institution in our India. India's science and technology workforce is estimated to be just 2 lakh. That is 4 researchers per 10,000 PG scholars in various branches, various programs, compared to 18 for China and 79 for United States of America. According to the latest statistics available with the DST, India ranked 6th place in the number of total annual research papers. If you refer, kindly visit to SciMaco country ranking, SCR. Number of documents, citable documents presented in USA, 84 lakhs 56,050 papers as on date. Citations offered on these 84 lakhs 56,050 papers, 20 crore 27 lakhs 50,565 citation. With that, United States of America, they have the H index 21.66. So H index, the citation per document 21.66. H index of the country is 17883 order, comparing the global scenario, 1783, the first place. What about the status of our Indian scientific community in terms of paper publication? Citable documents are 10,72,927 papers, on which we are able to get 84,58,373 citations. With that, number of citations per document 7.41. With this, we are able to acquire H index is 426 in the global scenario. America stands first, 1783 H index. Our India stands the 9th place, having H index 426. This is a happy message given to the young budding scientists who are gathered here. So this was surprised by the USA, China, UK, and Japan, because we are in the 9th place in terms of quality paper publication. This was surprised by USA, China, UK, and Japan. It is predicted that India's research productivity will be able on par with most G8 nations within 7 to 8 years. This is a data given. What is G8 nations? Leading advanced economics in the world group of 8 nations. What about 8 nations? Canada, France, Germany, Italy, Japan, Russia, UK, USA. Unfortunately, in the year 2014, Russia was suspended from these G8 nations. They are unable to compete with the global scenario in terms of paper publication. According to current statistics with Ministry of Human Resource Development, Tamil Nadu ranked number 1 in the enrollment of PhD scholars. Tamil Nadu stands on the top with nearly 20,000 PhD scholars as on date, exceeding 20,000. Followed by Delhi with 12,000 and UP with 12,000 something. At the same time, quantity is not important. Quality is very, very important thing. Quality research work is the main criterion to judge the standard of higher education institution, for which brain management is very, very important thing. My humble request to the gathering of the young budding scientists, young philosophers here, including the PG students. Brain management, to acquire the brain management, so reading habit is very, very important thing. You take Switzerland, there is one private company, the name of Current D Arch. They produce costliest pen in the world. That is golden pen with 1.25 crore. Golden pen with 5,000 pieces of diamond. Costliest pen. Cost is 1.25 crore. But இவ்வளவு காஸ்ட்லியா நம்ம பெண்ணை வாங்கினாலும் 1.25 கோடி கொடுத்து பெண்ணை வாங்கினாலும் ரீஃபில் இங்கு போட்டாதான் எழுத முடியும். Costliest human being system, costly living system on the surface is human being system. So human being system costly சொன்னா போதுமா? பயன்பாட்டிற்கு நமக்கு knowledge வேண்டாமா? Therefore, reading habit is important. To acquire knowledge, brain management. So reading habit is very important. You take honeybee, to collect just 100 grams of honey, one honeybee has to fly more than 10,000 flowers, for which it has to travel nearly 1 lakh kilometers. You take 1 ton kg weight of ore, to get 26.4 gram of gold from the ores, I mean pure gold, we need 1 ton, 1000 kg weight of ore. Therefore, to write 10 to 15 pages research paper, a research scholar should go through hundreds of paper. Then only we can think about quality of research publication published in the quality journals. As you know, the beloved student of K.S. Krishnan, a grand scientist, K.S. Krishnan. My wholehearted involvement came only after 8 years, when I got opportunities to read copies of Sir C.V. Raman, publications of Sir C.V. Raman. Then only it gave me a new feeling for science and the new world of science. Research பண்றதுக்கு முந்தி Sir C.V. Raman publish பண்ண அந்த 6 volume published by an organization, Indian Association of Cultivation of Science, 6 volumes, more than 400 articles. He required 8 years. அதுக்கு research start பண்றார். So reading habit is very, very important thing. Reading habits of the research articles will definitely provide brain management. Then only you think about the quality research articles. One junior researcher is asking to one avid researcher, senior researcher, how to publish quality research papers? This is the question raised by one junior researcher, for which the senior researcher has given the reply. Nice reply. என்ன reply? அதுக்கு 4 மெய்கள் தேவைப்படுது. அதுக்கு ஜூனியர் ரிசர்ச்சர் சொல்றாரு, ஹாப்பி 4 மெய் தானே, ஈஸி ஆச்சு. கருப்பு மையா ப்ளூ மையான்னு கேட்கிறாரு. தம்பி அந்த மெய் இல்ல, திறமை, பொறுமை, தனிமை, பேராமை, என்ன அருமை. ஸோ இது நாலுமே இருந்தால் தான் we can do some quality research article. தொடக்கூடாதமைகள், that is the plagiarism. கயமை, பொய்மை, மடமை, வேற்றுமை. பென்சிலின் அடியில் அழிப்பதற்கு ரப்பர் இருக்கும். ஏனென்றால் மனிதர்கள் நிச்சயமாக தவறு செய்வார்கள் என்பது உண்மை. அதனால்தான் பென்சில் அடியில் ரப்பரை ஆட் பண்ணியிருக்கேன் பாரு. தொற்று எழுதக்கூடியமைகள் என்ன? நன்மை தரக்கூடிய நேர்மை, திண்மை தரக்கொண்டிருக்கும் புதுமை, தூய்மை தரக்கூடிய செம்மை, வலிமை தரக்கூடிய உண்மை. இந்த நோக்கத்தில் ஆராய்ச்சியாளர்கள் தங்கள் கடமையாகவும் உரிமையாகவும் கொண்டு தமது இந்திய நாட்டிற்கு பெருமை சேர்க்க வேண்டும். Therefore, தன்னம்பிக்கையும் நேர்மையும் கொண்ட எந்த ஆணும் அழகன்தான். கனிவும் பணிவும் கொண்ட எந்த பெண்ணும் அழகுதான். அழகு என்பது உடம்பில் இல்லை, நீங்க ஆராய்ச்சி பண்ற அந்த குவாலிட்டி ரிசர்ச் ஆர்டிகல்ஸ் தான் இருக்கு. Don't dream about your beauty, that will spoil your duty. Dream about your beauty, it will make your life very beauty. Innovations come from creativity, creativities come from beautiful mind. உலகை பாருங்கள், வியக்கலாம். உழைத்து பாருங்கள், ஜெயிக்கலாம். நினைத்து பாருங்கள், சிந்திக்கலாம். உங்களுக்கு நம்பிக்கை இல்லையா? அதோ பாருங்கள் நம் அப்துல் கலாம். எழுந்து நின்றால் அந்த இமயமலையும் உங்களுக்கு இடம் கொடுக்கும். That is not doubt it. உறங்கி கிடந்தால் அந்த சிலந்தி வளையும் உங்கள் சிறை பிடிக்கும். Therefore, my dear young budding scientists, get ready. Go ahead, kindly participate in our research activities. Demonstrate your brain management. Demonstrate your time management. Demonstrate your human resource management to provide quality research work in our research area. Get awards and make it a record. Wish you all good success. Thank you very much.
Thank you, sir, for making us understand how to make us better things better and then better, and the making of a beautiful spider web from the teamwork and the research status and development of India. Thank you, sir, for the inspiring inaugural address. Academic success depends on research and publications. Here is the most awaited event of the conference, release of proceedings. I request Thiru R.P. Raji, patron of the conference, secretary of Sri Vidya Mandir Arts and Science College, to release the CD proceedings of the international virtual conference, and request Dr. T. Balasubramanian, conference chairman and principal of Sri Vidya Mandir Arts and Science College, to receive the first copy of the CD proceedings. Thank you. I request our Professor P. Dhananjayan, Vice Chancellor of St. Peter's Institute of Higher Education and Research, Chennai, to release the proceedings of the international conference, and request Dr. S. Gunashekaran, Dean Research and Development of St. Peter Institute of Higher Education and Research, and Dr. C.K. Jayashankar, Sri Venkateshwara University, Tirupati, to receive the first copy of the proceedings. Thank you.
Thank you, thank you, thank you.
Talent wins games, but teamwork and intelligence wins championships. Indian Spectrophysics Association was started on April 23rd, 1998 by a well-known professor, researcher, and scientist, Dr. S. Gunashekaran. It is the peak of a strong belief that enlightening minds and empowering them through spectroscopy and physical phenomena is a way for battling and eliminating social evils and uplifting the society. Indian Spectrophysics Association, through its initiatives, provides access not only for quality education in spectroscopy and its applications, enhance innovative researches, but also inculcates values, commitment, and dedication to the society, thus helping to build a strong future for every researcher like a spectrum of physics. Indian Spectrophysics Association is privileged to honor the notable services of the scientist with Lifetime Achievement Award. The award is conferred to whom those who dedicate themselves in the field of research and still working on the same respective fields to enrich the society with their findings. For young researchers who have made excellent contributions in the field of research made to benefit of humanity have been honored with ISPA Dr. S. Gunashekharan Award during conferences or seminars organized by ISPA. ISPA has the honor of giving 3 Veteran Scientist Award, 20 Lifetime Achievement Award, and 57 ISPA Dr. S. Gunashekharan Award so far. Adding to this prestigious moment, ISPA feels proud to confer ISPA Lifetime Achievement Award and ISPA Dr. S. Gunashekharan Award to 2 eminent scientists in the field of research. I request Professor N. S. Kumaresan, Treasurer of ISPA, to prelect the citation of ISPA Lifetime Achievement Awardee.
A very good morning to one and all present here. I take the privilege in reading out the citation conferred to Dr. Dhananjayan Perumal on his achievement, Lifetime Achievement Award. Indian Spectrophysics Association, ISPA, and Sri Vidya Mandir Arts and Science College, Uthangarai, presents Lifetime Achievement Award conferred on Dr. Dhananjayan Perumal, Vice Chancellor, St. Peter's Institute of Higher Education and Research, Avadi, Chennai. Dr. Dhananjayan Perumal was born on 12th May 1957. He has completed his undergraduate degree in electronics engineering from MIT, University of Madras, in the year 1982, followed by his post-graduation in engineering in electronics from the same institute in the year 1984. He went on to complete his PhD in electronics in the year 1998 from College of Engineering, Anna University, for his work on wireless communication, ad hoc and sensor networks. Dr. Dhananjayan has started his career as a lecturer in KSRM College of Engineering at Kadapa, Andhra Pradesh from 1984 to 85, and is now the Vice Chancellor of the prestigious St. Peter's Institute of Higher Education and Research, Avadi, Chennai. He acted as former principal of Pondicherry Engineering College, Puducherry, head of Department of EI and ECE, chairman of PG program, dean of examination from the same college. He also served as a coordinator for admission committee of professional PG courses by Government of Puducherry. Professor Dhananjayan has 35 years of teaching experience, 25 years of research experience in electronics. He is one of the earliest pioneers in the field of wireless and published significantly in this than 115 research papers as 34. He has guided 21 PhD scholars and significant number of postgraduate and MPhil scholars. He has organized 5 national and international conferences, seminars, and workshops, and has presented more than 150 papers in national and international conferences. He has delivered more than 50 invited talks in national and international conferences. He has authored or edited some chapters in international books in different publications. He is the member of several editorial boards and also the reviewer of several reputed international journals. Professor Dhananjayan has been the principal investigator and co-investigator of several sponsored major projects with a fund of more than 11 crore funded by the various organizations such as DST FIST, Atal Incubation Scheme, Niti Aayog, and Modrop's AICTE. Professor Dhananjayan has been a fellow of Institution of Engineers and a life member of CSI and ISTE. He has been a visiting professor seconded by the Government of India to Asian Institute of Technology, Bangkok in the year 2009 and Dr. Ambedkar Institute of Technology, Port Blair, Andaman during 2010 and 12. He has acted as an NBA evaluator. Professor Dhananjayan is a recipient of Man of the Year 2003 award sanctioned by the American Biographical Institute and its Board of International Research. He has visited many countries that includes Malaysia, Thailand, Singapore, Sri Lanka, Belgium, France, Switzerland, and the list is endless for his collaborative research. Given under the seal of Indian Spectrophysics Association and Sri Vidya Mandir Arts and Science College, Uttangarai, on 4th March 2021 at the International Virtual Conference on Physics of Emerging Materials and Molecules, abbreviated IVCPEMM 2021, in commemoration of National Science Day held at Sri Vidya Mandir Arts and Science College, Uttangarai, organized by the Department of Physics. I am thankful for this opportunity to read out one of the greatest scientists. Thank you. Thank you one and all.
Thank you, sir. I request Professor P. Dhananjayan, Vice Chancellor, St. Peter's Institute of Higher Education and Research, Chennai, to receive Lifetime Achievement Award under the seal of ISPA and Sri Vidya Mandir Arts and Science College on 4th March 2021 at the International Virtual Conference on Physics of Emerging Materials and Molecules held on an online platform from Thiruvi Chandrasekharan, founder of Sri Vidya Mandir Group of Institutions, Uttangarai, Professor M.N. Ponnusamy, CAS in Biophysics and Crystallography, University of Madras, Chennai, and ISPA President and Dean Research and Development of St. Peter's Institute of Higher Education and Research, Dr. S. Gunasekaran.
Yeah. Can I say a couple of words presently? We feel it a pleasure to. Can you hear?
Yeah, sir. You're able to hear your voice, sir.
Yeah, I'm just saying a few words. We feel it a pleasure to hand over this award, ISPA Lifetime Achievement Award to Professor P. Dhananjayan, the Vice Chancellor of the great University, Chennai. I'm sure that from the readout of the information that he is a very qualified and nice person to receive this Lifetime Achievement Award from ISPA, along with the Vidya Mandir Arts and Science College. It's a great honor for us to hand over this award to him. Thank you.
Thank you, sir. Thank you. Thank you.
Thank you, sir. Next, I request Professor M. Selvapandian, Coordinator of ISPA, to prelect the citation of ISPA Dr. S. Gunasekaran Awardee.
Good morning to one and all present this webinar. I am very much happy to read the citation of ISPA Dr. S. Gunasekaran Award at the International Virtual Conference on Physics of Emerging Materials and Molecules 2021, jointly organized by Indian Spectrophysics Association, ISPA Chennai, and Sri Vidya Mandir Arts and Science College, Uttangarai. ISPA Dr. S. Gunasekaran Award conferred on Dr. K. Sendil Kannan, MSc PhD DLit, Research Scientist, Director Research, Vice Principal, EGS, Pillai Arts and Science College, Nagapattinam. Professor Sendil Kannuswamy has completed his undergraduate degree in physics from Tiruvika Government Arts College, Bharathasan University, Tiruvarur, followed by his post-graduation from IVCPEMM Sri Pushpam College, Tanjavur, and Master of Philosophy in Physics from Manonmaniyam Sundarnar University, Tirunelveli. He went on to complete his PhD in Physics from University of Madras. He was awarded Doctorate of Letters for his academic and research profession and achievements. Professor Sendil Kannan is presently working as a professor, director and R&D, vice principal and research scientist in EGS Pillai Arts and Science College, Nagapattinam. Professor Sendil Kannan has 21 years of teaching and 16 years of research experience in crystal growth. He is one of the earliest pioneer in the field of ultrasonic spectroscopy, material science, crystal growth, crystallography, new material, nanoscience, thin film, and biomaterial, and has published significantly in this domain. Professor Sendil Kannan has published more than 350 research papers in international peer-reviewed journal with more than 71 citation, H index as 5 and I10 index as 3. He has guided significant number of PhD, postgraduate, and MPhil scholar. He has organized 25 national, international conferences, seminar, and workshops, and has presented more than 325 papers in international and national conferences, seminar, and workshops. He has delivered more than 20 invited talks in national and international conferences, seminars, and workshops. He has authored and edited some chapters in international books in different publications. Professor Sendil Kannan is recipient of several awards and recognitions. To name a few, he has been awarded Best Dean Award, Best Vice Principal Award, Best Indian Educationist Award, Global Scientist Award from Malaysia, Senior Scientist Award from Ministry of Commerce and Industry, Government of India, and so on. He has visited Oman, Zambia, Harare, Zimbabwe, Addis Ababa, Singapore, Malaysia, Tanzania, Sri Lanka, Vietnam, Taiwan, Indonesia, Bangkok, and Thailand for his collaborative research. Given under the seal of Indian Spectrophysics Association, ISPA, and Sri Vidyamandir Arts and Science College, Uttangarai, between 4th and 5th March 2021 at International Virtual Conference on Physics of Emerging Materials and Molecule, IVCPEMM 2021, in commemoration of National Science Day, held at Sri Vidyamandir Arts and Science College, Uttangarai, organized by the Department of Physics. Signed by Dr. R. Arivichelvi, Convener, IVCPEMM 2021, Dr. T. Balasubramaniam, Principal, Sri Vidyamandir Arts and Science College, Uttangarai, Sri V. Chandrasekharan, Chairman, Sri Vidyamandir Arts and Science College, Uttangarai, Professor Dr. S. Gunasekharan, Founder, President, ISPA, Chennai, date 4/3/2021, place Uttangarai. Thank you.
Thank you, sir. I request Professor K. Sendil Kannan, Research Director of Edayathankudi G.S. Pillai Arts and Science College, Nagapattinam, to receive ISPA Dr. S. Gunashekharan Award under the seal of ISPA and Sri Vidyamandir Arts and Science College on 4th March 2021 at the International Virtual Conference on Physics of Emerging Materials and Molecules, held on an online platform, from Thiruvi Chandrasekharan, founder of Sri Vidyamandir Group of Institutions, Uttangarai, Professor C.K. Jayasankar, Department of Physics, Venkateshwara University, Tirupati, and Dean Research and Development of Spire and Founder President of ISPA, Dr. S. Gunashekharan.
Thank you, ma'am. Thank you.
Thank you. Next to excellence comes the acceptance of it. I request Professor P. Dhananjayan, Vice Chancellor of St. Peter's Institute of Higher Education and Research, Chennai, to give the acceptance speech.
Good morning to all. Mr. V. Chandrasekharan, Chief Patron of this International Virtual Conference on Physics of Emerging Materials and Molecules. Professor Gunashekharan, Conference President. Mr. T. Balasubramanian, Conference Chairman. Professor R. Arivichelvi, Convener of this conference. Professor S. Suresh, Organizing Secretary. Professor M.N. Ponnusamy, Keynote Speaker. Professor Jayavel, Professor Jayashankar, Professor Reddy, the co-awardee Professor Sendil Kannan, and my faculty members, other dignitaries, the participants from various colleges, the members of non-teaching, and my dear student friends. First of all, I thank the organizers of this International Virtual Conference on Physics of Emerging Materials and Molecules, organized by Department of Physics, Sri Vidya Mandir Arts and Science College, Uttangarai, in collaboration with Indian Spectrophysics Association, ISPA, Chennai, who came forward to give the award to me. I am very glad to accept this Lifetime Achievement Award from this institute. I'm extremely happy. I want to say a few words. Actually, I am an odd man out here. Everyone is physics people, physicists. But I am an engineer. But basically, I am a professor. I am a teacher, just like you. Maybe I may be teaching a communication, but you people are teaching physics. My basic degree is physics, BSc Physics, Thakur Arts College, Pondicherry, from University of Madras at the time. Actually, there is no PG course during that time. It is very difficult to get the PG seats. Either I got to go to Annamalai University or Chennai, President's College. I applied 3 places for MSc Physics, Pundi Pushpam, Annamalai University, and President's College. I got the seat in President's College. So I am so happy. So I want to study MSc course. But my parents are not allowed to pursue this course. Then after my MN, I got the seat from MIT, ProMed, BTech seat I got it. So my way is completely changed now. Yeah. I'm so happy. Even now, I'm so happy along with you people, physics people. Since I studied communications, electromagnetics, even electronics in BSc, the first course actually it was in 1976. The semester system was introduced. We are the first semester system people. So we had studied many courses. Based on that only, I took electronics and communication engineering as my BTech as my course. So actually BSc Physics, it taught me a lot. Still I remember some of the courses when I'm studying in BTech or MTech, it was so useful. I must congratulate or I must thank our Dean, Gunasekaran. Actually, I know him, but he has a very good contact. I hope by seeing you people, I was a little bit excited because he's in our institute. He is the constant source of the inspiration of research. Each and every day, he insists that teachers, young teachers especially, to do research, increase your H index, go for quality publications. Even some young teachers may be somewhat irritated. Even then, he don't worry about it. He is an asset for our university, and he is the founder of ISPA. You know that his service is highly commendable. With these words, I thank once again the ISPA members, the organizers of virtual conference, and the Sri Vidya Mandir Arts and Science College management people who came forward to give this award. Thank you, sir. Thank you very much.
Thank you so much, sir, for the very beautiful acceptance speech. The happiest people I know are those who lost themselves in the service of the others. I request the patron of the conference, Secretary of Sri Vidya Mandir Arts and Science College, Uttangarai, Sri R.P. Raji, to deliver the felicitation address.
அனைவருக்கும் காலை வணக்கம். 2 நாள் இயற்பியல் துறை பன்னாட்டு கருத்தரங்கில் பங்கேற்றுள்ள வித்யாமந்திர் கல்வி நிறுவனர் அவர்களுக்கும் நிறுவன தலைவர் டாக்டர் குணசேகரன் அவர்களுக்கும், டாக்டர் தனஜயன், டாக்டர் செந்தில்கண்ணன் அவர்களுக்கும் மற்றும் கருத்தரங்கில் சிறப்பு பேச்சாளர்கள் அனைவருக்கும், எங்களது கல்லூரி முதல்வர், துணை முதல்வர், துறை தலைவர்கள் மற்றும் ஒருங்கிணைப்பாளர் அனைவருக்கும், இக்கருத்தரங்கில் பங்கேற்கும் மாணவ மாணவிகள் அனைவருக்கும் முதற்கண் வணக்கத்தை தெரிவித்துக் கொள்கிறேன். சிறந்த பன்னாட்டு கருத்தரங்கில் கலந்து மாணவ மாணவிகளுக்கு மிக சிறந்த அறிவுரை மற்றும் அவர்களுடைய நாலேஜை டெவலப் செய்வதற்காக பேச்சாளர் அனைவருக்கும், கருத்தரங்கில் பங்கேற்ற மாணவ மாணவிகள் அனைவரும் சிறப்புற உள்வாங்கி திறனை மேம்படுத்திக் கொள்ளுமாய் கேட்டுக்கொள்கிறேன். நன்றி.
Thank you, sir. Alone, we can do so little. Together, we can do so much. I request the Principal, Conference Chairman, Dr. T. Balasubramanian, the man of distinct vision and a fountainhead of illuminating ideas and experience and inspiration to all of us, to deliver the felicitation address.
Honorable Founder, respected Secretary and Joint Secretary, distinguished today Lifetime Achievement Awardee, Dr. P. Dhananjayan, Vice Chancellor, St. Peter's University, Chennai, Dr. N. Gunasegaran, Dean, Research and Development, St. Peter's University, and Founder President, Indian Spectrophysics Association, distinguished today Lifetime Achievement Awardee, Dr. K. Sendilkannan, Professor G.S. Pillai, Arts and Science College, Nagapattinam, Dr. M.N. Ponnusamy, Professor, Center for Advanced Studies in Biophysics and Crystallography, University of Madras, distinguished eminent personalities and speakers of this international webinar, dear participants of various institutions in India and other countries, dear HODs and staff members, dear students of our institutions, pleasure morning to all. I first thank our management gave permission to conduct this international webinar on physics of emerging materials and molecules. I thank Dr. N. Gunasegaran, Dean, Research and Development, St. Peter's University and Founder President, ISPA, for giving consent to collaborate with us to conduct this webinar. I convey my heartfelt wishes to the Lifetime Achievement Awardees, Dr. P. Dhananjayan, Vice Chancellor, St. Peter's University, Chennai, and Dr. K. Sendilkannan, Professor, G.S. Pillai, Arts and Science College, Nagapattinam. I thank our resource persons for accepting our invitation amidst their busy schedule. I convey my heartfelt wishes to head and staff members of PG and Research Department of Physics, Sri Vidya Mandir Arts and Science College, for their tireless effort for organizing such a wonderful gathering. Science and technology can be divided into basic science and applied science and technology, which are intended primarily to meet specific social and economic needs. The direction of scientific and technological development is influenced by various economic factors and conditions, as well by national and social needs. As the time prime mover for such a drastic change in the social environment, applied science and technology will positively promote new growth industries and highly competitive sources. I hope this webinar gives you all knowledge about physics of emerging materials and molecules. I convey my best wishes to all the participants. Thank you for the opportunity.
Thank you, sir. Correction does much, but encouragement does more. I request the conference chairman and vice principal of Sri Vidya Mandir Arts and Science College, Dr. N. Gunashegaran, a seasoned scholar and a navigator of this flagship of knowledge, to present the felicitation address.
The most venerable founder of the Sri Vidyamandir Arts and Science College, most respected Secretary through R.P. Raji, most respected Additional Secretary through P. Venkatachalam, most respected Principal Dr. T. Balasubramanian, most illustrious and distinguished Dr. S. Unasegaran, Conference President and Dean, Research and Development, St. Peter's Higher Institutions and Research, Education and Research, Chennai, and Founder, President, ISPA. The conference awardees, Dr. P. Dhananjayan, Vice Chancellor, St. Peter's Institute of Higher Education and Research, Chennai, and Dr. K. Sendil Kannan, Professor G.S. Pillai, Arts and Science College, Nagapattinam, and the most distinguished speakers from various nations and states of India, Dr. M.V. Reddy from Canada, Dr. Suresh Sugadevan from Malaysia, and Dr. Jibon Border from Bangladesh, and other dignitaries and invitees and speakers, special speakers from various universities and institutions and colleges, stockholders, professors, research scholars, and my beloved students. A pleasant morning to one and all gathered in the webinar. Today, I feel very much pleasure and delighted to know that the PG and Research Department of Physics organizing a two-day international virtual conference on physics of emerging materials and molecules. We know the Department of Physics always stands unique and being the best role model to all the other departments and faculties in all the steps of their life, in academic and non-academic activities, and also research. Since the inception of the department, 2000, the very first batch itself, the Department of Physics has secured and produced the gold medal in Periyar University, Salem. Since then, it has been maintaining its uniqueness by producing a number of gold medals and ranks, and also in result above 99%, almost sometimes 10% result, and in academic and research excellence. So there is a saying by a greatest German physicist, Albert Einstein, that try not to become a man of success, but rather try to become a man of value. I think the faculty members and the students of this department always trying and taking effort not to become a success man, success human, but to become a valuable lifetime achievers. And in this juncture, the speakers almost 14 topics and speakers of around 20 from various universities and colleges throughout nations and within India have been consented to be the speakers and the keynote addresser to this international virtual conference. And I hope the title of the conference as well as the topics of each speakers are need of the hour, including what we are facing, the COVID-19, the corona pandemic situations. I have seen some of the topics also cover a topic that what we face, the struggling life since 2020 March till now. And I think all the speakers' address and their lectures would be much beneficial to the scholars and professors and stockholders. And I hope this conference today, virtual international conference, would bring out the better output and useful to all the scholars and professors and participant students. And I conclude with the request to all the participants and scholars to make use of this program and make it a grand success. Thank you for the opportunity. Thank you, Ananda.
Thank you, sir, for the valuable felicitation address. Practice does not make a man perfect. Only perfect practice makes a man perfect. Dr. M.N. Konaswamy, Doctor of Science, Emeritus Professor, University of Madras, Tansawadi, has published 313 papers in international journals. He has presented about 207 research papers and supervised 32 PhD scholars and 100 MPhil students so far. He is bestowed with 10 prestigious awards from different organizations that include the Tamil Nadu Scientist Award and ISPA Veteran Scientist Award. His research areas are macromolecular crystallography, small molecular crystallography, computational molecular biology, bioinformatics, and theoretical crystallography. Let me take the privilege to invite the man of simplicity and perfection, young by heart, Professor M.N. Konaswamy, Emeritus Professor, Center for Advanced Study in Crystallography and Biophysics of University of Madras, Chennai, to deliver the keynote address.
Okay. Thank you very much for the nice introduction about me. Can you hear me? Can you hear my voice?
Yes, sir. We are able to
Yes,
hear
sir,
your
we
voice.
can hear you. We can hear you.
I'm so happy to participate in this international virtual conference on physics of energy materials and molecules. As our president rightly pointed out, this is a nice topic to discuss the latest kind of information about the research activities and whatever the things in this virtual conference. And I can actually able to see that really a lot of knowledgeable people are going to talk on this conference. Anyhow, to start with, I think it may be kind of appealing if I can talk something about something in Tamil. I think it's not a mistake. Okay. எண்ணும் எழுத்தும் கண்ணெனத்தகும் என்ற கோட்பாட்டை தானம் மனம் மற்றும் கருத்திலே தாங்கி நகர்ப்புறம் அல்லாத ஒரு சிற்றூரில் இவ்வளவு அழகான கல்லூரியை அமைத்து அனைத்து இன மக்களுக்கும் தன் மாண்புறு சேவையை செய்து வரும் எங்கள் தாளாளர் மதிப்பிற்கும் மரியாதைக்கும் உரிய சந்திரசேகரன் ஐயா அவர்களே, ஒரு மரம் மிக்க சுவையுள்ள மாங்கனிகளை தருவது உண்மைதான். ஆனால் அது பூத்து காய்த்து பின்பு கனியாக மாறும் வரை அதனை போற்றி பாதுகாத்து எப்படி பூவிட்டு கனியாக காயாகி கனியாகும் வரை அதை செய்ய முடியுமோ, அந்த காத்தல் தொழிலை மிக அழகாக செய்து இறுதியிலே நமக்கு அழகான அந்த கனியை கொடுத்து சுமக்க சொல்லும் பெருமை மிகு எனது தம்பி பேராசிரியர் குணசேகரன் அவர்களே. அவரை பற்றி சொல்வதென்றால் நான் எத்தனையோ சொல்ல வேண்டும். எத்தனை இடர்கள் வந்தாலும் இனிய முகத்தோடு செயலாற்றி இறுதியில் அனைவரது உள்ளங்களையும் குளிரை செய்யும் மிகவும் குற்றால அருவியை போன்ற ஒரு ஆற்றல் பெற்றவர் என்னுடைய தம்பி குணசேகரன் அவர்கள். அவர்கள் ஆரம்பித்த இந்த ISPA இந்தியன் சொசைட்டி ஆஃப் ஸ்பெக்ட்ரோபிசிக்ஸ் அசோசியேஷன் மற்றும் வித்யா மந்திர் ஆர்ட்ஸ் அண்ட் சயின்ஸ் காலேஜ் இணைந்து இந்த வெர்ச்சுவல் கான்ஃபரன்ஸ் வெபினாரை நடத்துவது என்பது மிக அழகான ஒன்று. இது தொடர்ந்து தொடர்கதையாக நடத்தி கொண்டிருக்கும் பேருடையது. கடந்த 10 ஆண்டுகளுக்கு மேலாக இந்த செமினார் கான்ஃபரன்ஸ் நடந்து கொண்டுதான் இருக்கிறது. நாங்களும் ஒவ்வொரு முறையும் உரையாற்றி கொண்டு இருக்கிறோம். அண்ட் டெலிகேட்ஸ்க்கு தேவையான இன்ஃபர்மேஷன்ஸ் கொடுத்து கொண்டுதான் இருக்கிறோம். பெருமைமிகு செயின்ட் பீட்டர்ஸ் பல்கலைக்கழகத்தின் துணைவேந்தர் அவர்கள் இந்த லைஃப் டைம் அச்சீவ்மெண்ட் அவார்டை பெறுவது என்பது போற்றுவதற்குரிய ஒரு சரியான செய்தியாகும். மேலும் திரு டாக்டர் செந்தில் கண்ணன் அவர்கள் பேராசிரியர் குணசேகரன் விருது பெறுவதும் ஒரு சரியான செயலையாகும். செந்தில் கண்ணனை பற்றி சொல்வதென்றால் எந்த ஒரு இடத்திலும் தன்னுடைய ஆராய்ச்சியை நிலைநாட்ட முடியும் என்பதற்கு அவர் ஒரு பெரிய எடுத்துக்காட்டு என்றே கூறலாம். நாகப்பட்டினத்தில் இருந்து கொண்டு ஒரு சிற்றூர், நாகப்பட்டினம் என்பது ஒரு சிற்றூர் என்றுதான் நான் கூறுவேன். அங்கு ஒரு கல்லூரியிலே பேராசிரியராக இருந்து கொண்டு இவ்வளவு பெரிய சாதனையை நிகழ்த்துவது என்பது இயலாத காரியம். ஆனாலும் இடம் பெரிதல்ல, எண்ணம் தான் பெரிது என்ற கோட்பாட்டை தன் மனதில் தேக்கி இவ்வளவு அழகான ஆராய்ச்சிகளை செய்து இந்த குணசேகரன் அவார்டை பெறுவது என்பது மிகவும் போற்றுதலுக்குரிய செயலாகும்.
Professor Ponuswamy garu, please speak in English. Unable to understand Tamil.
Oh, you want me to speak in English? Okay. So I thought, I want to, the delegates, I just want to do some, okay, I can speak in English, it's not a problem, okay. And I'm so happy that our secretary, Raji gave a nice address about the awardees. And then Honorable the Additional Secretary, Mr. Venkachalam, the respected principal of the college, Dr. Balasubramaniam, and the vice principal, Venkachalam, Gunasekharan, and then I can also be able to see that our convener, Dr. IVCPEMM, he put enormous amount of effort to bring back all the people together and conducting this conference, and the supporting faculty, Dr. Suresh, who is the organizing secretary, and the person who is going to give the word of thanks, Dr. Venkatesan, and my dear delegates and my colleagues, all my good students. I feel it a pleasure to participate in this nice conference. As I told you, it's a real kind of a beautiful conference and a nice topic. And I don't want to take a lot of time to say a lot of things right here, because we can talk about an hour or 2 hours about the people as well as the conference and so many kind of things. Maybe I can actually able to do a couple of information to the people, and then I can put a full stop to my topic. All that, as our president pointed out, creativity is the best kind of thing. All that we can say that we are all doing research. There is no doubt about it. But the creativity is the one which actually a little bit different from the conventional one. So solving a structure, I'm just saying solving a crystal structure, for one of the crystal structures is the same thing. We get new kind of information so that we can able to publish, and it will come out as a good paper in the research, good journal. but creativity is the one that we can actually able to make it from the conventional kind of research. So something different from the conventional one, right? Solving another structure, like that. It's a conventional kind of this thing, but if you can actually able to do it something different from this conventional one, which is called as creativity. So those people are honored with the Nobel Prize. But anyhow, when all people cannot come to that level, but in fact, if we want to achieve, then we have to think in a different way from the conventional way, so that we can actually achieve real kind of this thing. Coming down to what you call the real conference about this thing, light. Light is the one. If you can say light as the word to our president, he will talk about 2 days about light. I mean, all that, just we can actually think LIGHT, a simple few letters will constitute light. But our President Gunasekharan will talk about maybe for a year continuously about light. தமிழ்ல சொன்ன போனா ஒளி இல்லாத உலகம் உண்மை இருட்டுதான். ஆனா ஒளி இல்லாததிலும் இருட்டிலேயே மூழ்கிவிடும் என்பதுதான் அவருடைய கணக்கு. So, and all that we can actually able to see that our Nobel laureate, Sir C.V. Raman, has done enormous amount of work on light, and all that you people are well aware of the fact that you are awarded the Nobel Prize, and we are celebrating this event as a science day because the invention was made on this particular day, 28th February, way back in 1928 actually. And all that I can actually able to say that we can do creativity research, or we can do a conventional research, whatever the kind of this thing, but we have to concentrate and do the research, and whatever may be the kind of information that we have to publish all the information that you have found out. That's what more important kind of thing that I want to say. So the publishing the information to the world is the important kind of thing. So I just, as our president pointed out, for the budding scientists, I just want to say that I have to do research. That's not a big problem, but whatever the kind of research that you can actually get it in your hand, that you have to publish it and put it in the outside world. Then only, maybe not tomorrow or the other day or something like that, maybe after 5 years or 10 years or 20 years, your point of information will be read out, and maybe somebody will get some kind of idea from that knowledge, so that he can actually able to do research in that particular area. So I can actually able to insist that whatever the kind of information or whatever kind of research that you can actually able to do, that you have to publish it in a nice way. And as our president pointed out, HNDX is of course important. I'm not denying it, but whatever may be the case, that we have to publish it to the outside world. And all that, I want to insist another specific point, that you will never think about negativity. So as our Thomas Alva Edison pointed out that தமிழ்ல சொல்ல போனாக்க தோல்வியிலும் வெற்றி, that he has lost the information, but he has succeeded, that he cannot able to use that particular element as element for that life. That's his victory. So never think about negative kind of, even if you are defeated, or even if you are failed in your attempt, but never think that you are failed in your attempt, but you can actually able to think that this is a positive side, that you can actually able to proceed further. கீழே விழுவது மீண்டும் விழுவதற்காகவே அப்படின்னு சொல்லுவாங்க. கீழே விழுந்துட்டாக்க நம்ம அப்படியே படுத்துறது இல்லை. We have to get up and do again, make a further step, so that we can proceed further. So the fundamental thing is that the negativity factor will not come to your mind at all, so that you can actually able to achieve whatever the kind of thing in your life. I used to say that one particular point all the time about what do you call this Hiroshima Nagasaki event. Way back in 1940s, you people are well aware of the fact that the topmost scientists of 20 people were invited by the President of America. You know, America is the biggest country in the world, and the President invited some topmost scientists, including Professor Linus Pauling, to establish or to invent this atom bomb. But the only person, Professor Linus Pauling, got up in that meeting and told that, Mr. President, inventing an atom bomb is not a big problem, but whatever the kind of thing, you have to use that atom bomb only for the positive purposes. So producing electricity or whatever the kind of this thing, for it has to be beneficial for the human being. That's what the kind of thing that I want to say right here. But the president didn't hear his words. Then Ryan Sparling boldly told that I want to put this proceedings. I don't want to involve in this kind of invention at all. Then he came out. So I mean, you think about that. He opposed the idea of the president. He came out. But whatever may be the case, that atom bomb was invented and it was tested way back in 1945, August 6th and 8th in Hiroshima and Nagasaki. And when you know that lakhs and lakhs of people were collapsed right in there, and they lost their some of the organs down. In addition to that, a lot of people were irradiated, so many kind of unwanted materials. So even now, the thing is there. So தமிழ்ல சொல்ல போனா மனிதாபிமானமற்ற ஒரு மகத்தான செயல் அப்படின்னு சொல்லி சொன்னா இதுதான். மகத்தான செயல் சொல்லக்கூடாது, மனிதாபிமானமற்ற ஒரு ஈனமான செயல் சொல்லி சொல்லணும். So killing people in an unwanted way, that's what the main kind of thing. So people realize it, and afterwards, and of course, they what do you call the situation has come down. Now the thinking factor is reduced on the negative side, and people are now doing kind of progress on this side. So you can also be able to say that the negativity definitely will pay big loss to the human society as well as to the world. And the other more important kind of thing that I want to say, that nothing is impossible in the world. So I just want to address to the young scientists right here, nothing is impossible in the world. You know that our Napoleon pointed out, impossible is a word to be found only in the dictionary of fools. So nothing is impossible. That I can actually put to say one example of what do you call this impossible thing is possible is the biggest kind of President Barack Obama. So you know that in the history of American history, it will never happened before, but that kind of this thing was broken by Obama, and ஒரு பெரிய we can say in Tamil that ஒரு தத்துவார்த்தமான கோட்பாட்டை உடைத்திருந்த பீஸ் ஆக்கியவர் ஒபாமா என்று சொன்னால் அது மிகையாகாது. So he has won it, and he stayed as the president for 8 years, and he has done a lot of things. I mean, positively, he has done a lot of things to the world. So you can actually think that you just get away your impossible kind of feelings or thoughts in your mind, and you can actually able to proceed further. So if you can think in that particular direction, as in the physical world as well as in the research world, it will definitely do some kind of positive results to all of you. I can also able to say a lot of things right here. Due to the lack of time, I don't want to say prolong many things. All that ஒரு 3-4 தமிழ் வார்த்தைகள் மட்டும் சொல்லிட்டு நான் முடிச்சிடுறேன். அறிவியல் என்பது கற்க மெருகேறும் ஒரு அழகான செயல். ஸோ அறிவியலை நீங்கள் உணர்ந்து கற்று மேம்பாடு அடைய வேண்டும். இந்த மாதிரி the kind of conferences that we have to get together and share our information to all of the other people, so that we can actually able to realize, take home the messages and realize, so that we can do a lot of these things. தமிழில் திருவள்ளுவர் ரொம்ப அழகா சொல்லியிருக்காரு, உவப்ப தலைகூடி உள்ள பிரிதல் அனைத்தே புறவர்களின்னு சொல்லியிருக்காரு. அதாவது நம்ம வந்து happily we can actually able to join together, discuss the issues, problems, and whatever the kind of information that solve it and share it, so that we can actually able to put our steps in the higher level. We feel proud, so that we can go up. So காலத்தை, I mean, if you can actually able to spend time and you can actually able to do the hard work, and you can able to get away with negative feelings, definitely you can achieve in the positive direction, and tomorrow definitely a history behind you will be there. So kindly follow all the specific and information and instructions given by given by our great people, our president, our principal, our vice chancellor, Dhananjayan, our vice principal. They all of them gave a nice kind of information to all of you, and build your research. I mean, go higher steps above and above. That's what I want to convey to you all. So I'm so happy that the opportunity is given to me to say a few words in front of all of you. So I'm sure that you all will be benefited for the next couple of days, and take home the beautiful kind of messages in your heart. Thank you so much for the opportunity. Thank you. Thank you very much. Thank you very much.
தங்களுடைய ஆழ்ந்த சிறந்த அறிவியல் கருத்துக்களுக்கு அடங்கிய திறவுரைக்கு மிகவும் நன்றி ஐயா.
Thank you, thank you, thank you.
Saying thank you is more than a good manners. I request Mr. K. Venkatesan, coordinator of the conference, to propose the vote of thanks.
Very good morning to all. Honorable Founder, Honorable Vice Chancellor of St. Peter's University, Honorable Conference President, most valuable professors, respected Secretary, Additional Secretary, respected Principal, Vice Principal, staff members, scholars, and the students of our and other institutions. It's my privilege to offer thanks on this occasion. I, on behalf of my colleges and the entire community, first of all, I would like to spread my most sincere thanks to the Lord God. I want to thank the chief guest who gave his vital time from their busy schedule to grace this function. First and most, I must remark the profound sense of gratefulness to our founder, sir, for his everlasting support to conduct this type of events. Further, a big thanks to Master of the International Virtual Conference, Honorable Professor Dr. S. Gunasekaran sir, Dean of Research and Development, St. Peter's University, Chennai, founder and the president of ISPA, for his continuous support around the years to make this event happen and conferring the awards. I should mention the deep meaning of their appreciation and the thanks to the Lifetime Achievement Awarder, Honorable Vice Chancellor Dr. P. Dhananjayan sir, St. Peter's University, and ISPA Dr. S. Gunasekaran Awarder, Most Valuable Professor Dr. K. Sendilkannan sir, G.S. Pillai Arts and Science College, Nagapattinam, for the acceptance of the award. Thank you, sirs. I may like to express our sincere thanks to Honorable Professor Dr. M.N. Ponnusamy sir for his keynote address. I may like to express our sincere thanks to our most respectable Secretary, through R.P. Raj sir, most respected Additional Secretary through P. Venkatachalam sir, for their encouragement and the felicitation. A big thank to our venerable Principal sir, Dr. T. Balasubramaniam sir, respected Vice Principal Dr. N. Gunasekaran sir, for their efforts towards to make this happen. I also wish to express my gratitude Dr. S. Suresh, Controller of Examinations, Sri Vidyamandir College, for his focal theme about the international conference. Thank you, sir. I also wish to express my gratitude to our head of the department, Dr. R. Arivichelvi, for her constant tireless effort towards the virtual conference to make it a huge success. Thank you, ma'am. I would like to place my hearty thanks to all the head of the departments, staff members of various departments of our institution and other institution, research scholars, students, because of whom we made this meeting possible. Thank you, Anadal. I also want to thank the people who worked behind the screen to execute this event, our technical arrangement team, non-teaching staff, media persons for their support. I can't thank everyone enough for their involvement and their willingness to take on the completion of the task beyond their comfort zone. Thank you. Thank you, one and all. Thank you.
Thank you, sir. Let's assemble for the technical session now. Over to Professor MNP, sir.
Okay. Can we start that right now? Hello. Can we start the technical session right now?
We can start the technical session, sir, right now. No
Okay,
problem.
right, straight away we can start it.
Okay, sir. Okay.
Okay. One second.
Thank you.
Sir, good morning, sir. I am Jayvel here from Anna University.
Very good morning, sir. Very good morning.
Sorry.
Jayvel, one second.
Excuse me, sir. RJ, sir. RJ, sir.
Hello. Good morning to all of you. Hello.
Yes, sir.
Okay.
Happen to be the first talk is our.
Good morning, Professor Jayvel. This is Jay Shankar.
Good morning, sir. Good morning. Yeah.
Okay. Can we start the session?
Yes, sir.
Okay. I'm sure that our beloved Professor Jayvel is right here, and all that I can say a lot of things about Professor who is going to be the future Vice Chancellor of any one of the universities in Tamil Nadu. I'm just saying only in Tamil Nadu, I don't want to say. And he was the director, the Dean of Research of Anna University, and he was heading the Nano Science and Technology Department in Anna University for the past almost 10 years. He's a very good speaker and has given so many talks at the national level as well as the international level. And he's going to talk, he's the first person is going to talk about two-dimensional nanostructures for energy storage applications for next generation electric vehicles. I'm sure all you people have to concentrate and try to as much possible try to understand and if you are having any specific kind of doubts, kindly reserve your questions and our Dr. Jayvel will answer all these questions. Now I to deliver the address. Pardon me?
Small intro of RJ success.
Yeah, you carry on now.
Okay.
Now, we are going to start our first session on the first day of our International Virtual Conference. Research is to see what everybody else has seen and to think what nobody else has thought. According to the quote, we are here have an eminent professor, Dr. R. Jayvel sir, Professor, Crystal Growth Center, Coordinator, Center for Nanoscience and Nanotechnology, Anna University, Chennai. Now, I request our Assistant Professor, R. Dinesh Kumar, to give intro about our eminent professor.
Good morning to one and all present here. It is my great honor and pleasure to introduce the speaker, who is my PhD guide, well-wisher, and Professor Dr. R. Jayvel sir. And I am very much happy to introduce him. And I thank Almighty of God for making this wonderful opportunity. Dr. R. Jayvel sir was born in an agriculture-based family, a village called Sittarkoil in Salem district. He had his school education in government school Salem, and he got his BSc and MSc degree from University of Madras. Professor Dr. R. Jayvel sir started his research career in the field of crystal growth and was awarded PhD by the Anna University in the year 1995. Sir's passion on teaching made him to start his career as an assistant professor at the Crystal Growth Center, Anna University in the year 1995. Later, He was promoted as an associate professor at Crystal Growth Center in the year 2006. In the year 2009, he was elevated as a professor at Crystal Growth Center, Anna University, Chennai. Sir has 25 years of teaching experience and 30 years of research experience. And due to his tremendous effort, he got MTech program on nanoscience and technology at Anna University, Chennai, which was sponsored by DST in the year 2008. And he served as a director, Center for Nanoscience and Technology, Anna University, from the year 2005 to 2015. Over 10 years, he was served as a director, and he was the first director for the Center for Nanoscience and Technology. Sir served as a director, Center for Research, Anna University, from 2015 to 2018. He received many awards and recognition. Dr. R. Jaivel sir was awarded the topmost award of the state, that is Tamil Nadu Scientist Award in the field of physical science for the year 2016. He got a Lifetime Achievement Award by Indian Spectrophysics Association, ISPA, in the year 2019. Due to time constraint, among this, I list a few. Fellowship of Award of Science, Chennai. Research Excellence Award by Anna University in the year 2019. Leadership for Academician Program Fellowship by MHRD, Government of India, in the year 2019. Highly cited author by Royal Society of Chemistry, UK, in the year 2018. Active Researcher Award, Anna University, in the year 2012. Honorary Guest Professor, Shizuoka University, Japan, in the year 2009. Japanese Government Award for Foreign Expert in the year 2004. Special Researcher, National Institute for Material Science, NIMS, Japan, in the year 2001. Dad Sandwich Model Fellowship to visit Germany in the year 2000. Sir has visited to various countries as visiting professors like University of Queensland, Australia, University of Göttingen, Germany, Research Institute of Electronics, Shizuoka University, Japan, University of South Australia, Adelaide, in the year 2006. Sir has published more than 500 research articles in international recognized reputed journal with a high impact fact, with H index of about 49, I-10 index 249, and citation was about 9,258. Under his research mentorship, around 40 PhD scholars have been awarded degree, and I am one among them. And I am proud to say that I am the student of Dr. R. Jaivel sir. 4 are currently pursuing doctoral research. Professor Dr. R. Jaivel sir has been collaborating with eminent researchers within India and abroad. He has carried out research projects which was sponsored by national funding agencies such as UGC, DST, CSIR, and DRDO. And I thank you to one and all, and thank you, sir, and Dr. R. Jaivel sir.
Thank you, Dinesh. Thank you for your exhaustive introduction. And I know the time is very short, and I had another meeting. That's what I requested Dr. Arivil Chelvi to just continue the technical session. Okay, so let me just share, and I think I have to be permitted by the host to share my slides. It says that host disabled participant screen sharing. Okay, Dinesh?
Yes, sir.
Okay.
Yeah. And you have to permit me to share my screen.
Yes, sir. Jaivel sir. Yes, sir. Sir, just a minute, sir.
Okay, okay. I am very happy to see galaxy of people here. You know, that was because of the online program. So, but Professor S. Gunasekaran and myself, we had been to Vidyamandir College, I think 3 or 4 times, and it was a very lovely campus, and I could see a lot of participants for this conference also. Can I just share the screen now?
Sir, just a minute, sir.
It's coming.
Sir,
Yeah,
share right thing, sir.
Yeah. Okay, are you able to see the slides now?
Yes, sir.
Yes, sir. It is visible, sir.
Okay, yeah. So without taking much of your time, let me just get on to the topic of discussion today. I'll just take 25 minutes because I have just postponed my meeting scheduled at 12 o'clock to 12:15. Okay, please pardon me. And this is the topic going to be on basically the energy storage technology, which is a very potential technology for the electric vehicles. But you know, the electric vehicles are already running with batteries, and that is what I have just titled as next generation electric vehicles. And if you just see, as a physics students, you are all very familiar with this kind of storage systems, like from batteries to the integration of different kinds of batteries. And we have a very huge storage technology available now. This is directly connected to energy power sectors to store a large amount of energy for future usage. And this is actually the grid storage, which is also another important storage technology where we can significantly reduce the the power loss during this time. And when we talk about different technologies, it's also very mandatory that we have to think of the green technology, where it is very considerably reduced the environmental impact or environmental pollution when using this high-tech area. So today I'm going to discuss about the material aspects of this energy storage technology, and also just to give a brief introduction about the material which we have been working on in our laboratory almost for the past decade, and different kinds of energy storage systems. And I don't think I'll be able to focus on these topics because the time is very short. And because of the young researchers, I'll just give the flavor of the importance of this technology and also the materials choices, so that those who are interested in taking up the research can pursue in this area. Okay, so just let me give the introduction about the 2D materials. 2D materials are a special class of materials, which is nothing new because it's all very well-known materials. But based on the structural properties, this has been designated as 2D nanostructures, because when you talk about the individual layers, which is typically sub-nanometer scale. So therefore, when you talk about 2D, it mainly means which are all nanostructures, because we bulk, we don't, we always consider as a 3D materials. So the examples of these 2D materials are graphene, which is a very well-known material now. It's almost more than 15 years. It was discovered in 2006. And then we have hexagonal boron nitride, molybdenum disulfide, tungsten selenide. This is only representative examples, but there are plenty of other materials available under this category. And the specialty of this material is it was possible that we can isolate the individual layers when we have a layered structure like this. And each layer is of a few angstrom unit thick. So therefore, it's all sub-nanometer scale. So we have different kinds of sulfides, oxides, and nitrides, which are classified under this category as 2D materials. And the other interesting phenomenon of this material is that it has got multifunctional properties. For example, if you take hexagonal boron nitride with the energy gap of more than 5 electron volt, this is a perfect insulator. And some materials like MOS2 or tungsten selenide, which behaves as a semiconductors. And some of these materials are called as half metals, and some of them are semi-metals with zero band gap energy. And some materials are having very high conductivity, which are called metals. And some of them has a very extreme conductivity, and those materials are called superconductors. And if you look into the absorption capacity of these materials, it almost covers the entire electromagnetic spectrum, starting from UV to visible to NIR to mid-IR, far IR, terahertz, and including microwave frequency also. There are a lot of interesting areas. People are concentrating on these materials, mostly about the defect engineering, because Even if you take bulk material, defect is a very important phenomena. And nowadays we talk about what is called quantum materials, because which always deals with the defect engineering of defects and how these defects can be capitalized for very specific applications. And therefore defect engineering is one of the important areas. Basically the structural engineering, because of the complex nature of this material, and the phase tuning for a very specific requirement. These are some of the areas where people are working worldwide, and we are also working on this kind of areas. And just to introduce about the application of these materials, as I said, this has got multifunctional properties starting from communication. We can use it for digital and analog circuits, and it can also be useful for interconnects, memory applications, and sensors. And sensor is a major area of application. And if you take sensor alone, these 2D materials are widely used for electrochemical sensor, which is the more dominant area, followed by fluorescent sensors, colorimetric sensors, photoelectrochemical sensors, or electroluminescent sensors. And we can also do FETs, field effect transistor sensors. And in the case of electronics, as a physics people, that we are all very familiar with what is called VLSI technology. And now the VLSI technology is moving towards what is called ultra large scale integration devices, ULSI. And these kind of materials, the nanostructures, has taken the technology to the ultimate limit of what is called extremely large scale integration devices. So that means we can integrate millions and millions of transistors together in a single chip. And when you say extremely large scale integration devices, it doesn't mean that you fabricate 1 million transistors separately and then try to integrate. That was not possible. So what they do is they just make this kind of material. This is actually a graphene material. And it was possible that we can have individual electrons which can perform a transistor action. And it is easy to fabricate millions of, assemble millions of atoms together in a given circuit. So therefore, we can realize what is called extremely large scale integration devices. So apart from that, mostly these materials are highly flexible. So we can have different kinds of flexible applications like flexible sensors, or we can have transparent conductors or wearable electronic devices. There are a variety of application possibilities using this. In the case of biomedical area, it has got wide range of applications starting from diagnostic to therapeutic to bioimaging applications, biosensing, and it can also use this material to some extent for biosafety also. And it has got again plenty of opportunities in photonics area to fabricate new structures with very enhanced properties. I'll just give only one example, because as I said, we have molybdenum disulfide, tungsten diselenide, or hexagonal boron nitride. And this graphene is a very well-known material now. As I said, it was discovered in 2006, and then the Nobel Prize in Physics was awarded for this discovery in 2010. And this is the typical layered structure. And the graphene refers to a single atomic layer structure like this. And the typical layer thickness is of the order of few angstrom unit. And therefore, it's called a single atomic thick graphite plane, which refers as graphene. So basically, this graphene can be fabricated from this kind of natural graphite. This is the source material used for this graphene. And the advantage is that it has got the two-dimensional hexagonal lattice of carbon. And the carbon-carbon bonding is the strongest known bond in nature. So therefore, it can have a very high mechanical stability and mechanical strength. Very similar to, even better than the carbon nanotubes or fullerenes. And hence the application possibilities is very wide. Like we can use it for graphene electronics, as I told about the extremely large scale integration devices. And we can also use it for lithium-ion battery as a storage. And it has got a very high surface area of the order of almost 3,000 meters square per gram. So that means if you prepare 1 gram of material, the area available for application is almost 3 square kilometers. So therefore, it has got a lot of interesting applications. And supercapacitor is the recent development using this material. especially for energy storage application, large scale energy storage applications compared to batteries. And people have also demonstrated OLEDs, organic light emitting diodes, using this material. Recently, this graphene oxide has been realized as a very stable coating, as an antiviral coating, and there was a special scheme introduced by the Department of Science and Technology to make use of this kind of antiviral coating for face mask or personal protection equipment like PPEs for exclusively for the protection from COVID-19 kind of thing. So this kind of pandemic also has some ways that this material can be effectively useful for societal applications. So we have been working on 4 verticals based on this graphene material. We work on graphene FET, especially for sensors. And it is not a conventional gas sensor or humidity sensor or chemical sensors. These sensors are actually advanced level sensors where we can use it for DNA hybridization sensing or high energy radiation sensing or sensing of NBC, nuclear, biological and chemical weapons. And those kind of high-end applications are possible using this kind of material. And as I said, it has got a very strong photocatalytic activity, so we can use it for a variety of applications for environmental remediation or wastewater treatment or industrial effluent treatment kind of applications. And another area which we have been working on is actually the solar cells, and we can make very compact, miniaturized solar cells, which is almost 10 times size reduction compared to conventional silicon. Because the silicon is the mature technology today. We have all installations, but the major problem with silicon is that the space. We need a large area when we go for large installations. And it has been theoretically proved when we have this kind of graphene integrated with quantum dot structures, we can have the photoelectrons observed on the surface of 1 square meter silicon surface is almost equal to 10 centimeter square area of this kind of structures. So that is what it's coming up in a very big way. But the thing was, as of now, the conversion efficiency is only 1/4 of the silicon technology, but it is only coming up now. But it has a very high potential in future expansion to match with perovskite solar cells or silicon solar cell structures like this. So this is actually the supercapacitors, and because of the flexibility, it was possible that we can have a very flexible solid state supercapacitors without any solid electrolyte. And we can also have liquid electrolyte if we use it for battery and small scale applications. So these are the some of the applications of this. And I'll just give about the energy storage technology. I'm sure that you are all very familiar with this kind of e-bikes now and electric bikes, which are all already available both commercially as well as domestic usage. And all these electric vehicles, they make use of batteries. And the speed of this vehicle or the cost of the vehicle depends on the capacities of these batteries. And so it ranges from 1 to 1.2 lakh to almost 6 lakh. Now we have more than 10 lakh worth of two-wheelers based on electric vehicles. And we have three-wheelers or four-wheelers, even heavy vehicles also now running now based on the batteries. So the main difficulty was about the maintenance of lithium-ion battery, because the problem was lithium-ion is basically, the battery was discovered in 1970s and it was commercialized in 1990s by the Sony Corporation. And the Nobel Prize in Chemistry was awarded for the discovery of this lithium-ion battery in 2019. And we have worldwide, there are a lot of commercial production facilities, including Asia Pacific means that the major facility is located in China. And almost, if you just see the 2019 requirement is about 7 billion units of these batteries, mainly for to meet with automobile industries. Apart from that, China, then we have facilities in North America, Europe, and Middle East, and also to some extent in South America also. But in India, the problem was like, we have already adopted the lithium-ion battery technology for our electric vehicles. But the major challenge for the mass adaptation of electric vehicles is in India is the price, because it has got huge cost. And in fact, there was a very big discussion in the Lok Sabha about the import cost of lithium-ion batteries since 2006. And it was just rising until 2018-19, and then now there is a decrease, because the reason was that the import cost was very high. And the government has made a very major initiative to have this kind of indigenous development of these batteries, because we don't have lithium in India. We have to depend on Australia or China or some other South American countries. So without lithium source, importing lithium and then processing it and then making the batteries is not a viable solution. But still, the government has taken major initiative to develop these kind of things. And this is the indigenous development of lithium batteries. And there was an agreement between the Sekri Karakudi, and there is a Bangalore-based company called Rasi Solar Group company. And they have entered an agreement to develop the lithium-ion battery, and it was supposed to come very near to this the Sri Vidya Mandir College, and they have already located the place. And because of this lockdown and pandemic, there was some delay, but they expect that the commercial production will be out very in the near future. Apart from that, there are a lot of startup companies which focus on individual elements or components of electric vehicles, including batteries, battery innovations, and new areas like that. And not only for the laboratories or startups, and even Government of India has also taken up this technology in a major way, because ISRO is planning to supply the lithium-ion battery technology only to focus on automobile sector, and it is coming up in Bangalore in one of the ISRO centers. And in fact, there is also an opportunity for the private players to get into this venture, because the Indian Oil started developing batteries from the indigenous metals. As I said, the lithium is the major source for these batteries, and they have the IOL have some ore in Orissa and Chhattisgarh, and they have started using the local sources to power India's electric vehicle ambitions. So this is a kind of potential for batteries. But given with the lithium, and also the other thing is that lithium has a very high vapor pressure, and environmentally it is not very conducive, because those who have experienced the air travel, you are not supposed to take lithium battery in baggage. It has to be carried through hand luggage, because sometimes if the pressure increases, there is a possibility of explosion of this lithium batteries. And people also look for alternate battery materials, and we have different kinds of batteries like metal oxide based batteries, or phosphates and polymers, and sodium metals and aluminum, sulfur. Different kinds of materials are being involved for the development of batteries. And this kind of fluoride batteries are also very viable, because it has been proved that this kind of fluoride batteries can have almost 10 times more energy density than the lithium-ion batteries. And we have different kinds of graphene-based batteries, and this is actually air battery. Okay, so this also uses the 2D materials like MOS2 and lithium cobalt and lithium anode kind of things. So this is one way that the battery technology is developing. And the supercapacitor has been introduced as an alternative for the battery technology, because the supercapacitors can have very high power density compared to the batteries. And this is the fuel cell, and where you can have a very high energy density, but the power density is very minimum here. And if you have conventional capacitors, the power density is very high, but energy density is very minimum. So in order to have the compromise between these we have the supercapacitors, and it's also called as ultra capacitors, where we can have this kind of things. And another advantage of going for the supercapacitor is when you have the conventional rechargeable battery, and it takes a very long time for charging, discharging. But the supercapacitors have instant charging, discharging, so that especially when we use electric vehicles or long distance vehicles, it was easy that we can have charging done quickly, and also because of the discharge and a faster rate also ensures that the vehicle moves at a very faster rate. So this is actually the mechanism which I just skipped for want of time, and there are two ways that we can design this kind of supercapacitors. One is the electrostatic process, where we call it as double layer capacitors. Another one is the storage by electrochemical process, which is called pseudocapacitors. And the supercapacitor is known for almost for the past more than 2 decades now. The first supercapacitor electric they was used in electric vehicle in the year 1995 by Russia, and then China took up the challenge. That is what China leads still in the world for the manufacturing of this material, both batteries and supercapacitors. And in 2004, this was introduced to fast charging systems. This is the first electric charge system introduced in China. And this is in 2006, it was useful for commercial vehicles, or we call it as heavy vehicles for supercapacitors. And then from 2010 onwards, people started using these flexible supercapacitors, because these flexible supercapacitors are very user friendly, where we can have this kind of curved rooftops, or we can stretch it, or we can bend it without damaging their physical structure. So today we are mostly working on flexible supercapacitors, and these supercapacitors can also be rechargeable, so that we can use it for. So when you just look into the developments or evolution of this kind of supercapacitors, there are plenty of opportunities for applications, not only for small scale applications like memory backup or power backup systems. This is useful for these kind of high speed vehicles, and also the renewable energy integrated system. Like we have the solar installations, and solar installations can be integrated with this kind of power pack, so that power produced during daytime can be stored, and then whenever we want, this kind of power can be retrieved and then used for societal applications. So that is the kind of things. And really, if you look into the market share for the supercapacitors from just 2014 to 2020, there is plenty of developments. And the advantage was that the power density is very high for the supercapacitors compared to batteries, and then the energy density can also be considerably increased when we have the different material choices. And so the future requirement is that the supercapacitors can be useful for aerospace and defense applications, and these supercapacitors can also be useful for high-speed trains or next generation high-speed trains. And so if you just look into the defense application alone, we have application in avionics or emergency power or munitions, vehicle, radio frequency communication, radar, and these are all very things. And these kind of applications cannot depend on import material, because there will be an embargo that material cannot be used for this kind of defense applications. So it is better to develop our indigenous materials to meet with this kind of requirement for defense applications. So when you just look into the the supercapacitor sector, there are major things. One is about the material, another one is the storage capacity, and also design of this kind of batteries, including miniaturization and other kind of things, and application potential and future challenges. So there are plenty of opportunities to work with this kind of area, especially for high-end applications. And if you just focus on materials alone, we have different kinds of materials like metal oxides or traditional materials like elemental binary, or we can have different kind of conducting polymers, or different kinds of carbon forms, starting from graphite, graphene, fullerenes, carbon nanotubes. These are all basically nanostructures. And we have different kinds of metal oxide frameworks or metal nitrides, and then okay, there are plenty of material options for this. So if you just see the most suitable materials, as I said, we can have individual materials, carbon-based materials like activated carbon or carbon nanotube or carbon aerosols. And this material can be combined with this kind of polymers, and then or this can be combined with metal oxides. Then we can have a hybrid material or hybrid electrode for supercapacitors. And this kind of hybrid electrodes can have a very high specific capacitance of reaching almost 1200 farad per gram. And as a physics students, you are all very familiar with the capacitance, where when we use it for even BSc or MSc laboratory, the cylindrical capacitors capacities of the order of microfarad. Microfarad means 10 power minus 6, whereas this kind of things are 10 power 3. So you can have almost 9 orders of magnitude with higher capacitance. So therefore, it is useful for storing a huge amount of energy for this kind of electric vehicles or high-speed trains, or whatever way we want to use it. So metal oxides can be conveniently combined with this ruthenium oxide, and so there are a spectrum of material choices exclusively for this kind of supercapacitors. So I just wanted to convey to the young students that if you are interested in this kind of area, there are plenty of opportunities, because we have different kinds of metal oxides like iron oxide, tin oxide, manganese oxide, cadmium oxide, zinc oxide. Then these oxides can be combined with the polymers. We have different kinds of conducting polymers, so that you can make a very real hybrid electrodes which achieve very high energy density or power density to meet with various applications. Okay. So I think I'll stop with this, because I just have given the open problem for the young students if they are interested in making these materials and these sizes, because I have a large number of slides, but unfortunately I have to cut short and then things. Okay. So I think I'll just stop with this, and if you have any quick questions or clarifications, I'll be happy to clarify. Thank you.
Yeah, maybe a couple of questions, because owing to the paucity of time, we can have a couple of questions from the audience.
Thank you, sir. Thank you, sir.
Yeah.
Thank you for your wonderful talk, sir. Wonderful talk on two-dimensional nanostructure for energy storage applications. Dear participants, if you have any doubts or clarification, you may ask.
Hello, sir. I'm Dr. Nagaya Kambala. Hello.
Yeah.
Sir, actually, instead of using batteries, are like why people are not able to use this like a series connection of supercapacitor and battery? Is there any problem or any limitation? Can you please tell me?
No. Actually, the advantage of battery is still the energy density is very high for batteries.
Yes, sir.
Supercapacitors can have very high power density. So there is a compromise between these two.
Okay.
But the future development is that the supercapacitors with very high energy density or power density can be possible. But as of now, still the energy density cannot be matched with the battery. But now there is an integration between battery and supercapacitor. You can just heard of the word like supercapacitor.
Yeah.
This supercapacitor is a combination of battery and the supercapacitors. That is also coming up.
Okay, sir.
Yeah.
Yeah, thank you, sir.
Hello? Yes, sir. Hello. Yes. Yeah. Can you just call me after half an hour? I'm in a webinar. Okay, sir. Can you just leave now? Dinesh?
Thank you, sir. Thank you for giving the wonderful talk, sir.
Yeah, okay. Thank you.
Thank you,
Sir, thank you, sir.
Thank you, madam. Thank you. I'm just rushing because I have another meeting scheduled now. Okay, wish you all the very best. And you just ask the participants if you have any further questions, let them feel free to contact me through my email. Okay, thank you.
Sure, sir. Thank you, sir.
Thank you, sir. And dear participants, if you have any doubts or clarification, you may contact Professor Dr. R. Jaivel sir through email, or you can post the questions in the chat box. And now the time for the lunch and the next session starts at 1 p.m. Thank you. Thank you to all.
Okay, see you later. See you later, sir.
Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay, sir, please.
Okay, Guna. We'll see after lunch. Guna?
Sir, sir, ஓகேங்க சார். லஞ்ச் முடிச்சதுக்கு அப்புறம் பார்க்கலாம் சார். தேங்க் யூ சார்.
நான் என்னோட இது ஸ்லைட்ஸ் வந்து ஷேர் பண்ணிருக்கேன்.
சரிங்க சார், நான்
பாரு
பார்த்துறேன்.
இருக்கேன் பாரு உங்களோட ஸ்லைட்ஸ்
ஷேர் பண்ணிருக்கேன் சார், பாருங்க. அட்மிட் கொடுக்கணும்ல.
Thank you, sir. MNP, sir.
Okay, Guna. Very nice, sir.
Thank you very much, sir. நம்ம ஒரு நாள் இன் பர்சனா பாப்போம் சார், நம்ம மீட் பண்ணுவோம் சார்.
ஓகே, கண்டிப்பா.
ஓகே.
1 o'clock எனக்கு டாக் நான் வந்து முடிச்சேன்.
ஓகே சார். Thank you, sir. Thank you. Dr. Arviselli, அப்ப நம்ம let us close the session now.
Okay.
Yes, sir. Sir, PPT ஷேர் பண்றேன், செக் பண்ணிக்க சொன்னாருங்க சார். செக் பண்ணிக்கங்க.
ஓகே.
அது அப்படியே செக் பண்ணிக்க அப்புறம் நான்
ஓகே.
ஓகே சார். அதான் சார் 1 to 1:30 இது முடிச்சிட்டு லஞ்ச் கொடுத்துறலாம். லஞ்ச் முடிச்சிடலாம் சார்.
சரிமா. இருக்கேன் பாரு வந்திருக்கேன் பாரு. ஓகே.
சரி, ஒரே நிமிஷம் சார். ப்ளீஸ் வெயிட் சார். சரி, இது அவர் ஷேர் பண்றாரு.
ஷேர் பண்ணணுமா?
அவர் ஷேர் பண்றாரு. எங்க ஷேர் பண்றாரு? நம்ம லேப்டாப் வந்தா
தெரியும், ஸ்கிரீன் தெரியும்.
சார் நீங்க இல்லைன்னா மெயில் பண்ணிருங்க சார், நான் ஷேர் பண்ணிக்கிறேன் சார்.
அப்படியா மெயில்
ஆமாங்க சார், இங்க டிஸ்ப்ளே ஆகல சார். அங்க
ஆகலையா உனக்கு?
அங்க கேக்குது சார். அது நீங்க கொடுத்துருங்க சார், இங்க ஷேர் பண்ணிக்கலாம் சார்.
சரி நான் பார்க்குறேன் எப்படி சொல்லி.
நெக்ஸ்ட்னு சொன்னீங்கன்னா ஷேர் பண்ணலாம் சார். ஓகே ஆயிடுச்சா?
நான் பார்க்குறேன். ட்ரை டு சென்ட் இட் டு யூ.
சார் இப்போ ஷேர்
சார் இப்போ ஷேர் பண்ணுங்க சார். செக் பண்ணிக்கலாம் சார்.
இப்போ ஷேர் எங்க வருமா? இந்த இடத்துல
கீழ இருக்கும் சார்.
போஸ்ட் அட்டெண்டன்ஸ் ஜூம்
green color பாருங்க சார். green color ஷேர் ஸ்கிரீன்
இதானே? ஷேர் ஸ்கிரீன் தானே இதாமா?
ஆமாங்க சார், ஷேர் ஸ்கிரீன் இருக்குங்க சார். சார் நோ ப்ராப்ளம் சார், நீங்க கொடுத்துருங்க சார், நம்ம கூட பண்ணிக்கலாம். நம்ம நிறைய பேர்
நான் பார்க்கறேன்.
சரி சரி.
இப்ப பாருமா வந்திருக்கான்னு பாரு.
இல்லைங்க சார், இன்னும் வரலைங்க சார்.
நான் பார்க்கறேன். இப்ப ரெஃபர் பாருங்க. இப்ப வந்துட்டான்னு பாருங்க.
சார் இல்ல இருங்க.
இருக்கா
சார்?
ஷேர் ஸ்கிரீன் அது green தானே?
ஆமா சார், greenல ஷேர் ஸ்கிரீன் ஒரு ஆப்ஷன் இருக்கும் சார்.
போஸ்ட் ஷேர் ஸ்கிரீனா?
அத கிளிக் பண்ணீங்கன்னா உங்களுக்கு அந்த நீங்க ஆல்ரெடி ஸ்லைடு ஓபன் பண்ணி வச்சிருந்தீங்கன்னா அது டிஸ்ப்ளே பண்ணும் சார்.
ஆமா, அது ஓபன் பண்ணி தான் வச்சிருக்கேன் நானு.
ஷேர் ஸ்கிரீன் கொடுத்தீங்கன்னா உங்களுக்கு அந்த ஓபன் பண்ண ஸ்லைடு காட்டும் சார். அதை கிளிக் பண்ணிட்டு ஷேர்னு கொடுத்தீங்கன்னா ஷேர் ஆயிடும்.
இப்போ வந்து இப்போ இது வந்து வித்யா மந்திர்னு போட்டிருக்கேன் டவுன்லோட்ஸ்ல. இப்போ வந்து
சார் உங்களோடது ஓபன் பண்ணி
வந்து இப்போ வந்து எந்த இடத்துல இந்த ஷேர் ஸ்கிரீன்ங்கிறது எங்க வருதுனே?
கீழ green கலர்ல இருக்குங்க சார். பார்ட்டிசிபென்ட்ஸ் ஷேர் ஸ்கிரீன் கீழ இருக்குங்க சார். கீழ இருக்குங்க சார்.
கீழ தான் பார்க்கறேன் நானு. கீழ வந்து இது வீடியோன்னு இருக்கு, அப்புறம் குரோம் இருக்கு, இன்னொரு ரவுண்டா இருக்காதா? தெரியல
சார். அது ரெக்கார்டிங் சார். ரவுண்டா இருக்குது ரெக்கார்டிங் சார். அது பக்கத்துல
சார் green கலர்
ஏரோ மார்க் இருக்குல்ல சார்.
இது எக்ஸல்னு ஒன்னு வருதுமா? அது இல்லையா
சார்? சொல்லுங்க சார்.
சாட் பக்கத்துல சார்.
சாட் பக்கத்துல சார்.
இது பாருமா, இது வருதான் பாருமா. அந்த வித்யா மந்திர்னு சொல்லிட்டு வித்யா மந்திர் இது இதான் வந்திருக்கு எனக்கு.
ஃபோக்கஸ் பண்ணிட்டு லேப்டாப்
சார் உங்களோடது லேப்டாப் தானே சார்? இப்போ நீங்க
ஆமா லேப்டாப் தான்மா. டாக் டு போர்ட்டல்னு வருது. இன்னொன்னு வந்து டாஸ்க் வியூன்னு வருது.
சார் ஃபர்ஸ்ட் வந்து மியூட் அன்மியூட் இருக்கும் சார். அடுத்து ஸ்டார்ட் வீடியோ சார். அதுக்கு அடுத்து தேர்ட் வந்து பார்ட்டிசிபென்ட் இருக்கும் சார்.
ஷோ ஆஃப் இன்டர்நெட்
ஃபோர்த் ஆப்ஷன் சாட்னு வரும் சார். அடுத்து சாட்டுக்கு அடுத்தது ஷேர் ஸ்கிரீன் இருக்கும் சார் ஒரு ஆப்ஷன்.
ஸ்லைட் சார்ட்டர் இது வந்து வால்யூம். இந்த ரைட் சைடுல லெஃப்ட் சைடுல
சென்டர்ல வரும் சார். ரைட் சைடுல வரும் சார். சென்டர்ல வரும் சார்.
சென்டர்ல இது குரோம் ஜூம் கூகுள்னு வருது. அது இல்லையா
சார்?
போஸ்ட் அட்டெண்டி ஜூம் கூகுள் குரோம்னு வருது. அது கிடையாது.
அது இல்லைங்க சார்.
அது இல்லைங்க சார்.
அப்புறம் இன்னொன்று வந்து வித்யா வந்து 2020 அது நான் வச்சிருக்க ஸ்லைடு அது நேம் போட்டு வச்சிருக்கேன். இன்னொன்று வந்து எக்ஸல்னு வருதுங்கண்ணா.
வேற ஏதோ கிளிக் பண்ணிட்ட மாதிரி தெரியுதுங்க சார்.
வெல்கம் டு எக்ஸல்
சார். சார் நோ ப்ராப்ளம், நீங்க மெயில் பண்ணுங்க சார், நம்ம ஷேர் பண்ணிக்கலாம் சார்.
அப்படியே நான் மெயில் பண்ணட்டுமா?
நீங்க மெயில் பண்ணுங்க சார். நாங்க இங்க இருக்கோம் சார். நம்ம ஃபேக்கல்டிஸ் இருக்காங்க சார்.
சரி சரி.
நீங்க நெக்ஸ்ட்னு சொன்னீங்கன்னா நாங்க அப்படியே பண்ணிக்கிறோம் சார்.
சரி இருங்க ஒரு ஃபார்முலா ஓகே பிளாக் போர்ட். சரி நான் மெயில் பண்றேன் பார்க்கறேன்.
சரிங்க சார், மெயில் பண்ணுங்க சார்.
ஓபன்
ஹோல்ட் பண்ணி வைக்கலாமா இல்ல எண்ட் கொடுத்துட்டு அப்புறமா ஜாயின் பண்ணிக்கலாம்?
எண்ட் கொடுத்து ஜாயின் பண்ணிக்கலாம். ஒண்ணும் ப்ராப்ளம் இல்லையா?
அது ஒண்ணும் பிரச்சனை இல்ல. அப்படியே ஜாயின் பண்ணிக்கலாம். அப்படி பண்ணலாம்.
இல்ல இருக்குறதால
இல்ல இப்ப மெயில் பண்ணனும் ஷேர்னா வந்துரும்.
எப்படினாலும் சரி உங்களோட டிசிஷன்.
நீ யாரும் லீவ் ஆகல வந்து மெயில்ல இருக்காங்க.
செல்வி வந்துருச்சான்னு பாரு இப்போ.
சார் நான் செக் பண்றேன் சார். மெயில் செக் பண்றேன் சார்.
மெயில் வரல. இப்போ நான்
ஷேர் ஆகல சார்.
ஷேர் ஆகல சார். ஷேர் ஆகல சார்.
அது என்னமா இல்லையா செட் வெப் வாட்ஸ்அப் போகணும்.
கொஞ்சம் அதான் மெயில் வாங்கிடுங்க மேடம்.
சரி நான் பண்றேன்.
சரிங்க சார், நீங்க மெயில் பண்ணுங்க சார், ஒன்றும் ப்ராப்ளம் இல்லை சார்.
ஓகேமா. தம்பி இந்த பக்கம் நீங்க
சார் அங்க என்ன ப்ராப்ளம்?
வரமாட்டேங்குது. ஸ்லைட் ஷோ இல்லையே. வேலையே வேண்டாம். நாளைக்கு உங்க மீட்டிங்ல முடிச்சுட்டு நாளைக்கு வந்து அப்புறம் பார்க்கலாம். 10 நிமிஷம். ஓகே. ஆமா சொல்லுமா. நான் அதை பார்த்துருக்கேன். மெயில் பண்றது அதே LIMG தானே? அது LIMG எஃபெக்ட் அதான் சொல்றீங்க. அறிவு@gmail.com. ஓகே நான் பார்த்தேன். சரி பார்த்து இதில் அனுப்பிவிட்டேன். ஓகே மேம். குணா சொல்லுங்க. சொல்லுங்கண்ணா. நான் அதை பண்றேன். அதுக்கு அனுப்புற பார்த்துருக்கேன். ஓகே 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 குணா. ஓகே. இதோ வந்துட்டு சாமி. ஐயோ பூவா பூ வந்துட்டு சாமி, வந்துட்டு வந்துட்டு. என்ன சாமி? Hey. வந்துச்சாமா? ஓகேம்மா, ஓகேம்மா, ஓகே, தேங்க்யூ, தேங்க்யூ, ஓகே. நான் பண்ணி போய்க்கிறேன். ஓகே, ஓகேம்மா, ஓகேம்மா, ஓகே, தேங்க்யூ. Oh, ini Sami. No. அதெல்லாம் அங்கே அதை நீங்க எடுக்காத இது எங்க எடுத்த ஐயோ நீங்க கொடுக்குறீங்க இது எடுக்கப்படாது சந்தேகம்.
Happy Friends have been installed.
அது எதுக்கு எடுக்கிறேன் வேண்டாம் சார்ஜ் ஆயிட்டு சார்ஜ் ஆயிடுவான் சார்ஜ் ஆயிட்டு வேற வாய்ப்பு அம்மா கொடுக்கமா அதுமா வந்த பிறகு ஏறி கழுத்துனாங்க வாட டைம் வாட வேண்டாம் ஃபேமிலி சத்தங்க கேட்டாங்க நான் எப்படி ஒரு ஹாஃப் அன் ஹவர் லெக்சர் முடிச்சு வந்தேன் 1:30 மணிக்கு முடிச்சு போயிடாங்க அங்க போகணும் செல்போன் கொடுக்குறமா செல்போன் வரமாட்டியா என்ன வரமாட்டியா வரமாட்டியா வரமாட்டே நான் பை போறேன் போட்டு பை போறேன் சரி தப்பனே நான் வரப்பா நான் வரல நான் போறேன் புரியுது அத்தம்மா கார் வந்துட்டு முடியும் அத்தம்மா கார் வந்துட்டு வா நான் போன கொடுத்தேன் அத்தம்மா காரு அத்தம்மா கார் வந்து துணி கார் போல இருக்கக்கூடாது ஏமா செல்வி ஆரம்பிக்கலாமா? சரி, இப்போ நான் என்னோட ஸ்க்ரீன்ல ஷேர் பண்ண வேண்டிய இதை கொண்டு ஸ்லைட் ஷோ கொண்டு வருவேன். ஹலோ, சரி கொண்டு ஓகே ஃபைன் ஓகே.
In our first day of our conference,
அம்மா சொல்லு. ஓகேம்மா. சரி, என்னோட டிஸ்பிளே ஆகுது, ஒன்றும் இட்ஸ் நாட் ப்ராப்ளம். ஓகே. இப்போ வந்து இது வந்திருக்கேன், நீங்கள் இப்போ டைட்டில் போட்டிருக்கீங்க இல்லையா, இது மட்டும் வந்திருக்கு. அடுத்து நெக்ஸ்ட் சார். ஓகேம்மா வருது. ஓகேம்மா ஃபைன். டேய் கண்ணா நான் ஒரு மீட்டிங்ல லெக்சர் எடுத்துருக்கேன், முடிச்சுட்டு உனக்கு கூப்பிடுறேன். ஓகே
Good afternoon, everyone. In our first day of our conference, inaugural function was completed with our first session, and now we are going to start our second session. The price of our success is hard work, dedication to the job at hand, and the determination that whether we win or lose, we have applied the best of ourselves to the task at hand. Here we have the most valuable, respected Professor Dr. M.N. Ponnusamy sir. Now I humbly request our eminent Professor Dr. M.N. Ponnusamy sir, Professor, Center for Advanced Studies in Biophysics and Crystallography, University of Madras, Chennai, to take over the session. Thank you.
Okay, ma. Okay, thank you very much, ma, for the nice introduction. And then, can I talk right now?
So you may continue, sir.
ஆரம்பிக்கலாமா? ஹலோ. Okay. Can we start? Can I? Where's okay, fine. First slide, go back. Okay, fine. Okay, I'll start right here. Okay, welcome to the second session of this conference on physics of materials and molecules. Can you hear, gentlemen? Can you hear my voice? Hello?
Sir, it is audible, sir. It is
it's audible for me. Can you hear my voice?
Yes, sir.
Yes, sir.
Okay, fine. Can you proceed?
Sir, please wait, sir.
Okay.
An announcement, sir, for oral presentation participants, sir. Dear participants, the oral presentation time is 1:30. 1:30. The SAR session completed at 1:30. So please be waited.
The oral presentation will be starts at 1:30 p.m. As per the list, the participants are asked to get ready as per the list which was we have given, registered. Thank you, sir. You may start, sir.
Can I start, Tijan?
Yes, sir.
Definitely, sir.
Okay. So welcome to this second session of this international virtual conference on materials and molecules, physics of materials and molecules. And this is a beautiful kind of topic as we have discussed in the inaugural session. And Dr. Jaivel has given the nice applications of the lithium battery and the future kind of this thing. And I'm sure the battery is going to be the future kind of energy to supply and the supply for the energy of motors. And now I am going to talk a simple kind of introduction about biophysics and crystallography. I don't want to go deep into the subject since because it's a kind of basic kind of introduction. So you just try to follow, and I feel that the world of crystallography and biophysics are to be the future field for designing drugs for each and every disease. Even now, so many kind of drugs that we are using are all emerged from the applications of biophysics and crystallography. So whenever I start my talk, I used to do this திருக்குறள். எப்பொருள் யார் யார் வாய் கேட்பினும் அப்பொருள் மெய்ப்பொருள் காண்பதறிவு. I'll let people are well aware of the fact that whatever may be the source of any information, knowledge is to extract and assimilate the truth in it. So I hope this Tirukkural will soundly balance with the research that we people are performing right here, and ensure that you all people will enjoy kind of these things. Next slide. Can I go? I'll go. Hello. Can I go for the next slide? Next slide, please. Okay. So the topic is biophysics and crystallography, tools for drug design, and from the Department of Crystallography and Biophysics, University of Madras. I hope you people are well aware of the fact that Professor G. N. Ramachandran was the founder of this biophysics. He is the direct student of Professor Sir C. V. Raman. And in fact, J.N. Ramachandran is the, way back, a small story is that way back in 1952, our former Vice Chancellor, the then Vice Chancellor of the University of Madras, invited Sir C. V. Raman to establish a physics department in Madras University, but he sent Professor G. N. Ramachandran on his place, and he assured that he is capable of doing research more than me, or something like that, the words uttered by our Nobel laureate Sir C. V. Raman. And Ramachandran came back to Chennai in 1952 and established the physics department. And it was then afterwards it was separated from physics as crystallography and biophysics. And he has done wonderful kind of research, and the research was worldwide famous. His innovations are exemplary, and unfortunately he missed the Nobel Prize. But anyhow, he was the backbone for so many kind of new research activities in University of Madras. Next slide. All that you can actually be able to see right here. I'm just going to give a simple kind of introduction about biophysics. And right here, you can actually be able to see for a kind of equation right here, central dogma for molecular biology. That's what you can actually be able to see. But there are so many fields, all that we can say: biotechnology, molecular biology, bioinformatics, biophysics, even right now protein genomics, so many kind of fields. The basic equation is simply nothing but DNA, RNA, protein, and function. And all that you are well aware of the fact the property of DNA is simply nothing but to replicate, and it's a double stranded structure. All that you can also be able to see. I will show in the next slide. And DNA can be transcribed. It's a gene molecule. It can be transcribed into the form of an RNA molecule. DNA molecule is a double-stranded helical form molecule, and when it is transcribed into the form of an RNA molecule, it is a single-stranded molecule. And then this RNA molecule, ribonucleic acid, is translated into the form of a protein. And the protein is simply nothing but people are well aware of the fact that it's the 20 amino acids will combine together to form a specific kind of protein with a starting point and ending point. The amino group as a starting point and a carboxyl group as a ending point. So it is a content of a specific kind of molecules. Number of amino acids will be present. Maybe it varies from even 20 to even up to 1,000. It depends on whether it's a single molecule or dimer or trimer or something of that kind. And that protein that plays a major role in the functional activity of our biological system. So that's the thing that we can actually determine. If you specifically find a protein, then the modification is possible. But synthesis of protein is not that much easy job. It's a kind of a combination of so many kind of factors. So the functional activity depends on the protein molecule. Maybe 3 or 4 or 5 the amino acids responsible for the specific activity. So below that, I have shown that the protein factory right here, that double-stranded helical form, single-stranded RNA, and then it is converted into the form of a protein as a single chain. Next slide. Can you please go for next slide? This is for the DNA molecule. All that you can actually able to see that there are 4 bases, but specifically we call that as 4 molecules. But because that 4 molecules are used in deoxyribonucleic acid, it's called as 4 bases. So called as bases, and you can see ATGC. Adenine will always bind with thymine. Guanine will always bind with cytosine. So you can actually able to see that adenine, thymine, and guanine and cytosine right here. It is in the helical, double-stranded helical form in a shaded way. But if you can go for the exclusively the molecular form, you can see that sugar, a small phosphate group, and the adenine molecule right here. and that is bound with the adenine is bound with the thymine molecule with the use of hydrogen bonding. People are well aware of the fact that hydrogen bonding is a non-bonded kind of interaction, which plays a major role in building the molecule right in there. And next slide is an RNA molecule. It's a single stranded kind of molecule, and that it will fold on its own. It is usually we call it as a single stranded molecule, but it bends on its own to form some kind of what do you call the base pairs. In DNA molecule, ATGC is the base pair. Adenine will always pair with thymine, and guanine will always pair with cytosine. But right here, there is a small change. Adenine will always adenine pair with uracil, and guanine will pair with the cytosine. So you can actually able to see the difference between these. There are 5 bases in total: adenine, guanine, thymine, cytosine, and uracil. And these 5 bases played a major role in the history of biophysics. Can we go for the next slide? And here I have shown that ribosome is the big kind of molecule. The three-dimensional structure was followed by our great Nobel laureate N.K. Ramakrishnan, and he proved that it's one of the beautiful kind of molecules right here. Can we go for the next slide? The trend design happened right in there. If you come down to the simple step of a protein, all you people are well aware of the fact that proteins are the macromolecules, and there are 20 different L amino acids which will build up the protein molecule. And definitely a certain number of what do you call the amino acids, or we call it as residues, are responsible for the biochemical action. And normally the protein size varies from maybe some 30 to 40 residues, or residues in sense called as amino acids, to several hundred residues for the functional activity. And you can also able to see that large aggregates can be formed from protein subunits. Many thousands of actin molecules assembled into an actin filament. So if you go down, can you go for the next slide? You can also able to see this is the simplest form of an amino acid. It consists of 3 different groups. Although you can also able to see nitrogen is bonded with 2 hydrogens. It's called an amino group. And another one is called as carboxyl group. The last one, COOH. And the amino group is attached with the carboxyl group through a carbon bond. So this is the simplest form of the amino acid. All that you can also able to see right here. I have put R. R means a kind of residue, or we can call it as a small organic molecule, organic this thing. And if you substitute what do you call it, for the 20 different amino acids, if you can substitute a small organic group in the place of R, so that you can actually devise all the 20 different amino acids. If you substitute mere hydrogen in the place of R, it is called as glycine.
Sir, your voice was not audible, sir. Sir, is it is audible, sir?
No, it's audible. It's audible for me. Can you hear my voice?
Yes, sir. Yes, sir. Now it is audible, sir. You proceed, sir.
Okay. So can you go for the next slide?
Okay, sir. Okay, okay, okay.
Yeah. Now we have seen the amino acids. Now all that we are going to form a small this thing, that is what we call it peptide right here. So if we can actually able to combine two amino acids together, it will form a peptide. So we can actually keep on combining as many amino acids as possible. Maybe the same amino acids or different kind of amino acids right here. So just think about amino acid 1 will be combined with amino acid 2, and then I put that R as an organic, small organic group, but here R1, R2 as organic groups, maybe glycine plus alanine or something of that kind. So now only thing is I have put that the amino group, the protonated amino group right here, there is one hydrogen was added extra, and I removed one hydrogen on the carboxyl group. That is, it's always expecting something right here. So if we can also combine together this two amino acids, in amino acid 1, the carboxyl group will attach with the amino group of the amino acid 2. That is, two hydrogens from amino acid 2 will combine with one oxygen atom right here. It will form a water molecule right here, and then it makes a bonding right in there from carbon to nitrogen, so that it makes a bonding right here. So you can actually able to see right in the below, there is a bonding between carbon to nitrogen. The main thing is you can actually able to see that there are, carbon always stands for 4 valency, but unfortunately, if you can actually able to make an attachment, then it's having a kind of a double bond situation. But when they measured the distance by using crystallographic methods, the carbon to nitrogen here, I put an arrow mark right there. So it is not a single bond, it's not a double bond, it's a partial double bond in character. So then Professor Linus Pauling could not able to understand what is going on right here. Either it has to obey the valency of 4, or what will be the next kind of step. So then finally, after doing a lot of crystallographic work, after determining the 3-dimensional structure of the peptides, dipeptide, tripeptide, tetrapeptide, like that, then finally they have concluded that that carbon to nitrogen distance is not a single bond, it's not a double bond, it's a partial double bond in character. So that actually created a revolution way back in the late of 1940s and 50s. And it was the birth of, I can actually be able to say that the biophysics right in there. So that particular bond is specifically called as a peptide bond right in here. So then, all that I can say that Professor Linus Pauling determined the partial double bond character and measured the distance, and the measured distance was between a single bond and double bond. Then he left it right in there. And the remaining portion was taken over by our great scientist, Professor G. Ramachandran. Can you go for the next slide? Next slide, please. Yeah, now you can actually able to see that in a sequence of chains, protein chain or a polypeptide chain, all that you can actually able to see that carbon to nitrogen distance is only 1.32. It is a partial double bond in character, and that reflected the carboxyl group. So all that you can actually able to see that the shortened peptide bond, the bond is called as a peptide bond, and this is a shortened one. And I have colored that yellow portion, that carbon attached with the oxygen and the nitrogen attached with hydrogen. These all 4 atoms lie in a particular plane. So that particular 4 atoms lie in a plane is called as a peptide plane, or that particular portion is called as a peptide unit. So this kind of information was taken by our Professor G. Ramachandran. Can you go for the next slide? And then you can see this is what the main thing. So the carbon to carbon rotation, the single bond, the rotation was called as rotation angle was called as a psi angle, and carbon to nitrogen, the blue color, you can actually able to see that that is a single bond, that the rotation is called as a phi angle. So this is the basic of Professor G. N. Ramachandran's discovery. So he attached two amino acid right in there. So this phi angle and psi angle were varied, and the what do you call the interactions between the atoms were noted down, and they have figured a specific kind of map. So the variation is that the phi angle was kept in 0, and the psi angle was varied from 0 to 360 in steps of 10 degrees. And they have measured the interactions between the atoms right in there and recorded in the map. And the phi angle was increased to 10 degrees, and again this psi angle was varied from 0 to 360. Noted the specific kind of valuable non-bonded interactions and so many kind of these things, and noted in the map. Likewise, the phi angle was varied from 0 to 360, and psi angle was varied from 0 to 360. So overall, they have combined all this information, and they have plotted it out in a specific map called phi psi map. So can you go for the next slide? This is what the phi psi map. You can actually able to see this is what the greatest kind of discovery made by Professor G. N. Ramachandran. So initially this is phi angle and this is psi angle. Initially it was devised as 0 to 360 degrees, but afterwards one particular international conference was held, and varied that the changes was made, and it was accepted universally, that is minus 180 to plus 180. I mean the kind of these things will be the same from 0 to 360, 0 to 360 phi angle and psi angle, but the map was designed in such a way that minus 180 degree to plus the plus and minus side. So now that you can also be able to see this phi axis, and this is psi axis, and initially it was called as phi psi map. And after the conference or something like that, since because it was devised by Professor Ramachandran, the map was called as Ramachandran map, or it's called as Ramachandran plan. So this actually, even now, this created a big revolution in the biophysics world or biological world, I can also be able to say that. So here, if you take into account a particular protein chain or so, consisting of about 100 amino acids or something like that. So by rotation of this phi angle and psi angle, you can actually able to say what will be the number of residues formed in the helical form, and what will be the number of residues in the planar sheet, either parallel beta sheet or anti-parallel beta sheet, and how many residues in the left-handed alpha helix or right-handed alpha helix. So this map, even now, for validation of any specific kind of protein, they can actually to devise. Even now, Ramachandran plot is used as a scale to validate the protein structure. So you can think about the what do you call the importance of this particular kind of plot. So this is one of the biggest kind of discoveries by Ramachandran. In addition to that, he has made what do you call the triple helical structure of collagen. So unfortunately, the simple helical form was devised by Professor Linus Pauling, and he was given Nobel Prize. And the double stranded helical structure of DNA molecule was devised by Watson and Crick. They were given the Nobel Prize. But the triple helical structure of collagen was predicted by Ramachandran, but unfortunately, he was not given the Nobel Prize. So this is the important kind of plant. Can you go for the next slide? And just I want to show right here that is Professor G. N. Ramachandran right here in this plant. And afterwards, the Ramachandran plant was modified with simple kind of what do you call some right-handed alpha helix. In addition to some other kind of information will be there. Some different kind of helical forms are also will be right in there. And you can see that Professor Lakshmi Sangharia, the former Vice Chancellor of Madras University, and in center, Professor G. N. Ramachandran. Right side is one Professor Bertrand is also a good friend of Professor G. N. Ramachandran, and he was the person given the idea to Ramachandran to go for the structure of collagen. So can you go for the next slide? Then all that just a part of this thing that if you think about a protein molecule, I mean on the biophysical side, it can be divided into 4 different kind of categories. Where the one is called the primary protein structure, if you think about a protein molecule, what are all the amino acids present in that particular molecule is called as a primary structure. Here we have given a single letter code. There are proteins normally will be coded with a single letter code or triple letter code, or the full molecule written there, full name of the molecule written there. So here the single letter code is is given right here. And then after the prediction of G.N. Ramachandran, the helical form as well as the beta sheet. So either the helical form and the beta sheet, either parallel or anti-parallel, will be called as the secondary structure. And if you think about a protein molecule, approximately about some 60% will be in the helical form, and about 30 to 35% will be in the parallel or anti-parallel beta sheet, and about 5 to 10% will be in the coiled form. So because that is essential for the bending of protein molecules, that is the main thing. And if you think about a single molecule of protein structure, that's what we call it. A single three-dimensional structure of a protein molecule is called as a tertiary protein molecule. And if you can able to combine some 2 or more number of molecules right in here, then that is called as a quaternary protein structure. So the main thing that you have to keep in mind is that the three-dimensional structure that plays a major role in the functional activity right in there. So that's the message that you have to keep in mind, the three-dimensional structure. So the entire three-dimensional form of the structure that plays a major role in the functional activity of the molecule. So now, how to find out the three-dimensional structure? That was the question way back in 1940s and 50s. It was existed, and crystallography was the tool that they have used to find out the three-dimensional structure. Can you go for the next slide? So I told you that hydrogen bonding that played a major role right in there. That's the reason I just put a model right in there. So the what do you call the hydrogen molecules, how it actually bonds right there and forms a hydrogen bonding. Can you go for the next slide? Now, as I told you, how to find out the three-dimensional structure. So since because it plays an important role in the functional activity, so how to find out the three-dimensional structure was the question. So that's why the biophysics is so closely related to the crystallography kind of terms. Next slide. And science of crystals is simply nothing but what do you call the to find out if you take into account a particular kind of molecule that can be crystallized, and then it has to go for three-dimensional structure determination. For that, we normally use things because the crystallography term was termed because of X-ray source was used to find out the thermal structure, and the electromagnetic spectrum, if you take into account, and the X-ray wavelength actually lies in the range of about 1 angstrom, 0.1 to 100 angstrom range. So that's what we call it as the X-ray region. So, and you people are well aware of the fact that Conrad Röntgen was the person who discovered X-rays, and then X-rays were used for so many kind of purposes. Soft X-rays are used for, I mean, even the bone crack or something like that, that you can be able to do kind of medical treatment. But fortunately, hard X-rays that we have taken into account right here, mostly for determining the crystallographic, the three-dimensional structure of the molecules. So can you go for the next slide? So actually, crystals and crystallography. Crystals, all that you are much familiar, even our Dr. Jaivel has given a nice talk about nanocrystals and so many kind of structures. Crystal also plays a major role in the world of what do you call the crystallographic thing. But crystallography is the subject which deals with the crystal structures. I mean, to determine the crystal structure of, I mean, to find out, elucidate the structure of a particular molecule in the three-dimensional side. So that is the main kind of this thing. But of course, a crystal, you think about a crystal, it is a repeated specific kind of motif, or we can say an object repeated translationally on a three-dimensional lattice. Then you know that it actually extends in all three directions possible in a periodic way. That's the main kind of thing. So now, how to determine the shape of that molecule? Can you go for the next slide? So, can you go for the next slide? Yeah. Initially, if we want to go for determination of what do you call the three-dimensional structure, it is essential that you have to crystallize the sample. But the previous days, mostly they can also be to crystallize almost all kind of samples possible. But unfortunately, about 10% of the molecules will be finding it extremely difficult to crystallize. So then people started using different kind of methods possible. So even very small molecules possible, organic molecules or inorganic molecules or steroids or alkaloids, whatever kind of things, and proteins and DNA, RNA, all those kind of molecules. They have started using different kind of techniques to crystallize the sample, hanging drop method, and what do you call the sitting drop method, vials method, various of different concentration, and so many kind of methods are used to crystallize the sample. Now, the success rate of crystallizing a sample is approximately, not approximately, almost 99%. Maybe 1 in 100 samples is not possible to crystallize. And all that I can say that crystallography, the only flaw, if you think in crystallography, is that unless otherwise you crystallize the sample, it's very difficult to determine the structure. So that's the thing. But the modern technology actually helped us to crystallize almost 99% of the samples, so that you can go for crystallographic structure determination, that is three-dimensional structure determination. Can you go for the next slide? Now, the crystallized sample can be, can actually able to see the crystallized sample right here. Can be mounted in a small tube, and then you can actually able to expose X-rays. X-rays will pass on to crystal, so that X-ray diffraction takes place. So you can actually see that down the diffraction pattern of a particular crystal, and to determine the crystallographic structure, three-dimensional structure, all that you can have some basic steps right here. What are the procedure that you have to follow right in there? Grow a crystal, very simple kind of steps. Grow a crystal, and then the crystal can be mounted on a small fiber and expose it to X-rays. Then you have to collect the data, and then you have to compute the collected data are called as intensities, and square root of intensities is amplitudes. And then the computed phases are necessary to go for such a determination. For each and every data, every dot, that will be tabled in terms of Miller indices, and each and every what do you call the Miller index to have a specific kind of phase. So the phase has to be generated, and then you have to calculate the electron density map. Then you can actually able to see the tentative form of structure formation, and then you have to build a model. Then use your mathematical kind of simulation, what you call as least squares phenomena, to refine the structure. So that finally you can actually able to see how it actually the structure looks like. And then you can actually able to measure the different kind of parameters possible: bond length, bond angle, torsion angle, and even the way that the molecule bends, or whatever the group, whatever may be the kind of situation. So these are the basic steps that we have to follow to determine the structure of a particular molecule, even protein molecule or whatever kind of these things. Can you go for the next slide? Next slide, please. And then before that, all that it's as I told you, that it's essential to form a three-dimensional lattice, and all that you can actually able to see the formation of a three-dimensional lattice. So X, Y, and Z direction, and now all that if you can actually able to X direction, the A will be there, Y direction the B will be there, Z direction the C will be there. So that if you can actually able to attach A to B, B to C, and then you make a shape of that particular this thing, that's called, that's what we call it as unit cell. And the unit cell consists of 6 parameters. That is in the X direction, A is the length, and Y direction B is the length, and Z direction C is the length, and the binded angles A to B, B to C, C to A, the 3 parameters. So in total, all that we can have 6 kind of parameters that will determine the what do you call the unit cell. And now all that there are 7 different kind of crystal systems that is possible. Whatever may be the crystal that you can take the world or even the world sphere, the crystal will belong to one of the systems possible. Can you go for the next slide? So this is what the main thing you can see right here. Can you go for the next slide? Yeah, this is what the unit cell that you can actually able to see. Bravis is the person who determined the unit cell lattices right in there. So the 7 different crystals, that is triclinic, monoclinic, orthorhombic, all those things will be combined together to put there are totally 14 different kind of lattices possible. In total, whatever may be the case, you take into account it's the maximum that the 7 different kind of crystal system will compute only 14 different kind of lattices possible. So you can see that in the orthorhombic case, there are 4 different kind of these things, that is face centered, body centered, and base centered simple orthorhombic. And the other things are all minimum, maybe in a monoclinic a couple of cases. So in total, the great work done by Bravis is the 14 different kind of unit cells. So it's called as Bravis lattice units. Since he had designed these single unit cells, his name was included right in there. So it's called as Bravis unit cell. Can you go for the next slide? And now, how to pack the molecules in a unit cell. So depending on their crystal system, how many molecules are there in a particular unit cell will be packed right in there. But here, the symmetry plays a major role. If you take into account the triclinic system, there may not be any kind of symmetry possible at all. So no symmetry at all. The whole unit cell will be formed with a single molecule. And even if it turns out to be a centrosymmetric kind of structure, then the single will be transformed into the 2 different units. That's the inverted one, P1 and P1 bar. Likewise, you can go for monoclinic, orthorhombic, simple cubic, rhomboidal, whatever may be the case. So you can actually able to see in the unit cell there are 2 different, molecules, right? 2 molecules packed right in there. And likewise, the molecules can be extended in X direction, Y direction, and Z direction, so that the crystal forms like this. So it's possible that you can actually determine one motif or one molecule. Then it's possible, depending on the symmetry, you can actually generate the complete kind of crystal right in here. The whole 3-dimensional structure of the crystal right in there. So this is what the shape that I have shown for a single molecule right here. Can you go for the next slide? And normally in protein crystallography, if you mount the crystal, then diffraction data will be like here, and the data can be interpreted in terms of electron density, so that you can actually able to exactly find out or trace out the complete kind of molecule right in there. Can you go for this is the way that we have to build up the model and come down. And before that, what we call, this is the diffraction pattern that you can actually able to see on the left side. And a very simple kind of mathematical form is used to derive the electron density right in there. That's what we call the Fourier transform. So on the left hand side, there is a simple kind of equation that is the sigma runs from a number of atoms right in there. And it will be converted into the form of what do you call this amplitude will be converted in the form of electron density on the right side. So it's 1 by V. Then you can actually able to see FHKL and then exponential factor right here. On the left hand side, that you can actually able to see F in the bracket we have put J. That F is simply atomic scattering factor for the various atoms, carbon, nitrogen, oxygen, or chlorine, or even if you can go for higher level of things also. So that we can also able to decide the electron density right in there. The more the number of electrons, the more the electron density will be there. So likewise, we can also able to use the simple mathematical logic, and this diffraction pattern will be converted into the form of an electron density map, so that for each and every index we can compute a phase, so that they'll combine together to form the 3-dimensional structure. So this is the way that we use it to determine the 3-dimensional structure. Way back in 1940s and 50s, the automatic diffractometers are not available. So we have to expose the crystal into the camera. The camera was loaded with the film, and it's about 100 hours of exposure or something like that. We have to take out the intensity is possible. But nowadays, since because the automated diffractometers are available for each and every index, the intensity measure, so that you can go automatically and then find out the phase or compute the phase, so that the electron density map can be mapped out and the molecule can be determined. Can you go for the next slide? So this is what normally the shape of the molecule that you can actually able to see. And for phase computing, in those days, people used to use this what is called the Patterson method, heavy atom method, or whatever the kind of these things. Now the direct methods are the most famous one. By using this combination of intensity or amplitude with the phases, you can actually able to see the three-dimensional structure determination of the molecules. And in the proteins, and of course, the molecular replacement method, or multiple isomorphism replacement method, or multi-valent anomalous replacement. These are all the specific kind of methods adopted to solve the protein molecules. This is because protein molecules are fairly big molecules, molecular weight of about 20K or 30K or something like that. So we have to adopt the different kind of methods to solve the phase problem and have to trace out the molecule by using electron density map. So, and then finally you have to refine it by using least squares refinement procedure. And you can also be able to see that, I mean, the first phase that we have seen, that the three-dimensional structure actually plays the major role in the functional activity, but in the second phase that you can see that how to determine the three-dimensional structure by using crystallographic methods. Now we have decided to determine the what do you call the three-dimensional structure. So now, can you go for the next slide? I just want to finish it in another 5 minutes. Can you go for the next slide? No. So now, what are the use of these two things, the biophysics and crystallography, and specifically we can go for the application of designing a drug molecule by using these methods. So next slide, please. Here in all that we can see that this is what a drug design pipeline. And I mean, in those days, since because crystallography was not existing right in there, simply synthesis of chemical compounds, and then you have to go for scrutinizing the molecule, this and that. It takes for years together. Maybe it took about 8 to 14 years to design a single drug molecule. And they used to analyze about 10,000 compounds. And they have taken and they spent about $800 million to come out with a single successful drug molecules. Since because crystallography came into picture, and crystallizing the specific kind of molecule and determination of the three-dimensional structure, it actually reduced the what you call the number of days, the number of compounds, number of amount, the amount of money. Everything has gone down for 100 times less. So maybe even $100 million or even less than that, $100 million will be sufficient, and about 1 year is sufficient to design a particular molecule. And it's not necessary to go for 10,000 compounds. It is sufficient if you can go for about 100, 150 compounds once you know the specific activity right in there. In the protein, as we have seen that three-dimensional structure determines the functional activity. The protein structure, three-dimensional structure consists of the activity zone right there. If you know the shape of that activity zone, so that we can actually able to bind the small drug molecule right in there, so that it actually binds in a way what we call it as non-bonded interactions, and the kinetics mechanism will be satisfied, so that it acts accordingly and the drug will be designed. So this is simple words that I'm just saying, but if you can do it, it will take its own kind of time. So people are now using these kind of techniques and designing the molecules. Can you go for the next slide? Next slide, please. Yeah, this is what what we call it as structure-based drug design by using crystallographic methods. Initially, you have to find out a specific kind of ligand or a organic molecule, and then the properties of what you call this molecular value properties of the compound will be known by using protein chemistry methods, and then you have to determine the three-dimensional structure of that molecule, And if already determined the protein molecule's active site, then you have to dock it inside. And then if it actually fits right in there, if not right in there, it will be okay. You can as well able to analyze, and you can as well able to see the kind of capacity. If not, then again you have to choose another ligand. So if you know the active site size, so we can design a molecule in such a way to dock it with that molecule inside. So that's what we have done right here. So it's not necessary for you to go for thousands of molecules. Maybe 100 molecules will be sufficient to design and dock it with the active site of the protein molecule. Can you go for then we can go for the clinical side, preclinical side, and if we are quite okay, then things will be all right. That's the reason it is called as structure-based drug design. That's a thing that people are now using. For this purpose, can you go for the next slide? We are using two different kind of. So you can see that the small molecule ligand data. I mean, they have created the database right here. Even now, people are well aware of the fact Cambridge crystallographic database is there. Stored all the three-dimensional small molecules structure, it's about 15 lakh structures are stored right there. And then targeted protein structures, even the protein data bank is there. And it's about 2-3 lakhs protein structures are stored right in there. If you're interested, we can do theoretically also by computing the specific, taking out that specific target protein molecule with the small molecule, so that we can do the molecular docking, and finally we'll come out successfully with a particular drug molecule. So this is what the way that we use it to go for the rational drug design idea. So people are doing virtually people are now doing all kind of work right in there. So crystallography actually is the backbone that they have solved about 15 lakh small molecular structures and stored in the Cambridge crystallography database. Can you go for the next slide? And designing the molecule, drug molecule, they have used two different kind of methods. One is called as lock and key method. The other one is called as what we call as induced fit method. The lock and key method is the lock is there, the key is there, so that you can actually able to put the key inside the lock to open the lock. But induced fit method is a little bit complicated. The lock is there, the key is there. The key will not open the lock. So what we have to do is we have to shape the what you call the key little bit to open the lock. So that's what we have to design the molecule in such a way to open the protein molecule. So, but mostly now people are doing this induced fit method, so that maybe sometimes people are using both the lock and key and induced fit combined together to form to find out a suitable kind of molecule. But the induced fit method is the famous method. And now people are doing it right here. You can see the yellow form and the small molecule comes and binds right in there, so that it can do the kind of functional activity. Can you go for the next slide? So now, yeah, this is what one specific kind of docking right here I have shown. So I'm just showing that the ligand actually, the receptor, the ligand, how it binds actually the receptor. That was shown right here in the form of the protein molecule, how the small molecule goes and binds. The red color shows the negative zone, so that it binds right in there. Next molecule, next slide. So finally, this is the way that we used to design the molecule, and I'm just showing right here one what do you call the HIV particle right in there. It actually looks very beautiful, and people are making attempts to find out a suitable active site and active site, so that they can actually able to dock it and cure the AIDS affected people. So, and you can actually able to see on the right side that people are making attempts and have docked a few molecules inside that active site of the HIV particle. But unfortunately, it actually works about 60 to 70%, but not purely 100%. And it works for about a few months or maybe a year or so. But still, we need what do you call the enormous amount of step to devise another effective molecule to solve this HIV affected people's problem. So hopefully, in the near future, what do you call the number of the structures already stored in the what do you call the Cambridge crystallographic database and the protein database will help to solve the problem in future. Bioinformatics is the subject. People are working on it to solve these problems. Can you go for the next slide? Yeah, this is what the way that inhibitor docked inside the HIV protease right in there. And hopefully, I mean, this is more effective, but still we need another effective kind of molecule so that we can actually able to solve the problem. This is one of the major problems that has to be solved. And another one is next slide. I'm just going to complete it in another minute. The main thing is that people are now aiming to solve from gene to drug. Is it possible that we can actually able to solve the problem in the gene level itself, the DNA structure itself? The DNA molecule is a gene molecule. Is it possible that we can actually able to vary the base pair so that it's possible to solve the what do you call the continuous kind of disease? Some people, I mean, the sugar kind of diabetic people, you know, if the grandfather is affected with diabetic and the father also will be affected with diabetic, and the son will also be, grandson will also be affected with diabetic. So people are nowadays thinking, is it possible that we have to go for solving the problem in the gene level itself? But unfortunately, the thing is not successful, even though a slight, I mean, a simple kind of variation, about 5% or 10% variations are there from one species to other species, but still we find it extremely difficult to solve this problem. And hopefully, I think in future, people will try to find out suitable base pair so that they can also be able to solve the basic kind of problems that தமிழ்ல சொன்னாக்கா அந்த வடி வடியாக வந்த அந்த டிசீஸ் வந்து சால்வ் பண்ண முடியுமான்னு சொல்லிட்டு எதிர்பார்த்திருக்காங்க. And I'm sure that we are going to be successful on that kind of attempts. And maybe in future that the crystallography and biophysics will do still more kind of what do you call the information to solve these kind of problems, so that the human life will be much better than now we think of. So definitely, I think these kind of things will be useful. So although I can also be able to say that it's a very simple kind of understanding for you, that's the biophysics and crystallography will be useful to solve the human kind of problems possible in the form of drug or whatever kind of these things. And many kind of many diseases, maybe the paracetamol, insulin, so many kind of drug molecules came out successfully from the vitamin B12. All they came from successfully from the crystallography and biophysics. So these are all the things that I want to convey for all you people, and I'm sure future these two parameters will play a major role. So I'm thankful for the opportunity given to me. I'm sure that the webinar will be going to be a very grand success, and the number of great personalities going to be deliver the talk. And I'm sure our President Dr. Gunasagaran and the convener Harish Sendi, and then additional organ secretary Suresh, all people will enjoy the real kind of benefit and fruits, these kind of these things. I'm thankful for all of you. Thank you so much.
Thank you, sir. Thank you for your wonderful talk, sir, on tools for drug designs. Dear participants, if you have a doubt or clarification, you may ask the questions.
Very nice, sir. Just expect. Any questions from the audience?
If there is question, you may ask, or otherwise we can wind up the session.
Yeah. So, I mean, if there are no questions, I request all them to, if there are specific questions, they can let them send it to my email ID. I will try to answer, or they put it in the chat box or whatever the kind of these things.
If there is a question, please contact SAR's mail ID.
Yeah.
And
Thank you, sir.
Yeah. So thank you very much for your support, and so I'm so happy. I enjoyed a lot writing here. Thank you so much.
Thank you, sir. I will call later, sir.
Okay, fine. Thank you. Thank you very much. Okay, bye. Bye.
Bye, sir.
Thank you, sir. Nothing changes if nothing changes. Well, if nothing changes, we say the same. Don't grow, we don't evolve, we don't get better. And that's not going to work, not for you and not for the world. We need positive change, we need new ideas, and we need progress. To get progress, The only way to discover the limits of the possible is to go beyond them into the impossible. Now, we have the most valuable professor, Dr. P.M. Anbarasan, Professor, Department of Physics, Periyar University, Salem, who is going to discuss the possibility of interaction of extreme laser radiation with radioactive hazardous material. Now, I request our Assistant Professor, Dr. S. Gaurisen, to give short intro about him.
Good afternoon to all. I am very much happy to talk about Dr. Ponusami Munusami Anbarasan. He is the Professor of Physics, Department of Physics in Periyar University, Salem. He was born in 29th May 1964. He was completed in MSc, MPhil, PhD and MA Public Administrative. Apart from that, he is Fellow and Life Member in Optical Society of India and Solar Energy Society of India. He has 33-year teaching experience and research. Dr. Ponusami Munusami Anbarasan is interested in laser and spectroscopy, then nano-optics, solar cell and material science. He got a fellowship award from Indo-Hungarian Educational Exchange Program. He was published 203 articles. It consists of 186 international journals and 17 Indian journals. He was published 3 books and 6 study materials. Then 24 PhD scholars got awarded under the guidance of Dr. Anbarasan sir. He was doing more than 36 collaborative research with scientists of various institutions and agencies. He was handled 9 projects funded by various organizations. He got the award listed by GATE 86 passed, then UPS All India selected in 2nd position, lectureship in Government of Pondicherry. In 1988, he got the award of Best Motivator cum Teachers. Dr. Ponusami Munusami Anbarasan will going to discuss about the interactions of extreme laser radiations with radioactivity hazards materials. Thank you.
Good afternoon.
Sir?
Good afternoon to everybody.
Sir?
Sir?
Sir,
Yes?
please wait, sir. Sir.
Shall we start?
Yes, sir, your screen. Sir, your PPT, sir.
Okay.
Shall we check, sir? Shall we check, sir? Your PPT.
Here?
Sir,
Can I
PPT.
start?
Sir, PPT check பண்ணிக்கலாமாங்க சார்? Sorry.
பண்ணிக்கலாமே.
அதுதான் சார்.
எப்படி வரணும் சொல்லுங்க.
ஷேர் சார் ஷேர் பண்ணுங்க சார்.
ஷேர் பண்ணிட்டுமா?
ஆமாங்க சார்.
சார் ஃபர்ஸ்ட் பிபிடி ஓபன் பண்ணிக்கங்க சார். கீழ வந்து கிரீன் கலர்ல இங்க ஷேர் ஸ்கிரீன் இருக்குங்க சார் சென்டர்ல அது
பண்றேன்.
ஓகேங்க சார்.
இதுல கோஸ்ட் டிசேபிள்ட் பார்ட்டிசிபென்ட் ஸ்கிரீன் ஷேரிங்னு வருது. அது டிசேபிள் பண்ணி வச்சிருக்கீங்க. அதை ஓபன் பண்ணு.
இல்ல சார் ஓபன் பண்ணியாச்சு சார். இப்போ பண்ணிட்டேன் சார்.
இன்னும் டிசேபிள்ட் தான் வருது. நான் ஸ்கிரீன்ல வச்சிருக்கேன்.
ஓகே
ஓகே. ஷேரிங் போக மாட்டேங்குது. டிசேபிள்ட்னு வருது.
ஓகே. கோஸ்ட்
எஸ்.
சார் இப்போ பண்ணுங்க சார்.
இப்போ ஓகே.
थैंक यू சார்.
थैंक यू சார்.
வெச்சிங்களா?
ஓகே சார். ஓகே
சார்.
நைஸ் சார். ஓகே சார். எஃப்
हम सारा பண்ணா சார். सारा பண்ணா. Is it okay now?
Yes sir. Yes sir.
So first of all, I would like to thank the organizers, particularly the management of Sri Vidya Mandir College, Uttangarai. My title of talk in this virtual conference entitled Interaction of Extreme Laser Radiation with Radioactive Hazardous Materials. So the title itself giving more broad fields, I combine together into one talk. I mean that the extreme laser radiation generation itself is a tedious job, very tremendous work, and also how it can interact with the heavy element is the another title. So I want this field to present my idea within half an hour. So here I welcome one and all to this international virtual conference on physics of emerging materials and molecules. So before that, I want to tell you that the background about the history of the development of lasers. We know very well that in the year 1960, Neumann started his work, and also we are celebrated 60th anniversary of Neumann's massive achievement in concurrence with the International Day of Light Year from the year 2020. Still we are celebrating and continuing his achievements. We live in a photonics way today. So it will again continue to play a key role in shaping our tomorrow society with the most important of the modern lasers. So here our aim is how we can produce or generate the extreme energy of or the highest energy of the lasers and propagating through smallest spot is our achievement through the target. So that is also within the short duration, only in femtosecond duration has been always one of the main goal of laser matter interaction experiment. So in this way, in this European community, they have established extreme light infrastructure that is called ELI. You can refer from the website. ELI is the scientific community dedicated for producing the extreme light intensity, that is billion times billion brighter than sunlight falling on the surface of the earth. That means they have produced more than 10 power 24 watt per square centimeter intensity. So this will afford wide benefits to the society, ranging from improvement of study of cancer in the medical field and the fast electronics and our understanding of aging nuclear reactor materials to develop of new methods of nuclear waste management. So in this way, my title itself saying that the interaction of extreme laser radiation with the radioactive hazard materials. So before we start that, some of the basic information should touch for understanding these two, what is that interesting and very hard to understand these two extreme difficult jobs. So in this way, we know what is optics. Optics is nothing but study of light. Now we have switched over to modern optics. So it leads to where we started from classical, I mean that geometrical optics, particle optics, then quantum optics. So now the quantum optics field is developed tremendously how the laser dominates in our walk of life. So in this way, how the laser can be tightly focused. For that, beam shaping technique is we have adapted in our Periyar University laboratory. Different types of lasers are shaping the beam shape by doing different softwares. Apart from that, we are also doing some experimental part in our side. So in this, we have developed a Gaussian beam, Bessel beam. Bessel means the beam having non-diffraction. That means a diffraction-free beam is called Bessel, Bessel beam, and also Logger beam. Everything as it was studied in the special functions like LPH, like that. Okay, we touch it later. So even that's the prediction of extreme light intensity by titanium sapphire laser. The sophisticated titanium sapphire laser is my talk today. So how that the titanium sapphire laser can be produced the extreme light intensity, how it can be tightly focused. The technique is called optical parametric chipped pulse amplification, that is OPCPA, optical parametric chipped pulse amplification technique is the most powerful technique to create shortest pulse durations. I mean that when they are reducing the duration of time, automatically the highest peak can be achieved. So in this way, 10 power minus 15 second duration is the femtosecond. And also that the highest peak means roughly 10 power 21 watts per square centimeter. The area of 1 square centimeter, we can produce the power intensity in terms of 10 power 21 plus 21. So how it can be used in the processing of nuclear waste management is our talk today. So there are number of ways of nuclear waste, even the waste material derived from the nuclear reactor, how it can be disposed. There are different methods of disposing the nuclear waste. One is direct dispose method, another one is reuse in reactor to generate the electricity, that is what is that, again in the same method we can reuse it. Then types of radioactive waste and recycling nuclear waste by processing with the lasers. Nuclear it is what is that, hazardous waste material can be bombarded or blasted with the extreme light intensity, what I said. So the reprocessing of used fuel as per the International Atomic Energy Agency, that is AIEA, that is International Atomic Energy Agency. So these are all the classified one, how that fuels are having classified by this agency. Then nuclear waste management, treatment and conditioning and storage, then disposal. Then my last one is how the conclusion taking part in our talk. So before that, modern optics is nothing but it encompasses the areas of optical society, optical science and engineering that became popular in the 20th century. So here the modern optics also deals with the electromagnetic or quantum properties of light due to some other topics. Apart from that, it also included in other titles like quantum optics, then specifically quantum mechanical properties of light is involved. So this quantum optics is not just theoretical. Some modern devices such as lasers have principles of operations that depend on quantum mechanics. That is our talk. So here, what is optics? So for discussing our extreme laser, we need some of the basic information about how the optics can be classified. As per our study of light, this phenomena is associated with its generation, transmission, and detections. So apart from that, these optics can be classified broadly into three sub-major divisions. One is geometrical optics, wave or physical optics. Third one is quantum optics. According to that, it can be sub-classified into five major divisions like rectilinear propagation of light, speed of light, laws of reflection, law of diffraction, then dispersion. When we are talking this dispersion, again we have to understand about what is group delay dispersion, what is third order dispersion. These knowledge is required for understanding our high power titanium sapphire laser propagations. So here, what is geometrical optics? Nothing but the light goes straight line. It tells about rectilinear propagation of light. As per our Fermat principles, we know that the light travels one place to another in minimum time. That tells about rectilinear formation of time. The speed of light also measured by the different scientists. And finally, we have identified that approximately 3 into 10 power 8 meter per second. So the law of reflection, refractions are says that how the angle of incident is reflected equal to the angle of reflections. Then law of refraction is nothing but Snell's law. We can also explain that according to the optical reversibility, the ray goes from rarer to denser medium, it bends towards its normal. According to that, the reversibility, we can also express that the ray goes from denser to rarer medium, it's away from that normal. So these are all the sin A by sin R equal to mu. This is the things we have discussed. So dispersion is nothing but when white light is passing through the prism, it will be splitted into our constant colors that we know the VGR, we studied in our lower. So here the dispersion also classifies normal dispersion and anomalous dispersion. When you are talking about the dispersion to the next stage, there are some group delay dispersion and the third order dispersion. It tells about many applications. So I will tell you at the end of my slides. When next we pass on to wave or physical optics. Here, the physical optics is nothing but the wave travels in that wave form. It tells about, and also that it can be identified that electromagnetic waves, that is the vibrating electric and magnetic vectors traveling perpendicular to the direction of propagations. That is known that it can also pass through vacuum, and also it is transverse in nature. These are all the basic behind that electromagnetic waves, and also that according to the increasing order of frequency of electromagnetic radiation, it can be classified from that radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, and the cosmic rays. These are all the increasing order of frequency of electromagnetic radiation. So interference, as our famous scientist said, light plus light does not give more light, but may in certain circumstances gives darkness. This is the important concept to understand the interference. Interference is nothing but the modification in the light wave intensity according to the principle of superposition of two or more waves. So it is nothing but that there are two types of interference. One is constructive interference, another one is destructive interference. It can be produced by two methods. One is division of amplitude, another one is division of wavefront. The division of wavefront example is Young's double slit experiment. Division of amplitude is nothing but the Newton's ring experiment. So in this way, we can classify that physical or wave optics. What is diffraction? Diffraction is nothing but the bending of light rays around the corner of the obstacle and the spreading out into the geometrical shadows. The region away from the direct ray is called geometrical shadows. There are two types of diffraction. One is frontal diffraction, another open diffraction. So this is the both the source and screen at the finite distance, that is called frontal diffraction. The source or screen is infinite, that is called frontal diffraction. Then polarization is nothing but the particle vibrations are constrained to vibrate in a particular plane of vibration is called polarization. There are again, it can be classified into many types. One is linearly polarized, elliptically polarized, and circularly polarized, azimuthally polarized, then radially polarized, many type of polarized light. So these type of polarization we are producing in our laboratory, that is our peculiarity. We have achieved many types of polarization of light using the beam shaping technique, that is linearly, elliptically, then circularly, radially, azimuthally, all types of Gaussian beam, Lager beam, Bessel beam, then everything we are doing in our laboratory. The next one is double refraction. Double refraction is nothing but birefringence. Then monochromatic light is passed through the nickel prism. It will be split into another one is E-ray, ordinary and the extraordinary ray. So in this way, there are different types of crystals. If we are considering the positive crystal like quartz SiO2 or the negative crystal like CaCO3. These are all the crystals that change the characteristics. The two rays are, one is going faster. These are all the behavior study we can express in terms of the field, physical or wave optics. So in the quantum optics is nothing but very interesting title. It starts with some statistical mechanics like three types of statistics we may understand that is Maxwell distribution, that is Bose-Einstein, and also Fermi-Dirac. So according to this classical, then semi-classical and quantum mechanical treatment, the last one is followed for finding the subject quantum optics. It tells about the density of states using that different atomic structure model is studied, and also how atomic spectra is classified. Then energy levels. In the case of lasers, there are different energy level diagrams important for identifying where the laser action taking place. Then quantum and laser are the things we have studied. Then atomic and nano optics. So here it is considered that the nano optics is nothing but making the beam shape in the nano level, that is in the 10⁻⁹ meter. So the beam or part size can be reduced in terms of nano level. It tells about the nano optics. So it is nothing but particle-like properties of photons. So again we pass on to modern optics. We need to understand what is fluence. It is nothing but that laser pulse is the optical energy delivered per unit area, that is commonly identified that the unit is joule per square centimeter. So Faraday's isolator, most of the experiment in the laser demonstrations, many isolators are used, particularly in our titanium laser experimental setup where I worked in the European community, where one famous Faraday's isolator is a kind of optical isolator. It can be used to transmit certain light one direction, blocking the opposite direction. That is the peculiarity of this Faraday's isolator. This is based on Faraday's rotator. That means it constitutes the technologically most important type of optical isolators. Then the most important thing is focals and the Kerr cell. In general, when a strong electric field is applied to a material, the refractive index of the material changes. There are many types of electrically induced refractive index changes. It's the benefit of many heterostructure substrate are produced. It is that particularly in the case of what is that? That is, I will tell you that tuned lasers. But if the change in linearity is proportional to the electric field, the effect is called the focal effect. So if it is proportional to square of the field, then it is called Kerr effect. Then what is Q-switched lasers? A quality switched laser is a non-invasive laser that creates high intensity pulse beam of light. The Q-switched laser beam process lasts a merely billionth of a second. The energy emitted from a Q-switched laser is concentrated into very powerful pulses. And also that what is group delayed dispersion? It is a things of optical element is a quantitative measure for chromatic aberrations or chromatic dispersions. It is defined as the derivative of the group delay or the second derivative of change in spectral phase with respect to the angular optical frequency. Then third order dispersion is nothing but it is derived from the group, it results from the frequency dependence of the group delay dispersion in the Taylor expansion of the spectral phase versus angular frequency offset. It is related to third order, that group delay dispersion is second order, this one is third order. Then compressor, that is prismatic compressor. We might all studied or known that or heard that there is prism and the gratings. When combining these two elements like a prism, GRISM, gratings plus prism is called prism, there is some prismatic compressor is used. The prism, it is used to shorten the duration of positively chipped ultra short pulse laser pulse by giving different wavelength components at different time delay. There are some grating that is roughly when we are considering a 1200 joules per mm. Just imagine that the gratings having 1200 joules per millimeter. So this, when you have passed through that gratings, that components time delay or different time delay, that is called some compressor. There is some stretcher also used. So similarly, the inverse of the compressor is called stretcher. That is also we will discuss in our later slides. So NOFA is the important term often used in our titanium sapphire lasers. NOFA is nothing but non-collinear optical parametric amplifier. It is a white light continuum seeded optical parametric amplifier able to generate extremely short pulses when pumped by an amplified titanium laser system. So BBM crystal also important role in our titanium sapphire laser work hearts. Here the BBO crystal is a non-linear optical crystal with a combination of number of unique features: wide transparency region, broad phase matching range, large nonlinear coefficient, and also high damage threshold. These are all the components used in our work parts. So here again we can classify that there are two types of optics. One is linear optics, another one is non-linear optics. It is subfield of optics consisting of linear system is called. That means that is principle of superposition of waves is valid. But in the case of non-linear optics, it is invalid. The principle of superposition of waves is invalid. It describes the behavior of light in non-linear medium. So non-linearity observed only at a very high intensity, that is 10 power 8 volt per meter intensity. That is electric field in electric field is having that values of 10 power 8 volt per meter. Such those provided can be provided by the lasers. Here the superposition is no longer valid. So that is called nonlinear optics. Again, it can be classified into solid state optics, liquid optics, or gas optics. So these are all required for our understanding of the extreme light is interacting with the heavy elements. There is some plasma optics plays a major role for understanding that light matter interactions. In this way, there are three types of optics. One is called the solid state optics, liquid optics, and the gas or plasma optics. Here, the plasma optics is nothing but microscopically small, momentarily light reflectors formed by high power laser beams irradiating and ionizing solid surfaces, or powerful photonic devices for manipulating light that too intense to be handled by conventional optics. So this is not only can plasma mirrors redirect and focus high power light, they can also serve as ultra fast nonlinear filters, suppressing unwanted side lobes in the laser pulse beams. It means that unwanted lobes means that is one you may have studied in the diffraction. There are one central peak and side lobes, secondary. There are ups and downs. Same. Here we are suppressing the unwanted side lobes or unwanted noise in pulse laser beams to produce the highest peak power. So the generators a broad range of frequencies from terahertz to exes, potentially with the properties that are beyond the reach of current laser sources. So here nanophotonics. This field is study of application and the mounting technique associated with using the propagation and transmission, generation, propagation, and detection principles. Here, this plasma optics refers to use of plasma to manipulate light. So it has always been broken and therefore withstand
Sir,
extreme light
excuse me, sir.
intensity.
Sorry
Hello?
for interrupt, sir. Sir, next speaker is waiting, sir.
10 minutes.
Kindly take 10 minutes, sir.
Okay, so sorry. Okay, these are all that within 10 minutes, right? Okay. So the bright known for lasers light is there are the extreme laser is 10 power 21 watt per meter square. Here, these are all the things we have considered that how we have introduced different focal engineering for nano optics to identify the high intensity in the optimal locations. These are all the beam shaking, either circularly polarized, linearly polarized, then asymmetrically polarized, groundnut shape, or even for many waves techniques can be produced for our application, various applications. Even for solar cell preparation also, we have produced some beam shaping technique from the laser source. So here, the titanium sapphire laser, these are all the specification about the lasers. So these are all the, this is the important, this range is from range of absorption taking place. Here the emission, this is the absorption emission range from 600 to 1100 range. This is pumped by 900 nanometer source, and then this is also the pumped by another laser. The peculiarity of the titanium laser is this also pumped by other lasers. That is
technical issue at the sir கிட்ட speaker கிட்ட. Dear professors.
Dear professors, there is a small interrupt due to the technical issue. Sorry for that interrupt. Please wait 1 or 2 minutes. The technical issue will be cleared. Thank you, sir.
Dear professors, Dr. Anbarsan sir have some technical issues, sir. So kindly please wait for 1 or 2 minutes, sir. So we can rectify the connection, sir. Thank you. Excuse me, sir. Sir, kindly share your PowerPoint, sir. Anbarsan sir. Now it is visible, sir.
Visible?
Yes, sir. Visible,
yes,
sir.
Okay.
Yes, sir. Visible, sir.
Thank you.
Sir, kindly enlarge your PPT, sir. Okay. Okay, sir. Okay,
Yes,
sir.
sir.
Now
Yes,
it
sir.
is okay, sir.
Okay. So the applications of titanium sapphire lasers, this one we have discussed. So this is the pumped by another laser. It is having its pump source wavelength is 500 nanometer and the lasing out with center leak power of peak power of 800. So starting from 600, this is the broad emission spectrum from 600 to 1100 nanometer. So these are all. This is a 4-level laser, which is also schematically shown here. So these are all the applications of titanium sapphire lasers. So it can be generated high level generation, that is more than 60th harmonic generation they have achieved. It can also be used the picosecond. These are all the applications. As the time is restricted, I have switched over to the principle is called OPCP, optical parametric shift pulse amplifications. This is the father of this inventor, this professor named Gerard Moreau, who is working in the France, and the student of this Nobel or laureate. These two scientists, professors got she is from Canada. Her name is Professor Donald Dio Strickland. Both of them got 2018 Nobel Prize for this invention of optical parametric chirped pulse amplification, OPCPA. This is Gerard Moreau. This is Donald Dio Strickland. She got degree from this guide. Moreau. This technique is nothing but this is the vibrating or oscillating titanium oscillator. Again, it is having its seed pulse in such a way that the shape, when it is stretched through some structure, it is elongated like that. After that, we have amplified this stretched pulse into that one. Again, it is compressed. It is the peak power achieved, extreme light intensity. They have achieved. This technique is called OPCPA technique. So this is the technique. This is the titanium oscillator is emitting the seed. After that, it is through the beam splitter, it is going to structure. It is designed in such a way that that is 12,000 1200 grooves per centimeter. Just imagine this grating is arranged in such a way that after going to the structure, it is going to NOFA crystals having that focal effect. After that, it is going to amplifier in such a way that this signal, this seed signal is again it is amplified. Again, it is going to compressor. The same technique, it is also compressed in such a way that just imagine that after that it is going to structure the reverse pattern of this compressor. Compressor is the reverse pattern of structure. After this, it is going to that some pair of gratings reverse the dispersion of the first pair of compressor pulse. It is going to the resulting extreme light intensity that is called OPC technique. Here it is nothing but in terms of its work hours, it is also identified that this is the seed pulse is generated from the Kett cell, monolocked titanium sapphire oscillator pumped with 3.2 watt power of a frequency doubled continuous wave ND-arc Helium ammonium oxide laser. After that, it is produced pulse with a 17 femtosecond laser duration at a wavelength of 800 nanometer with a mean output of 6 nanojoule at a repetition rate with the rate of 72 megahertz frequency. After it is going to Faraday's isolator, it is the direction will blocking light in the opposite direction. That is the non-reciprocal optical propagation device. Again, it is passed through the structure. It is made up of, already I told you that it all the reflective light structures consistently pair of two gratings which we have shown in the last slide. After the grating and the spherical mirrors, it is going. That means 6 nanojoule is reduced into 0.6, 10 times reduced its energy by stretching the seed pulse. So automatically that time also increased. It is 17 picosecond is increased to 25 picosecond. After it is going to NOFA and the focal effect, again it is amplified, then it is compressed. Here for that achieve that extreme laser, one more amplification is given by the ND laser. Frequency doubled. The 1064 divided by 2 is 532 nanometer. Having its energy is 350. Again, it is going through the non-collinear optic parametric amplification through the this is high representation techniques. After that, it is going to amplifier. So these 2 times it is. There are different types of amplifier. One is called multi-pass and compressor. That we will discuss later. After compressing that one, you see that 6 nanojoule is increased to 35 millijoule with a similar same repetition rate. That is pulse seed pulse and also the both output also having the same value. So this is also whenever you compare that the direct way can be also used to the compressor for the auto correlation method technique. So here, this is also the same thing we have discussed earlier. This is the titanium sapphire laser facility available in the extreme laser infrastructure in the European community where I worked in that place. So here we use this technique for identifying many applications in such a way that I have also done some work with these facilities. So this is the thing. These are all the amplification techniques, how it can be amplified, this one. And also that these are all the theoretical part, how we can increase the spot size, reducing the spot size, increasing the intensity. That is the tedious process where it requires many calculations to identify that pulse energy and the repetition rate. So these are all the mathematical side. Whenever you want, I will tell you the slide whenever I see any questions. So due to some time factor, I am moving the slide very fast. These are all the different types of amplification method. Multi-pass amplifier. The pulse is going to that BBO crystals, that is beta barium crystal. It will be passed many times with the different beam reflectors. So output will be the highest amplified seed pulse is many times amplified. There are different types. Another one is called the regenerative amplifier. That is also one. This is the multi-pass amplifier technique. This is that also the schematic diagram showing that how we can go for chip to pulse amplification with the Professor Gerard Mauro and Stickland. Both are guided. This technique is called optical parametric chip to pulse amplification. There are different types of stretching and compressing technique methods are involved here. So I am moving very fast. So these are all the things. This is the achievement for making the highest intensity. During the year, they have touched that at 10 power 24 or 25 watt per square centimeter. So this is the Nobel Prize winner during the year 2018 for physics. This is Arthur Askin. He is manipulating. He identified that light can lift the object. He identified that optical tweezers he identified. So their application in biological system. And also this is Professor Gerard Mauro and Donald Stickland. So these three got Nobel Prize in the year 2018 for their invention of high power laser and OPCPA and twisters, optical tweezers. So when you are going to other side, how it interact with the heavy element, that is our title which we have given. So there are different types of heavy elements: solid active waste storage, solid radioactive waste disposal, and how the proportion of waste type is still in our godown. So these are all the things when you are bombarded many nuclear reactors, when many explosions happened in the many places like Japan, Russia, and other places. The trace element still giving some hazardness to the society limelight. So in this way, how the trace element can be collected and bombarded to reduce the lifetime achievement, the half-life time. That is our aim and objective of this our work. Here, these are all the storage where Chernobyl disaster happened, how the fuel cells is identified, how the causes are different. These are all the physigamma and other. For that, how we need some of the basic idea about gamma ray spectroscopy, how the interaction of radiation with the matter. The radiation is nothing but in terms of high energy gamma ray is interacting with the heavy go for nuclear fission process. So in that case, when you are interacting laser with the heavy element, we can change the after reaching the plasma conditions, we can go for changing the half-life period from million years to few minutes. That means they have also achieved. So in that case, I will give you that what happens matter irradiated with the extreme light radiation. When the extreme light titanium sapphire laser having about 10 power 21 watt per square centimeter falling on that heavy element, there is some plasma mirror will appear in terms of flow of plasma. When there are different accelerated photons and heavy electrons clouds and the total elements, these are all giving out. So when you are talking about the experimental setup for photofusion fission using high energy electrons.
Excuse me, sir.
Yes.
Sir, sorry for the interruption. Sir, next speaker is waiting, sir.
Okay. So this is the gamma ray spectroscopy target, the significance of gamma emission peak like that. So this is the thing, applications of extreme irradiance and its applications. So this is the conclusions. So that Nobel orator identified that. So we can go for any long duration that is radioactive hazardous waste can be reduced in terms of a few minutes. That is the achievement by the Mauro, Professor Gerard Mauro. 18 Nobel Prize in Physics with the Donald Sticks. The pair won their work inventing the process of chip to pulse amplification the laboratory for laser energetics at the University of Rochester. So they identified that these are all my obligations for tight focusing achievement. So these are all my students. This is where I worked in the place. Titanium sapphire facilities infrastructure in the European community. So this is the myself with Professor Gerard Mauro, who got there 18, where I worked with him in the University of Transylvania University at Brasov, Romania. So this is myself with Professor Gerard Mauro. This is the organizer. So these are all my, this work is funded by Indo-Hungarian Education Exchange Program by EGC. So thank you one and all for nice sessions listening. Any question, please?
Sir, thank you, sir. Thank you for your wonderful talk, sir.
Thank you.
Dear professors and dear participants, if you have, this is the question session. If you have any doubts or clarification, you may ask.
Any question, please?
If you have a doubt or clarification, you may ask through the email also. Otherwise, you can post the question in the chat box.
My
Thank you,
email
sir.
ID is anbarsanpm@gmail.com.
Okay, sir.
Thank you, sir.
Thank you, ma'am.
Thank you, sir. Thank you, sir.
Good afternoon to everyone. The only way to discover the limits of the possible is to go beyond them into the impossible. If you want something new, you have to stop doing something old. Today at this session, we have most reputed resource person, most respected professor, Dr. S. Kumaresan sir, with us to discuss about phytofabricated zinc oxide and iron oxide nanoparticles for antibacterial drug delivery applications. I invite S. Kanimuri Assistant Professor, to give intro about Dr. S. Kumaresan sir. Thank you.
Good afternoon to one and all present here. First, I thank you for giving me the opportunity to introduce our today's special guest, Dr. S. Kumaresan sir. A warm welcome to you, sir. At present, he is working as an assistant professor in Harinyanana Government Arts College at Cheyyar, and he has 22 years of teaching experience and 14 years of research experience. Moreover, he has specialization in the field of spectroscopy and computations on crystal growth. He got 2 awards for his research work. Additionally, he published many papers and more than 15 in reputed journals at national and international levels. Moreover, he published 4 research articles in the same above. He also published 5 engineering physics related books during 2000 to 2009. Recently, he organized state level quiz competition and allocation competition for his excellence. Thank you, sir.
Sir, your PPT has been shared, sir. Okay, sir.
Yeah.
Thank you.
Now it has been shared. Is it clear now? Shall I proceed? Sir, is it audible?
Yes, sir. It is audible, sir.
Yes, sir. Okay. See, thanks for your nice introduction. And I'm always very happy when there is an invitation from Sri Vidya Mandir Arts and Science College. Thanks for the authority and thanks for the initiative that you have taken an international virtual conference. And I'm thankful to this. So today the talk is something about the phytogenic metal oxide nanoparticles, especially for biomedical applications. We are working on some other applications also, but we are concentrating only on the biomedical aspects and how the phytogenic metal oxide can be prepared even with a simple laboratory setup. Yeah, first of all, thank to my academic father, Dr. Sethuraman Gunasekharan. He has given a lot of chances to me, and this chance is also one and all in that. Without him, I am nothing. This is the only thing I should say to my academic dad. And thanks for giving such an opportunity, sir. This is the college I have affiliated and comes under the banner of Indian Spectrophysics Association, affiliated to Arijarana Government Arts College. Recently, we have celebrated the Golden Jubilee here. And this is the laboratory we have initiated, and it was inaugurated by my academic dad. And I'm going to present such a simple work which we have carried out in this simple laboratory at Arijarana Government Arts College. And last year, we have conducted an international conference, and probably the first ever international conference in the government college setup under the able leadership of my academic daddy, Dr. S. Gunashekhar. First of all, let me just highlight a few aspects which I am going to discuss today. What are the advantages of a phytogenic approach? Why we need to go for it? And I'm going to show you two different metal oxide nanoparticles, how we prepared using this phytogenic approach, and how an antimicrobial assay, which will be an application for this, and in what ways that these are all advantages than the traditional thing or traditional one, the others will be using it. Though the method is simple, but it has got its own way, and it will be useful for most of antimicrobial activities, especially the zinc oxide. And this is a material which can be prepared in many ways. Rather, most of the nanoparticles like zinc, iron can be prepared in n number of ways. But our concentration is only on the biological aspects by using the biomethods, by using the available facilities in our college. So this method we simply refer it as with bio preparation of zinc oxide and iron oxide nanoparticle. And it has been from ethnobotanical species Achanthras aspera. In Tamil it is called Nayuruvi. It is available everywhere. And after that we have to characterize the protein characterizations like the diffractional analysis, and of course our favorite for conformational analysis like Fourier transform infrared. And to mention the sizes of it, the scanning electron microscope as well as EDOX. And the biological applications like antibacterial, it is more susceptible than any other nanoparticles, especially to E. coli and S. auris strains. This is the materials which we prepared, and importantly, we have the Achanthratis aspera leaves extract. This plays a vital role. Varying the concentration of these leaves extract, we are going to control the capping agent as well as the stabilizing agent in order to avoid the agglomeration in the nanoparticle system. We are varying this with the various concentration for all possible polar solvents and solutions. Rather, the extracts which are with a different concentration will behave differently based on whether it will act as a capping agent or as a stabilizing agent. If not, they should not be acting as a reducing agent. And all are water-based compounds. And for these water-based compounds, it is much important to have at what stage that this will be going to stabilize. So these are all the materials that all are easily available, and it can be easily procured too with a high degree of purity. And this is the sample I am showing you. Wherever you can find it, you just take up this and you can do such wonderful work. In fact, it is in English. It is devil's horsewhip, but it is not doing any devilish thing. Rather, it is doing all good things for us. And in fact, naturally, it is the best antibiotic, and it can be directly applied to most of the open wounds. If you have some open wounds, you just take 2 or 3 leaves, you crush it, and that extract has been directly applied for it. This will be a Paka antibiotic. And to show you some of the result analysis for biosynthesis to zinc oxide particles, later on I'll come to iron oxide. We are very specific about the biosynthesis because we have taken only the acquired materials which are all available, except the precursors. The remaining things are purely biomaterial. So the precursors only the zinc acetate hydrate, zinc nitrate, ferrous sulfate, and sodium hydroxide. That's all. And all are basic components. So we claim that it is a biosynthetic method, and this is the simplest scheme. For most of the phytoconstituents, it is already available in our leaf extract. What actually happens is the zinc nitrate will get reduced to whether it is going as a capping agent or as a reducing agent. In the first case, this will be acting as a reducing agent. And in the second case with the zinc nitrate, this is supposed to act as a capping agent. In both these cases, the removal of water molecule that will be showing something that whether it can go on either way to act as a capping agent or as a reducing agent. This is something fishy. But when we see this, the end result, we have got a zinc oxide nanoflower. This is almost similar to the flower structure what we have. And the other one is zinc oxide nanoparticle system. Both are entirely different. So when we have zinc nitrate, its behavior is different if you use zinc acetate. So that's how the scheme refers to us in which way that the concentration of your extract, the phytoconstituent in it, which will be either acting as a capping agent or as a reducing agent. In simple terms, if you got a flower-like structure for this concentration, this will be acting as a capping agent. Whereas if you got a zinc oxide nanoparticle, this will be a regular zinc oxide nanoparticle. It will be a reducing agent. So this is how we can classify on this, depending on how we can manipulate ourselves in taking up the capping and the reducing agent. So this is a simplest protocol even in your laboratory we can do. If we are able to do it in our laboratory, definitely you can do it in your laboratory. So this is a zinc acetate dihydrate solution. And of course, the key is the concentration. And we have the leaf extract. Preferably it will be this brown color. And it has been filtered nearly 3 to 4 times for better results. And after reduction, that means after adding up these two in 4 hours time, there is a possibility of reduction. What we have shown in the scheme, we'll have zinc hydroxide. So the water presence will be there, and after calcination, we'll be getting a Paka pure zinc oxide nanoparticle. And of course, the yield itself is also very good. Preferably, we'll be getting almost 1 gram, and if you use it for an extract of almost 250 ml. So this is the simplest protocol. Only thing is the calcination to be done not beyond 400 degrees centigrade. If you do so, there may be a possibility of charring. And in order to avoid it, we can not go beyond 400 degrees centigrade. And on the end of it, you will find a wonderful zinc oxide nanoparticle. We did some characterizations so as to confirm whether the biosynthesized material is a zinc biosynthesized material is a nanoparticle or not. And we did the protocols like XRD with the FTIR and UV spectroscopy. Just to confirm the size of it, we used SEM as well as EDAX, and at last we did some antibacterial activity. See, the XRD exactly confirms there were two concentrations we did. The blue color is zinc oxide B of different concentration, and the red color, which will be zinc oxide A, we jumped to B. Almost similar peaks. Only thing is the concentration variation may just vary the intensity of the peak, but not the orientation. So exactly on the same places you'll be getting the peaks. There may be some additional peaks also that we are investigating on in what shape and size that it has got. This is an average size. Whenever we did, we just took normal procedures like divisor. We have gone for the William Hall's method. And of course, it is a perfect straight line. The variations is not much. We are absolutely getting a linear fit. And either way, we have got the points. So the line will pass through for these two concentrations. And the average crystallite size will be almost uniform. So this is how these two graphs will illustrate us. There is a linear fit for these two concentrations. And if we synthesize it, definitely it has to be confirmed with FTIR. And we have zinc oxide, the 664, which has been shown here. Whereas in the other part, here also there will be a smaller peak. This is not an easy peak to identify, whereas we have got it. And 460 and 461 on these two exactly confirms the zinc oxide. All other peaks are due to our precursor material in it. The important thing is the purification, which is not so easy for us because of the lack of facilities we have. We tried hard to take up this, and at last there is one keto group which is present in the plant material itself, and we have one NH2 vibrations. We are unable to evade it because this is a very short peak in this. And also the CH bending peak, I mean NCH bending peak, this is at 880, whereas here it is at 830. There may be some concentration and interactions is also there. So we just confirmed that the synthesized nanoparticle is purely of zinc oxide. That will be a confirmation which has been carried out with the FTIR at 460 centimeter inverse in both the concentrations we reported. And definitely without UV, we cannot directly confirm exact similarity at this. I already mentioned there is the purity issues, which is in our laboratory system. When you go for it, even after 8 to 9 filtrations, obviously there will be some impurities. And the question of a pure sample itself is such a good research one has to carry out. And with the available sources in our college system, we have got to the purity level to this extent, and UV will be the example for it. So 346 nanometer and 345 nanometer for these two concentrations definitely confirms the presence of zinc oxide. This is the same image, and you see how perfectly oriented when we zoomed to 1 micrometer. And if you go further for 200 nanometer, we can find the same pits which is available, which means it has been evenly oriented and the shapes are almost similar. And William Hall's method have confirmed there should be a linearity in it. And this image is mere confirmation there should be linearity even at the depth of 200 nanometers. and this is of zinc nitrate salt. It is something glassy from 1 micrometer to 200 micrometer, but it finds some sharp edges, and also it have the flower structures. So you find the difference. This is, you are not getting any sharp edges here, whereas here you can have the sharp edges. And look at here, I'm just showing it in the cursor. It is almost a flower, and this is also a flower structure, and here also a flower structure. This is something funny, that if you zoom further, you can get an ideal flower structure. Only for this concentration you'll be getting it. Here I have shown this for 1 micrometer, and this has been shown in the scheme. So the zinc nitrate salt will be doing something. We have identified a biogenic zinc oxide nanomaterial, and this flower structure is something interesting to us. And further investigation is on for varying concentration to get different flowers. We did some antimicrobial activity because it is a very good bacteriocide, and Miller-Hilton-Agar method was carried out, and we have a different plates. There is a well 6 millimeter diameter, and the incubation period is only 24 hours. The thing is, we maintain at the room temperature, it will be around 37 degrees centigrade. So if there is a range, if you reduce further to 25 degrees centigrade, the zone inhibitions will be something different. And then it was very erratic. Because of the flower-like structures, the growth will be on only one direction. So unidirectional antimicrobial activity can be suppressed if you use this. So for a test of any pathogens at the room temperature, it is possible if you use zinc oxide. And as I already mentioned in my introductory slide, it is just against the E. coli and SRS strains. For both this, it is very, very effective. And we have taken a positive control as azithromycin, a general antibiotic in nature. And we have a positive control. But the gram-negative bacterial strains, which exhibits potent against the bactericidal activities. And also, it exhibits potential fungicidal activities. Rather, it is susceptible to both these, which means it can be used as a fungicide as well as it can be used as a bactericide. So both way it is possible. We just introduced with the copper oxide, zinc oxide and copper oxide combination. We have two types of it, that means bactericide and fungicide. Both have shown some potent activities in terms of zinc oxide as well as copper oxide. Copper oxide also has produced in the same way, but in the mixture with that, it will showing different strains. So this is the zone of inhibition, and you see such a large areas for these two strains, SRS and E. coli. And there may be overlapping for gram-negative because the concentration is something higher, and it may be because of the spread in room temperature is higher than the spread in temperatures lower than the room temperature. So almost we are getting the similar pattern. And to tell you something more about the iron oxide synthesis, the same procedure, but used this time with some concentrational changes along with the sodium hydroxide. It has been well stirred. Homogeneity has been maintained at a particular temperature, preferably around 60 degrees centigrade. This leaf extract has been added with the sodium hydroxide solution of 0.1 molar concentration. And it has been stirred for 2 hours. You'll be getting two distinct layers of separation. After mere filtration out, Rather, if you heat it to 400 degrees centigrade for more hours, this calcination takes place and we'll be getting a wonderful, almost more than 2 milligrams of iron oxide nanoparticle. Let's see a perfect orientation which has been matching with it. And all these orientations for an iron oxide has been matched out in XRP. And we have here, just for an instance, we have zoomed. The exact iron oxide peak will be at 853. And iron oxide combination, that means oxides combinations, which will be at 571. So this clearly confirms the presence of iron oxide. All metal oxides will be in the range of less than 400, whereas iron is something special, which will be coming around 600 centimeter inverse, and we got a peak of 571. And similarly, this is UV spectrum. The UV spectrum, exactly about at 400 nanometer, 399 euro. Again, it is a purity issue. And if you go for the scanning electron microscope, just for an instance at 200 nanometer from 1 micrometer, there are 3 different orientations possible in that. It has been shown in the red samples. This is something different, whereas here we have some broad shape, but it seems to be like a slab, and within which some depth in it. And there are one such an area where we have an accumulated same size oriented particles that has been zoomed into 200 nanometers. This is perfect iron oxide on these 2 areas which we have been zoomed out. See that? This is antibacterial activity. The similar activities for both iron oxide and our zinc oxide. The control seems to be the same. A similar patterns will be observed, but this time we have changed the concentration to 150 microliter. This is 150 and this is 50. And here this is 100 to 150. Previous case is only 150 and 25 ml. Just for iron oxide, which are much active. So we increase the concentration so as how the spread which will be taken within 24 hours time. So almost the spread is exponential and it will be much faster than our zinc oxide. And you see that the crystalline size of zinc oxide nanoflowers, which will be around 7 to 22 nanometer. Previously, all other workers, they did it with 6 nanometer to 15 nanometers, whereas we have matched with almost 7 to 22 nanometer. But this is XRD calculation, whereas when we go for SEM analysis, but this is something different. We have got 20 to 40 nanometer. Of course, that variation will be there. This variation has to be reduced if you go for the refinement by doing a lot of filtration, as well as we have to go for the purity content. And in the morphological point of view, both zinc oxide as well as iron oxide, which exhibits certain microstructural features. We identified the flower-like structures which will be having a sharp edges, whereas for iron oxide will be having a slabs which is also having the sharp edges, which others have not reported. So in our conclusion, we find some ionic species influence. That may be the reason for it to have such a morphologist, so that it will be having the microstructural features. So the further study is on for the surface morphology of zinc oxide nanoparticle, and also how the microstructural features can be enhanced so that the size of the particle can be reduced to less than 6 nanometer. Both have the same antibacterial activities even at very low concentration, but the methodology for which the concentration of the leaf extract, which will have different designs of our nano system or nanoparticle. So the design cannot be modified. Rather, the concentration can go for different changes. So the design originally, the nanoparticle, what it does have, can be modified, or rather it can be changed with different morphologies by just varying the concentration of the leaf extract. And more so, it is eco-friendly technique, and there should be a fine control by changing the concentration of it in terms of size, the shape, as well as the composition of nanoparticle. Truly, this is one such a simple work which will be useful for most of our budding scientists to go and do their research work in a trial and error method with the same zinc oxide, copper oxide, iron oxide, which are all easily available for us. And I should be thankful to those people. They did a lot of characterization work, and we acknowledge all these institutions who have supported us as we are in a rural college. We don't have any such facilities, and we will be doing some research work along with our scholars. I'm thankful to all these institutions. They have helped for us. Thank you very much. I hope I have completed in time. So thank you one and all for your patient listening. And if you have any queries, don't feel for it. Please ask me. I'll be in a position to tell you.
Thank you, sir. Thank you for your wonderful presentation, sir, on metal oxide nanoparticles for drug delivery application.
Yeah.
Dear professors and dear participants, if you have any doubt or clarification regarding the metal oxides for the drug delivery application, you may ask. Now it is a questioning session. You may ask the question. You may also post the question in the chat box also.
Yeah, that will be better, so that I'll be in a position to answer them if they are not able to ask for it. Anyway, thank you so much.
Thank you,
Thanks a lot.
sir. Thank you, one and all. Thank you, sir.
Thank you, sir. Thank you, SK, sir.
Thank you. Thank you so much.
Good evening to everyone. Creativity is thinking up new things. Innovation is doing new things. Today's research is tomorrow's innovation. In this session, we have a valuable personality with an innovative mind. He is our today's resource person, the most respected professor, Dr. Muthusenthil Pandiyan sir. Now, I request our assistant professor, Balaji sir, to give a small intro about our eminent personality.
Good evening, everyone.
Okay, sir. Okay, sir.
I am very much happy to introduce and welcome
Okay, sir. Okay,
Dr. Muthusenthil Pandiyan, Research Scientist, SSN Research Center, Chennai, on behalf of our SVM College and IVCPEMM 2021 team. He had completed his PhD in SSN Research Center under the guidance of crystal legend, Professor Dr. P. Ramasamy. His research areas are single crystal growth by solution and melt techniques for NLO and ferroelectric and thermoelectric applications. Also, he is working on perovskite solar cells, dye-sensitized solar cells, quantum dot sensitized solar cells, nanomaterials, and thin films. He had received nearly 23 project funds from BRNS, SERB, DST SERI, UGC DAE, IGCAR, Recycle 3, Canada, and SSN Institute. About 298.81 lakhs. He had received 24 awards for his presentation in national and international conferences. And he published nearly 93 publications in SCI Scopus journals with 1387 citations with a 20 H index and 40 I10 index. Also, he has 35 proceedings in chapters. Also, he had attended 183 in conferences. He had given 89 invited talks in several institutions, conferences, and seminars. And he had visited 6 national laboratories and have many collaborations with various national and international laboratories. Under his guidance, 4 students had completed their PhD, 5 currently pursuing their PhD. In addition, 7 postdoctoral fellows are working with him, with 3 senior research fellows and 4 junior research fellows are working under various projects. In person, he is kind-hearted, humble, great motivator, and soft in nature. I once again welcome him to deliver his talk. Thank you.
Thank you, sir, for your nice introduction. I just share my PPT.
Sir, kindly share your PowerPoint, sir.
Yes, yes, I am doing that, sir.
Yes, sir, it is visible, sir.
Okay. Good evening, and
Yeah.
thanks for your introduction, sir. First of all, I would like to thank the conference president, Professor Gunasekaran, sir, and the convener of this program, Dr. IVCPEMM madam, for giving me this opportunity to share some of my recent research work in development of high-quality nonlinear optical and periodic single crystals by Sanganaya Ramasamy method and RSR and ISR methods for practical device applications. I myself, Muthu Sendil Pandian, working with Professor P. Ramasamy sir in SSN Institution, Chennai. So, growth of high quality, large size, with defect free, with high physical property single crystals are still very challenging task for crystal growers by solution growth method. High quality single crystals is of great importance when it's come to the device making. In this presentation, I am going to present you a method which gives you the crystals of very high quality. So all the crystals, whatever you are going to see my next slides by solution growth method. So this is the outline of my today's lecture. Importance of several nonlinear optical and periodic single crystals and growth of nonlinear optical and periodic single crystals by ordinary slow evaporation solution growth technique, and what are the problems in the conventional method grown crystals, and growth of the similar nonlinear optical and periodic single crystals by another method is called as unidirectional Sanganaya Ramasamy method, and what are the advantages in the SR RSR method grown crystals, and finally comparative characterizations have been made between the conventional and SR method grown crystals, and growth of 4 interphenol derivative single crystals, and we have selected one amino acid based single crystals for SKG device applications. We have grown these crystals by normal SR and RSR method, and comparative characterization between the SR and RSR method grown crystals, and finally I conclude my presentation. So single crystals forms an indispensable part of rapidly advancing technology. The art of growing this kind of single crystals has turned into science with a variety of wide range of applications, and a variety of single crystals find applications in lasers, nonlinear optics, LED, periodic detectors, optical components, and so on. So the availability of these kind of single crystals is equal to the ability to raise the country's economy. The ability to grow the crystals is an essential criteria for the competitiveness of our nation. All these single crystals are grown by unidirectional SR method grown by us. And these are some of the possible single crystal application, and quartz crystal is used in India watches, and KTP single crystals in the frequency converter devices, silicon single crystals in your solar cell devices, and these are some of the possible lithium ion single crystal application that has been used in India. Piezoelectric gas laser, optical data storage technology, telecommunication industries, and eye treatment through laser. And these are some of the borate family single crystals, and it has been used in your frequency converter devices, and it also produces lasers. These are some of the different crystal growth techniques are available to grow the good quality single crystals, in which solution and melt techniques are most commonly used. In the present lecture, I am only concentrated in this unidirectional solution crystallization method invented by Professor K. Sanganarayanan and Professor P. Ramasamy when they are working in Alappa University, Karaikudi. These are some of the properties needed for nonlinear optical single crystals. So it should be high nonlinear optical coefficient. For laser applications, one must know the laser diameter threshold value of the grown crystal. So we must grow the crystals with higher laser diameter threshold values and fast optical response time wide transparency range in the range of UV, visible, and IR, that is 200 to 1100 nanometer. It should be high thermal stability. For practical device application, we have to polish the single crystals with a different shape and different size. So we must grow the crystal with higher mechanical stability, and we have to grow with higher chemical stability also. The ability to process into the crystals, and finally, device fabrication should be very easy. These are some of the 4 interference derivative single crystals grown by conventional method. We have grown these crystals in a beaker or petri dish or crystallizer. Some of these crystals are finding more than 100 times greater than that of the normal potassium dihydrogen phosphate single crystals for nonlinear optical application. And this is again 2-amino 5-nitropyridine derivative single crystals for nonlinear optical application. As I said, we cannot use these crystals as it is for practical device application, even though it has the very good perfection and very good nonlinear optical coefficient. The size of the grown crystal is very small. So what we have done is we have chosen the same crystals by different method. This is a crystal grown by conventional method. The same crystal we have selected for the unidirectional crystal growth. So this is the crystal grown by unidirectional method as grown crystals, and this is the cut and polish wafers. So here we can use it as it is for the device fabrication. So 100% solution to crystal convertibility is possible in this method. So several attempts have been made to grow the crystals by slow operation, slow cooling, seed rotation, melt growth technique like Bridgman, Zegralski, and so on. So, but all the reported methods are at elevated temperature that leads to thermal induced growth defects, and it also the complicated equipment, difficulty in growing large single crystals, and also multi-step processes are also involved. So these are some of the drawbacks in the conventional method grown crystals. Because of the temperature instability, multinucleations are formed in the grown crystals, and cracks formation are during the growth, and milky opaques are also formed in the conventional method grown crystal. This is the crystal grown by conventional method. This is the ferroelectric triglycine sulfate single crystals, and we cannot grow the single and bulk size single crystals in this conventional method. And all the crystals are having different planes, growth sector and growth sector boundaries. So this has been already reported that the dislocations have been originated from the growth sector boundaries. In conventional method, we cannot avoid the facets, growth sector boundaries, and growth sector, etc. So the dislocation content present in the conventional method grown crystal is very high. So we have to avoid this, and we cannot grow with highly uniformity in the grown crystals by conventional method. And formation of different solvent inclusions, low angle grain boundaries are appeared in the conventional method grown crystals. So not only these crystals, almost all the conventional method grown crystals are having these problems. So because of these reasons, the crystal grown by conventional method are very high dislocation content and very low physical properties. And these are some of the crystals grown by conventional method for nonlinear optical and ferroelectric application. If you see the crystals, all the crystals are having different planes, facets, growth sector and growth sector boundaries. But for practical device point of view, application point of view, so we need phase matching direction. So other portions are cutted after cutting the phase matching angle. For devices like frequency doublers and optical parametric amplifiers, phase matching needs to be achieved. Otherwise, the conversion efficiency would be very low. So in this point of view, this SR method has given the solution, and it is possible to grow the crystal along its phase matching direction, along A direction, along B direction, C direction, or phase matching direction, or polar B direction for ferroelectric material. So whatever direction you want, you can grow by this method. So this is the 2 examples I have given here. This is the conventional method grown diglycine barium dihydride single crystals grown by conventional method. So we have grown these crystals along its C direction, and this is again sodium sulfide dihydride single crystals, nonlinear optical application. We have selected this 100 direction, A direction for unidirectional crystal growth. So this is the one of the main example. So this is the standard potassium dihydrogen phosphate single crystals for laser applications. People are still using these crystals for laser application. So SKG direction, second harmonic generation, that direction is 59 degree. So what we have done is we have cut the crystal along its phase matching direction along its 59 degree. Like this, we have to mark like this, and we have to cut along its phase matching direction, and we have to mount at the bottom of the glass sample, unidirectional glass sample, and you have to pour the saturated solution, and you have to grow along its phase matching direction. So this is the work done in RRK Tindur. This is the SKG directed KDP single crystals grown in RRK Tindur. So this is the KDP single crystals grown in SSN. So this is the conventional method grown 2-amino 4-nitrophenolate single crystals grown by conventional method. The same crystals we have selected for unidirectional crystal growth method, that is SR method. So in order to get the highly purified material with higher physical properties, we have slightly modified this SR method. It is also called as a RSR method, that is rotational Sangaraya Ramasamy method. So we have rotated the glass sample in order to avoid the impurity segregation in the glass sample. I will explain you in my next few slides how to grow the crystals by SR method and RSR method. This is the type 1, type 2 SHG element we have fabricated using these grown crystals. So this is TGS single crystals, as grown crystals. As I said, we cannot use these crystals for practical device application. So for ferroelectric single crystals, we have to consider only this polar B direction. So what we have done is we have selected a small portion of this TGS B direction, and you have cut like this, and you have mounted, and you have grown the crystal like this. So this is the conventional method grown crystals, and this is the SR method grown crystals along its polar B direction. This is again glycine phosphate single crystals for ferroelectric application, and we have selected this polar B direction for IR data application, and this is the SR method grown crystal. So the crystal growth techniques for the present investigation, I am going to concentrate only in these two techniques, that is the conventional slow operation solution method and the Sangaraya Ramasamy method. So for the growth of the crystals by SR method, we have to consider all these steps very, very carefully. That is instrumentation, synthesis and conventional crystal growth, selection of different seed crystal direction. That is, you have to first identify the phase matching direction using this NDR laser, and different sizes of the glass sample. It depends upon the solubility of the material. If it is a very high soluble material, we can choose higher inner dia and outer dia. If it is a very low soluble material, we have to choose very small in size glass sample. And unidirectional crystal growth and growth optimization, that is, we have maintained two temperature. One is at top portion and another is at bottom portion. So it depends upon the solubility of the material. We have to choose the growth temperature at top and bottom portion separately. Depending upon the growth temperature and the growth rate will vary, and you have to measure with different direction. So the experimental setup of this SR method consists of the glass sample, and this glass sample is kept inside this water bath, and a small thin plate like a seed crystal is mounted at the bottom of the glass sample, and a saturated solution is poured inside the glass sample. A small hole was made on the top of the glass sample for the solvent evaporation. After 3 hours, due to the gravity-driven concentration, all the solid molecules are approaching the crystal surface directly. So this crystal surface attracts more atoms very easily. So in this SR method, the concentration at bottom portion is very high comparable to the top portion because of the gravity-driven concentration in SR method. So after that, we have to apply the temperature. One is at top portion and another is at bottom portion separately. And this temperature coil is directly connected to the temperature controller separately, top and bottom portion. And we have to choose the little higher temperature at top portion for solvent evaporation, and bottom of this temperature is only for growing crystal. The only thing is we have to maintain the uniform temperature near the seed crystal and the solution interface. So to avoid the temperature fluctuation of the daily variation, water is frequently added inside the water bath. So we have to maintain the uniform water level in the bath. So and then the freshly prepared saturated solution is frequently added inside the SR ampoule in order to avoid the fungus growth. So after a few weeks or few months time, depends upon the solubility of the material and the material nature, the crystal will be grown like this. So this is the complete experimental setup of this SR method. So this is a selection of seed crystal cutting and mounting in the SR method. This is the morphology of the TGS single crystals. So we have to choose like this, a small portion, thin portion, you have to choose for cutting. And then we have to make it's a very thin plate, and you have to mount at the bottom of the glass sample like this. And then you have to pour the saturated solution. This is schematic diagram. This is the actual TGS crystal mounted at the SR growth sample. So some of the advantages of this SR method. So single crystal with specific orientation in a glass sample. So we can grow the crystal by A direction, B direction, C direction. So whatever direction we want, we can grow by this method. Or if you need the phase matching direction for harmonic generation application, we can choose this. If it is a ferroelectric material, we have to choose the polar B direction. So everything can be possible in this SR method. So easily we can find out the growth rate along any plane. That means we have to choose the crystal with a different direction under identical condition. What is the growth rate along different direction? That we can be possible in this SR method. So the entire quantity, 100% solution to crystal convertibility is possible in this SR method. So this is the 25 centimeter longest TGS crystal grown by us for ferroelectric IR applications. So with a thin plate as a seed crystal, this much of large size crystal can be possible in this SR method. This is the conventional method grown sodium sulfide diode single crystals for nonlinear optical application. The same crystal we have mounted at the bottom of the glass sample here, and this much of large size crystal can be possible in this SR method. You see, from the 2 mm thickness, this much of nearly 10 centimeter longest crystal can be possible in this SR method. So the requirement of large size crystal growth chamber is avoided in this method. For the growth of crystal by this SR method, we need only this water bath. This water bath is nothing but the fish tank only. The size is 1 feet cross 1 feet, and we need 2 RTD temperature controller and a sensor and a ring heater and ammeter and etc. So within 5 to 6,000 rupees, we can make our own experimental setup of SR method in our laboratory. For that, we need at least we have to maintain the 1 kV or 2 kV UPS. So we have to continuously monitor the system. Otherwise, the crystal growth is not possible in this method. So not only cylindrical shape depends upon the growth of the crucible. Any shape can be possible in this SR method. This is the longest benzoin single crystal by SR method, organic single crystal for nonlinear optical application. So this is the crystal growing inside the glass sample, and this is the crystal outside the glass sample. So crystal which have post-growth cracking tendency can be grown without resulting in the post-growth cracking tendency. That means we can grow the crystals without any milky opaque or micro cracks present in the grown crystal, because in conventional method, due to temperature instability, several micro cracks appeared in the grown crystals. So we cannot avoid this in the conventional method. But in the case of SR method, so we have selected 2 temperature, one is at top and another is at bottom portion. So there is a stable saturation and a uniform growth rate. There is no solvent inclusion or milky opaques are present in the SR method grown crystal. So the crystal quality is always superior to the conventional method grown crystal. This we have confirmed with several characterization like HRXID, dielectric, birefringence, and chemical etching and so on. So far by this method, more than 250 numbers of crystals have been grown. So we can grow the positive and a negative solubility crystal. We can grow the low soluble single crystal like potassium acetalate. We can grow the moderate soluble like TGS single crystal, and we can grow the highly soluble benzoin single crystal. You see, the maximum solubility obtained in the benzoin is 265 grams per 100 ml. This is a very, very high soluble material. So this is the low soluble KP, this is the moderate soluble TGS, and this is the high soluble benzophenone, and this is the negative soluble lithium sulfate single crystal for scintillation application. So based on our experience in the SR method, we have attempted to grow the crystals by this SR method. The total length of the grown crystal is 1350 mm longest long, and then the diameter is 5.5 centimeter. This we have grown in 2012 with collaboration with the National Physical Laboratory in New Delhi. So this is the actual experimental setup of 8 feet experimental setup of SR method. So we have mounted the seed crystal here at the bottom portion, and we have maintained the 1 temperature at the bottom portion and 1 temperature is top portion, and top and bottom is directly connected to the temperature controller. So when the crystal is growing, we have moved the controller, the heating coil from bottom to top. So we have maintained the uniform temperature near the seed crystal and the solution interface. This much of transparent crystal can be possible in this SR method. So this is the morphology of the benzoin and single crystals. We have selected this A direction, 100 direction, because the growth rate along A direction is very high compared to the B and C direction. This is the different growth stages of this SR method. This much of transparent crystal is growing in the SR method. This is the 850 mm longest benzophenone. This is the 1350 mm longest benzoin crystal. This is the double refraction pattern of this benzoin crystal. The total thickness of this crystal is 5.5 centimeter. So how to harvest the crystal from the glass sample? So this is the 25 centimeter longest crystal grown in the solution in the water bath also. So we have to reduce the temperature from high temperature to room temperature. If it is a 40 degrees Celsius, we have to reduce like this 1 degree Celsius per day. And then we have to capture from the glass sample like this. And we have to mark the top and bottom portion separately using the glass cutter. And you have to cut using the diamond wheel cutter. And you have to remove the top and bottom portion separately like this. So this is the 25 centimeter longest TGS single crystal inside the glass sample. So we have to again mark the top and bottom portion separately using the glass cutter. We have to carefully remove the glass sample very carefully. Otherwise, the crack will be formed in the globe sample. So this is the transparent crystal without glass sample. This much of transparent crystal can be possible by this SR method. After that, using this diamond wheel cutter, we can cut the crystal. This is the as-grown 25 centimeter longest TGS crystal, and the ethylene glycol is kept inside the tray in order to avoid the crack formation in the grown crystal. And depending upon the mechanical stability of the material, we can vary the speed in the crystal cutting machine, whether it is a low hardened, and whether it is a moderate hardest material or very high hardest material. Depends upon the material, and we can vary the speed also. And this is the cut portion of the TGS. This is the as-grown crystal here. And this is the cut and polished TGS wafers for iodide application. And you are going to see some of the crystals grown by SR method. And this is the sodium sulfide dihydride single crystal. And this is the cut and polished wafers. And this is the diglazine zinc chloride dihydride single crystals by SR method. This is the as-grown crystal. This is the cut and polished wafers. And this is the 2-amino-5-chlorobenzamidine single crystals. And this is the as-grown and cut and polished ferroelectric glazing phosphate single crystals. And this is the 4-nitrophenol derivated single crystals by SR method. And this is the sodium para-nitrophenol single crystals for nonlinear optical applications. This is the crystal grown by conventional method, and we have selected this A direction for this unidirectional crystal growth, and this is the cut and polished wafers. So the crystals grown by conventional and SR method, we have carried out all these studies in order to identify the crystalline perfection of the grown crystals. We have carried out the high resolution X-ray diffraction and chemical etching measurement. In order to check the laser damage threshold, we have carried out under identical condition. For mechanical stability, we have carried out the Vickers micro harness. For optical quality, UV NIR. For electrical measurement, we have carried out the dielectric permittivity and dielectric loss. In order to get the optical homogeneity of the grown crystals, we have carried out the Bayer-Benson measurement. So the samples grown by conventional and SR method were prepared with identical thickness. The surface damage is affected by the energy absorbing defects such as stains, scratches, and polishing contaminants, which strongly influence the physical properties very strongly. Therefore, all the experiments are performed on the highly polished crystals grown by conventional and SR method. So in order to confirm the reproducibility, all the characterizations were repeated several times, and more or less similar results have been observed. So this is the high resolution X-ray diffraction pattern of the sulfamic acid single crystals. This is the grown by SR method. This is the crystal grown by conventional method. If you see the conventional grown crystal, there are a lot of low angle grain boundaries which clearly seen the intra-beta solvent molecules in the crystalline matrix in the conventional method grown crystal is only the responsible for observing this kind of low angle grain boundaries. But in the case of SR grown crystal, there are no grain boundaries because of no solvent inclusion, and a single and sharp peak of the SR grown crystals, which clearly describe the crystal grown by SR method is very superior compared to the normal conventional method grown crystal. This is again for sodium sulfide dihydride single crystal. For SR grown crystal, it is 70 R-second, but in the case of conventional method grown crystal, there are a lot of low angle grain boundaries because of the solvent inclusions present in the conventional method grown crystals. And the chemical etching studies have been carried out for the conventional and SR method grown crystals. And for chemical etching is an important and powerful tool to identify the dislocation density present in the grown crystal. And these first two pictures is for the conventional method grown crystals, and the third and fourth pictures for the SR grown crystals. And randomly distributed but strictly oriented etch speeds have been observed for the conventional and SR grown crystals on successive etching for 5 to 10 seconds. And the etch bits enlarge the size, retaining the geometrical shape and do not disappear, just suggesting that the bits are due to the dislocation. The calculated average etch bit density of the conventional method grown crystal is 8.2 10⁻³ centimeter per -2 approximately. But in the case of SR method, it is very low compared to the normal conventional method grown crystal. You can always see that the number of HPs present in the SR grown crystal is less comparable to the conventional method grown crystals. And these are some of the various type of defects present in the conventional method grown TGS crystal. So not only TGS crystal, almost all the conventional method grown crystals are having this kind of problems. That is the solvent inclusions, low angle grain boundaries, micro cracks, milky opaques, microcrystallites, and so on. So this much of several problems are appeared in the conventional method grown crystals. The reason for less dislocations in the SR grown crystal is like this. This is the morphology of the conventional method grown crystal. It has been already reported that the dislocations have been originated from the gross sector boundaries. But for practical device point of view, we have to use only the single direction, that is a phase matching direction. In SR method, we have grown the crystal in a morphological defined facet. There is no gross sector boundaries or less gross sector boundaries comparable to the conventional method grown crystals. So less dislocation present in the SR grown crystals and the higher physical properties present in the SR grown crystals comparable to the normal conventional method grown crystal. In order to check the mechanical stability of the grown crystals, we have carried out the Vickers micro harness measurement, and this is the load dependent harness measurement. When the load increases and the harness also increases, and having maximum harness at the 100-gram load, and after that the number of cracks appeared near the indentation is very high. So further measurement are not possible in the conventional SR method. And this blue color indicates for the SR grown, the sodium sulfate dihydride single crystal. You can clearly see the mechanical stability of the SR grown crystal is very high comparable to the normal conventional method grown crystal.
Excuse me, sir.
Yes, sir.
Sir, sorry for the interrupt, sir. Next
yes,
presentation was speaking, sir.
5 minutes.
Okay, thank you.
So this is again for glazing phosphate single crystals. You can see because of the higher mechanical stability, large number of micro cracks appear near the indentation, the SR grown crystals. This is for the SR grown crystals. And the reason for lower mechanical stability in the conventional grown crystal is because of the solvent inclusion and a variety of parameters such as variation in supersaturation and a minor fluctuation during growth and a non-uniform growth rate are governed the solvent inclusion. These are some of the solvent inclusions appeared in the conventional method grown crystal. But in the case of SR method, we have maintained the 2 temperature. There is no solvent inclusions present in the SR grown crystal. And we have carried out the laser damage threshold value because of the higher mechanical stability and a higher crystalline perfection. The laser damage threshold value of the SR grown crystal is very high, that is 17 millijoule per centimeter square, comparable to the normal conventional method grown crystal. This is again for benzoin single crystal. This is for SR grown crystal. This is for conventional method grown crystal. And we have carried out the dielectric permittivity and the dielectric loss value of the conventional and SR grown crystal. And the optical quality of the conventional and SR grown crystals are measured using UV-VCNIR measurement under identical condition. This much of several surface problems are appeared in the conventional method grown crystal because of the higher crystalline perfection. The surface smoothness is high comparable to the normal conventional method grown crystal, and there are less scattering centers appear in the SR grown crystals. So the higher output intensity, which clearly indicates the higher UV-VCNIR transmittance in the SR grown crystals. This is again for diglazing zinc chloride dihydride single crystal. So the final conclusions of my this lecture is, so because of the higher crystalline perfection, the physical properties such as mechanical stability, optical quality, and the optical homogeneity, dielectric permittivity of the SR grown crystal is very high and superior comparable to the normal conventional method grown crystals. And in the SR grown crystal, there are no gross sector boundaries, so there is no solvent inclusion present in the crystals, and the less scattering centers and no micro cracks, milky opaques, and less dislocations are present in the SR method grown crystals. So maybe I conclude here, sir. So thank you for your kind attention. If any questions, I am very happy to respond. I have a few more slides also. If time permits, I will explain.
Thank you for your wonderful presentation, sir. Sir has taken a tremendous effort for the growth of various type of crystals based on non-linear applications. And dear participants and professors, if you have any doubt or clarification, please put your questions in the chat box. Next, we move to the next session. Thank you, sir.
Thank you. Thank you.
Thank you, sir. Good evening to everyone. A man does not need brilliance or genius. All he needs is energy. Energy will do anything that can be done in the world, and no talents, no circumstances, no opportunities will make a man without it. In this session, we have an eminent professor, Dr. M.V. Reddy, sir, with us, who is joining to discuss about energy storage and conversion. I request Mr. G. Kalayan, Assistant Professor, to give short intro about the eminent professor.
So he took the admission for the field. So the way like because he doesn't have the iron.
பாலும் தேனும் பாகும் பருப்பும் இவை நான்கும் கடந்து நான் உனக்கு தருவேன்.
Maybe I have some other meeting. Shall I? Maybe I can we'll keep in touch by email. Is okay? Yeah. Okay.
Good evening to one and all. I have a very pleasant duty of introducing our resource person, Dr. M.V. Reddy, sir. He is currently working as a senior researcher level 3 at the Institute of Research.
Thank you very much.
Center of Excellence in Transportation, Electrification and Energy Storage, Hydro-Quebec. Over the last 20 years, he has conducted leading research on materials for energy storage, solar cells, electrocatalysis and photocatalysis. Dr. Reddy sir has published around 200 papers in various international journals. Dr. Reddy sir is serving as an editorial advisory board member in Material Research Bulletin and Journal of Energy Storage, as well as several open access journals, and the regional editor Nano Science and Nanotechnology. Dr. Reddy sir has conducted several workshops related to functional materials and energy storage and conversion, and delivered 12 plenary, 14 keynote, 62 invited and 18 contributory talks at various conferences, and conducted a number of workshops on battery materials, fundamentals, synthesis and characterization techniques. He trained many more than 120 high school, college and international exchange BTech, MS and PhD students, and personally mentored 7 students for electrochemistry and material science. His research won many awards in national and international conferences. His projects won awards in Singapore Science and Engineering Fair, SSEF, awards gold 10, silver 8, bronze 6, merit 10. Dr. Reddy sir is an invited life member in the International Center for Diffraction Data, USA, and he was awarded a free life membership award in 2010. He won an excellent safety lead 2015 and a long service award 2014 at the National University of Singapore. He is an elected committee member in Institute of Physics, Singapore 2015 to March 2018, Material Research Society, Singapore, 2 times 2016 to 2020. He served as an honorary auditor IPSS and MRS Singapore, Global Material Networks 2012 to till now, and a member in MRS USA and the International Electrochemical Society. Thank you, sir.
Okay, thanks for your kind kind introduction. In fact, thank you, madam, and then especially for the management for inviting me. In fact, today morning I'm able to attend all opening ceremony. In fact, really.
Sir, good evening, sir.
Good evening, sir.
Yeah. Good evening. Good evening. It's really very kind people. Although for me, it's like I'm not able to listen all the talks since I just wake up. So okay.
Yes, sir,
Hopefully,
sir.
I'm able to.
Morning 5 o'clock. I'm correct, sir.
Yeah. Well, hopefully I'm able to convince you, saying that since I trained in the area of maybe what I will do is that just I'll show my slides, so and then we can okay. Shall I?
Sure, sir. Sure, sir.
Okay. Okay.
You share the screen, sir.
Yeah. Share slides. Yeah. It is there. Share. Okay.
Yes, sir. Now it is visible, sir.
Okay. So whatever it is, sorry, we are able to go next slide one.
Yes, sir. Yes, sir.
Okay. So again, I think welcome to all. So in fact, I am also from your neighbor. So I am from Bangalore. So from Kolar. So I can speak Telugu, Kannada, and then Tamil. I'm able to understand. In fact, since So overall, again, thanks for a kind invitation. In fact, really I enjoyed the opening ceremony. I think a lot of different physicists. In fact, few physicists already know them, especially for example, Professor Jaishankar or Jaivel, and then few other people also. Some of the speakers already familiar with them, and I met them personally during the conference. In fact, first time I'm presenting your college. In fact, you see that at least you people have a lot of interest. I think this is very important. And also I saw that a lot of physics community, since based on, you can see although I'm trained in the area of material science, so almost like 16 years, the whole like solid state ionics means basically I trained in the area of the condensed matter, so physicist. So both what they call thin films. During my PhD, I worked on RBS, Rutherford backscattering spectroscopy, and again energy storage for lithium battery, etc. In fact, I'm going to tell a little bit more fundamental. So,
Good evening, sir. This is Jai Shankar from Tirupati, sir. How are you, sir?
Sir, yes, sir. I know you, sir. Because in fact,
because you pronounced my name, it is my pleasure duty to say hello to you, sir.
Yeah. In fact,
waiting for your
lab
talk,
also
sir.
we visited. In fact, okay. So since it's a physics talk, so I make it as a more, since we want to impress you, we would like to tell the story about the physics. So I'll talk about the thin films. See, I know that sometimes the battery materials, I think we need a bulk material is very important.
Please
In
go
fact,
ahead,
a few years back, we have been able to present the I think conference organized by Professor Jaishankar. So I think he's the main person, and we were able to visit the Tirupati Darshanam also. In fact, thank you very much, sir. Still, I remember. Sir, really great. In fact, Professor Jaishankar is one of the best, very nice conference organizer. In fact, they have done very good job and really great. So I think nowadays, because of COV, I think we are able to talk in a more what they call as virtual. I think that is okay. Somehow we are able, no other option. Still, there is a way to survive. Time being. So these are the outline of my talk. In fact, I think previously I was there in Singapore. Again, you can see the climate temperature. You may go to I think now ice is melting slowly. So sometimes these are the little bit extreme climate. Sometimes 25. Still okay. Only few days, not for all the time, and other areas. So I think so. This is very important since we know that some few people from the only few PhDs. You can see a lot of high school and junior college students have been trained in the Singapore. So idea here is that since the lab was very excellent, so only thing we take care of the safety. I think people can, many students, they're able to train the area of the what they call nanomaterials or material. Still, they're not a video. I'm not able to do any laser physics or a little bit, because there we need a little bit more safety issue. Still, with the background of the material chemistry, we can do the research in the. And also sometimes some students were able to, especially these slides are very important since you people are doing masters. I think so this will motivate you. I think these people have been, they're able to present in the various national and international conferences. And you can see the Web of Science at this particular website. I think a lot of school students also have been published some few papers. I think that will be made them to, so that way we can demonstrate them to, I think anybody can do research. Only I know that sometimes depending on facilities, we are a little bit lacking. So don't worry, at least with the best teacher, I think with the physics teacher, you're learning the both and basics. I think that will be very useful for your future if you're doing the research, especially in India or within university or IISc, IIT. It's a lot of opportunities at the end. Sometimes we are getting experience, we can go outside. So these are the different opportunities people can do. So overall summary is that nowadays is a global world. So in the sense that I think a lot of opportunities are there. Don't be shy. I think especially your, I think today morning I saw something. Just don't be, at least be optimistic. Don't be negative. I think you can do what are the things you want. So that's why everybody will get opportunity. Don't be, okay. So these are the small help. I think since I was in Singapore, it was next to, it is easier. I think it was, we are able to do a lot of people within the, especially Indian universities, as well as some our neighbors and within Singapore as well as outside. So these are my research interests. In fact, I don't have much time. I'll discuss some few examples and a particular example, and then again, I'm telling that you're a physicist, you can work with the thin films for microbattery technology. Again, so in fact, this technology already, some people from especially Tirupati University also they're working. So again, I'll tell a little bit difficulties of thin films. So that's why not much success in the thin film microbattery technology when compared to your bulk material. Again, since you're a physicist, is very important. For example, developing the in situ technique, for example, spectroscopy. I think the Ramans are sometimes any different spectroscopy I'm going to discuss. I think that is very important. Again, so remember, for example, if you go to solar cells, I think a lot of physics is playing examples. For example, batteries are solid state ionics. I think like physics or chemistry will play an important role in the. So I think one slide, importance of materials. For example, if it is being use it for different applications, I think UV energy, environment, sensor. I think some of the other areas have been previously covered with different speaker. For example, the zinc oxide, what are the applications? I think previous speaker have been already covered. And for example, I think we are going to touch up more on battery material. Again, in general, energy storage is a multidisciplinary. I can tell you the physicist, chemistry. I think we have, I'm telling you with the master's your background, I think we can do, you can switch to, for example, physicist can learn chemistry. So that way, I think is more, if you go for research level, don't be think that I'm a physicist, I want to look only for the instrumentation. That is not possible. It is nice. You can do all the things. For example, I think today, our keynotes are first, second presenter, he already is electronic, although with based on the physics background, I think he went to the electronic engineering, so what they call electrical engineering. In fact, recently I heard some talks with somewhere in IIT, NIIT Raipur, I think one electrical engineer, I think he is able to present how the potential start will work. I think this is very, I think you're able to catch the idea about how the electrochemistry, so sometimes physics, So at the end, it is very important if you go for research, I think we have to be more multidisciplinary. That will be good for you to future to succeed. In fact, these are the small things. For example, energy storage, what is the importance? For example, in the battery industry, I think you want to what they call a smart grids. We want to do solar energy or wind energy or run electric vehicles. I think battery materials are will play an important role. Or what they call a smart cities. I think so, especially physics are the example. For example, sensor design. I think a lot of physics will play an important role. I think understanding the principles of physics depending on the applications. So is one example. I think the people are replace the hybrid vehicles, electric vehicles. One opportunity again, the problem mainly is the cost is a major hurdle. So these will be difficulties. Again, I think you can see one more interesting thing is that, for example, Tirupati, Amar Raja, I think they're well-known battery company that they're spending extensive, especially lead acid battery. They're very pioneer in this for the last many years. They're working. In fact, they're one of the important people working in the especially battery materials, example, especially lead acid battery, etc. And another one is solar cell. Presently, I think people are telling that compared to the solar cells, the batteries, I think they want to look for the low cost battery package. I think the cost of nowadays, the cost of the battery pack is more expensive. So that's why they want to reduce further cost of the solar energy. I think we have to look for the low cost battery material. I think these are the small things you can tell different opportunities. For example, so there's a huge interest with the different type of people are spending in the, especially in terms of the different companies working with in terms of electric vehicles or autonomous vehicles, the driverless vehicles, etc. I think these are the one slide I'm going to tell the principle how, since you are doing masters is very important. I think everybody is carrying this type of mobile phones. I think they contain, sometimes you may see that 3.7 volts, this type of pulse cell. So it contains a positive and negative electrode, and there is a coin cell. And usually, suppose, for example, you use the same type of material in a 18 cylindrical cell with a laptop, I think you use the similar things. Or future you want to run for electric vehicles, I think they can use big type of the packs or put it in the big type of the model. Again, so again, it depends on the technology, depending on size, they will do different things. So I think what are the importance of, for example, these are the one slide I'm telling what is important, for example, in a, so here, so it is physics or chemistry will play an important role, understanding the materials. Okay, again, the simple principle, I think all might have known that how the electric battery will work. So it contains a positive electrode coated in the aluminum foil and negative electrode coated in the copper foil, and there will be a separator. So separator is nothing but to avoid the short circuit. There is nothing but there is a polymer separator. So positive electrode means they call as a cathode, sometimes a chemist they will call, or so usually lithium containing compound, layered compound, or iron phosphate. And negative means it contains lithium metal or graphite, or sometimes of the metal, different type of things are going to use. Charge means sometimes these are the similar concept means oxidation, or anodic scan means positive current, and sometimes we electrical engineer they call it state of charge means 70%, 50%. In fact, if you buy in future electric vehicle, I think these are all the SOC means 70%, 50%. Based on that one, you can tell, okay, my batteries will be discharging fast, like that way we can tell the state of discharge, charge, like that way you can tell, okay. And discharge is contains reduction. I'll tell you next slide. What anodic scan, negative current if you do the cyclic voltammetry. And the electrolyte, we use some liquid based 1 molar LiPF6 and ionic liquids and polymer based. So these are all the, again, if you go for the solid state ionics means solid electrolyte, solid state ionic, like solid state physics will play an important role. Again, the current collector is we use the copper current collector for anodes. And the reason for that one is that it form alloy if you use the same thing here, and it may oxidize to 3.5 volts. That's why we need a proper way fix the electrolyte. I think these are the simple concept. I think we may need a connecting binder and PVDF because your materials you want to stick in the current collector. We need a PVDF. It is like gum, and conducting carbon to improve the pickup of the fast charging. I think we need this type of the things. I think these are very important one. I don't feel that it's another Nobel Prize given to chemistry. You may see carefully Professor John Goodenough. I think he's a physicist. You know, he's one of the well-known superconducting physicists. I think his background, I think, so solid state chemistry. So based on the physics and chemistry knowledge, I think he's one of the persons who contributed, for example, layered your cathode, positive cathode you're using for mobile phones. I think because of his discovery, I can tell them, although the original work is done by the French, from Hagen-Muller, the one of the well-known, I think they used to study with the sodium chemistry. I think based on this idea, I think people have a different way people can do. I think by listening always is very important. Research ideas will get sometimes people go to visit some different places. I think, oh, okay. Some people have, for example, Professor physicist. Okay, I think he's working to particular application, for example, NLO or optics. You know, he may not bothered about electrochemistry. Sometimes people like me, I go visited his lab. Oh, I'd say they're doing some material. Okay, maybe why can't you try for lithium containing, for example, lithium niobate? You know, can I use this material for the battery? So that way curiosity will develop, and the end sometime by clicking, doing some new experiments. I think there is a way we are learning. I think there is a way what they call as with the exchange collaboration, or sometimes sharing the knowledge. I think this is very important for the community, scientific community, and that will be make them to, I think people can think differently. So always there is a way I can tell that since you're a young researcher, although whatever I'm presenting, I'm not able to, although I worked for 20 years, still I didn't do any breakthrough work. Still, I think maybe it's a lot of challenges are there maybe with young researcher. By listening some few points, maybe you can pick up in a different way, or you can focus in a different way. That's why always research is, as an academic researcher or anybody, I think we can focus in some particular thing. We are contributing to society, okay? At least after doing all this one, anyway, everybody wants to get a Nobel Prize. It is not so easy, I think still. So that is the way we are aiming for all the people, especially any academic researcher, we are able to get Nobel Prize. I think it is not so easy still. So this is the way, so we are contributing to society, okay, to the, in terms of the either physicist or chemist or material science. So these are the principles of lithium battery. I think Professor J. has not really discussed about the principles. Just I'm going to touch up some basic fundamentals. So we know that there contains a positive electrode, lithium move from one side to another side, whereas electron will pass through external circuit. During discharge, the reverse reaction occurs. So we can get a voltage, for example, oxidation means we get a this plateau, for example, 4 volts. Same thing, if you do with the galvanostatic current, you will get a 4 volts. That's why these are complementary, called oxidation reduction. Or they call this way called rechargeable batteries, means you have to get this. So this is very important. Okay. For example, cobalt 3+ is there. 3+ becomes oxidizing to 3+ to 4+. Okay. So since this is not a specialized battery conference, so I'm going to skip saying that there are, if you go to more focused research, we can do depending on materials. We broadly classified 4 type of mechanism. Among more popular is the intercalation. The intercalation means one lithium we are going to play. So that is my summary. Again, in summary, if you want to work with like batteries, I think we want to look for long life. This is very important, more reliability, and adapt the climate condition, for example, temperature. Extreme cold climate or the high temperature also is to adapt. That's why we need a separate heating and cooling system depending on the pack. like climate conditions. And also we need a fast charging because people wants to charge a battery, or for example, you know that by, for example, petrol pumping, they do fast, like that type of things we want to do. That's why sometimes there is a lot of interesting things going on. It's not so easy because since they are solids, so there is a problem with the diffusion. So that's why we have to wait for some time to charge a battery. It's not a problem with your battery charger. It is a matter of the material inside. So that's why we need some time to, there is a lot of technologies going, still people are working in a different directions. I think at the end we look for more safety. I think these are the main important criteria. I think the cost is a major issue. For example, people want to be electric vehicles and green. I think the cost made them to think in a different way. I think nowadays we don't have any option. Now the people are thinking that so still we want to reduce the pollution, or for example in COV they're thinking that mainly because of pollution. So since the cost they're not bothering. So now alternative is that we have to look for the batteries. That is the way people are thinking still. So I think I can tell that there is another maybe 20 to 30 years. I think people are telling people have to replace by all gasoline vehicles. So that is the predicted one. We'll see how the things will move in future. I think already discussed. These are the important points. I think already. So you may ask you what is the importance. For example, if you see this type of, for example, compared to a lead acid, so nearly 1.25 volts and nearly 4 volts we can get, for example, if you use the lithium battery. That's why in terms of energy density compared to your other type of batteries, and you will get a high energy density. Energy density is nothing but difference between this charge minus discharge potential multiplied by capacity. So that's why, okay, you can, because of this lightweight, and people can use it for more like space applications, or for example, different type of applications. So these are the materials. It's very important. Since you're a physicist, you can do with concentrate on only thin films, or I'm chemist. I think we, depending on that one, we can use different type of. Since I don't have much time to discuss all the details, still I'm going to. So these are the various materials people can focus. For example, optical material. I think they need a single crystals depending on the things people have research. People have to plan. Okay. So regarding characterization techniques are concerned, we can do either X-ray, it is very useful. X-ray diffraction is a Bragg's law, a lot of physics is involved. Or for example, Raman spectroscopy, I think we want to see the results of a very well-known technique. Or thin films, the Rutherford backscattering spectroscopy, I think a lot of physics is involved. And then all you can see that, for example, you can focus specialized, for example, X-ray absorption, neutron. Still, your physicist, you can do again at the end. So sometimes if you go to research in a more focused way, I think you can understand. For example, XPS is also physicist will do. So since I trained as both physics and chemistry, for me, I think it's nice to learn all the techniques. That's why I'm able to handle the many techniques to run myself, and I can interpret the data, and then I can do simulations. So that way, there are all a lot of experience I gained by, I can tell long-term experience like that way. So these are the various characterization techniques people are going to do. For example, you can do either XRD, that is very useful, or you want to do Raman spectroscopy or microscopy techniques. Or sometimes we need more sophisticated like solid state NMR. These are all the things we can concentrate, or sometimes surface area. So again, what I am telling, one simple thing is the olden time, maybe almost 20 years back, I used to take the spectra, nearly good spectra for refinement, where 24 hours I used to run. Nowadays, because of detector technology, just same spectra I can run with 5 to 10 minutes, in the sense that because the technology, I think now our life is a little bit easier. So still we can do a lot of in situ. So idea is that what the world is also we are able to do. Only thing we are a little bit slow. So new generation people, you can get fast data. I think that is advantage for you. And also nowadays, because of this technology. So these are simple XRD. We can take, for example, for this particular sample, somewhere this is a X-ray tube, and then there's a detector. We can put somewhere sample here. What will happen when X-ray is incident on the thing? So diffraction will occur by knowing the in-planar distance and the angle, Bragg's angle, by knowing what they call it, the Bragg's law, 2D sin theta n lambda. I think they're all things you learn by the MSc solid state physics. Or so with this formula, we can calculate what is going to happen. For example, you want to see either materials amorphous or polycrystallines, or depending on lattice parameter, we can calculate and also full width of maxima, we can calculate what crystallite size, and you can only to go per TM still, and we can see either by amorphous or nanocrystallines like that. So that is a very useful technique. And we can do either comparing the TEM, either armor pulse and nano size, etc. So these are the various characterization techniques we are going to use since I don't have much time. So regarding thin films are concerned, I think we can get a different approach. For example, either chemical vapor deposition technique, CVD, and physical vapor. Again, depending on your applications, you would optimize thickness and composition, understanding the surface and mechanical properties are important. So these are the RF sputtering. So attached to the glove box, I think if you have a hygroscopic sample, you can do. I think interestingly, you're a physicist, you can play with power, all the lot of parameters, composition, deposition rate. And if you want to work with the micro batteries, you can do layer by layer, you can deposit. Again, I'm not talking about the difficulties and these technologies due to time limitation. Sometimes you're a physicist, you can do with the smart windows for electrochromics. If you use organic chemistry background, you can work with the same organic molecules or conducting polymer, etc. So characterization techniques is concerned, I think Rutherford backscattering is one of the useful technique. For example, thin films. So usually is that when the helium beam is hits on the thin films, due to binding the backscattered kinetic energy, for example, higher atomic number will come first. So by knowing the Rutherford manipulation software, we can know the composition, thickness, and what are the elements you have, etc. Again, so the importance of the what they call a nuclear atom ion beam spectroscopy. So again, you can do a lot of interesting physics. Okay. So since I don't have time, again, for example, you can take, for example, you can do a lot of interesting physics depending on that one. You can understand things. And for example, what is the composition with respect to the different sputtering parameter or deposition rate, etc. I can do. And sometimes with the Voger electron spectroscopy, again, is another spectroscopy. We can see the homogeneity of thin films with respect to thickness, etc. Again, so since you're a physicist, when we need a sophisticated techniques, it will be useful for you to analyze what type of composition, etc. And if you do a XRD, if you see the amorphous samples and then crystallization with respect to sintering, etc. Again, sometimes you can understand how they what they call target. These are all things. These are all a kind of observation while doing the research. I think you have to observe all the things and write to note in a properly record. I think that will be very useful for you people. Suppose since you, I think I have another 10-15 minutes, madam. How much time I have? Okay.
Sir, you may take 10 minutes, sir.
Okay, so I'll try to finish by 10 minutes. Okay, 10 to okay. So 10 to 12 minutes. Okay. Okay. So these are the important things. It is very important. Sometimes if you make a battery, we need a 70 with 15. This way you can do at a lab scale. Again, the same approach in tons of the quantity or kilograms in an industry, they will do all is automated setup. Since in a laboratory, you can do 70, 15, 15. So we can coat it in either ductile blade or take a glass slide. You can coat a copper foil or aluminum foil. Copper is for anodes and then aluminum for the cathodes. You can roll it or without rolling also good contact is there is fine, and cut into small discs and finally put in a vacuum bag. There are all things you can do. Again, I'm telling that sometimes lithium battery a little bit more expensive. I can tell the university still. I think these are the little bit difficulties. So again, you can do either by coin cell fabrication, is you can put somewhere here and the separator and lithium metal, and you can put the sample. So these are bulk material. If it's a thin films, what you do is that again you can coat in the either by current collector, for example, stainless steel substrate. You can put the sample, same thing. Really, you don't need to do any coating procedure, etc. And these are the characterization tool I mentioned already. You need a battery tester and impedance. Again, the impedance analyzer is very important. If you can do, for example, heating and cooling, you can do and understand the conductivity measurements. And again, a lot of physicists you can do. So very important measurements you can do. I think I don't know how we can calculate capacity and how much time is taken from one voltage to another voltage, and knowing the time and current, and then by mass we can calculate the capacity. So this capacity multiplied by voltage will give the energy density. Okay, and anyway you can do, if you go more focused research, you can do a lot of things, interesting things, and we can see how the performance looks if it is a battery, what is the good capacity, etc. So since I don't have much time to discuss, usually, for example, there are another characterization techniques called high voltage current plots, and impedance spectroscopy is very useful tool. For example, if you want to either by solar cells or, for example, resistivity measurement or superconductivity. So this technique is the same instrument. You can use it for different type of the applications. So for example, battery is nothing but simple resistance. How the resistance is going to vary with the before charging or after charge the battery. So these are all, if you focus more details, since I don't have my, since you're doing masters, I think I do more focusing research is not, maybe I can tell that this impedance is nothing but resistance as a cell. So before charging and after charging, so overall total resistance should be negligible in the sense that we don't see, for example, initially you're getting some 10 ohms or 100 ohms. After cycling, if it's exceeding to around 1000 ohms, 2000 ohms, something wrong with your battery. That's why this technique is very useful to tell that to see the health condition of the battery. Okay, so again, I don't have much time to discuss all the details, and since you're a physicist, you can do complex modeling, for example, resistor, capacitor, or for example, different type of, for example, inductor. So many what you learn from the electronics, for example, what they call a solid state physics background, you can use this knowledge to adopt this one. Okay, again, I don't have much time, so we can do with RBS, we can do, for example, lithium yield, how it is going to happening like that way. So again, the concentration, how the homogeneity of films, I can do this one. So since I don't have much time, thin film, I'm going to skip these details on the cobalt nitride again, so we can try to prepare the sample. So I'm going to tell some few examples on the bulk material. Again, as you know that I think usually cathodes is a limit of 3 to 5 volts and lot of anode materials. I think these are the promising cathodes are there. So due to time limitation, I'm going to tell some one example, lithium aluminum fluorophosphate. So again, we need a good capacity for a long time. That is the only thing. And we have to understand a lot of physics is there. Again, understand the crystal structure. So this will play an important role. And since you are a chemist, I think again, we need a little bit knowledge on how to prepare the new material, we design it, and we have to understand the redox potential, etc. So in summary, some people are looking for, why don't you use this, I think JBL size lithium is a little bit expensive. You can do sodium chemistry. Again, the disadvantage of sodium is that we can get a little bit lower potentials, that a little bit difficulties are there. Again, with the same sodium compounds, you can do some interesting superconductivity. For example, sodium cobalt oxide is already known. Here, a lot of physicists, there is a lot of opportunities for the physicist, okay? Again, remember some materials are maybe interesting for other applications, so I don't have much time to discuss. So these are the one of few example with the sodium-based chemistry. Again, I think these are the little bit challenges. So these are the different type of the wind screen for the last, okay. Again, I think there are a lot of opportunities. For example, some of a few materials, people can use it for the energy storage. For example, there's a lot of things. Since I am not able to discuss each and even individually, still overall as a battery thing, we have to look for the potential is lower and higher. So that is really interesting for the large scale applications. Again, as if you see, for example, some spinels are there, I think maybe interesting for you for the magnetic properties or some other applications. I think people, tomorrow, some people, few materials are going to cover with some defining and other applications, okay? Again, as the battery energy storage is concerned, I think we have to look for reduce the potential to lower is very interesting for applications. Again, some examples are there. So the TiO2, I think already known, people can use it for either by photocatalysis or different type of applications, or for example, solar cells, people want as a dye-sensitized solar cells also you can use. Again, one example is importance of surface area. We have to look for high surface area, especially for dye-sensitized, so that electrolyte will nicely penetrate. And this is one example with commercial sample with the molten salt prepared high surface area material. I think you can do some improvement in the performance. Again, if you do with nanotechnology, you can do nano to submicron size. I think these are a special example. I'm telling you, I know some cases too small size also not good. I don't have much time to discuss. So since you're a physicist, you can concentrate on the sensors. So again, we can see very lot of, for example, you can take semiconducting material, we can use it for sensor application or different type of the, so here a lot of physicists, you can work in a different areas. I think supercapacitor, I don't have time. I think these are the different areas. So these are the conclusions and efforts have been made, the thin and bulk material. Again, it depends on if you're a physicist, I can do thin films, I can do is great. So according to me, it is nice to know both the things. At least you try to prepare the material that will be useful. Again, if it is in terms of physics, thin films, I think RBS is the best technique to know the composition. It is difficult to access the facility. So there is my personal, since I was in France, I'm able to access in Singapore also, there is good facilities. So that's why it's easier to run the things. And among them all, few materials are promising. So again, I think industry or future, I think we need to look for low cost material, safe and long term, in the sense that once I buy the battery, they need to look for the long term applications. Again, we need cooperation with this, what they call as a physicist, chemist, and engineers is very important to prepare the large scale applications. Okay, and thank you very much. Okay, sorry I taken some another 5 minutes or 10 minutes, I'm not sure. Thank you very much. Okay, maybe you can try to raise a question, that will be very useful. Okay, thank you very much, sir. Thank you.
Sir, thank you for your wonderful presentation on thin film and bulk smart materials, which was used for the energy storage and convention applications, sir. Okay. And now it is the time for the question session. Dear professors and participants, this is the question session. If you have any doubt or clarification, you may ask the question, or otherwise you can post the question in the chat box.
Yeah. So, or if you're a little bit shy, I think you can send me email also. That is also very important sometimes, you know. So idea is that since although I am academic research, what are the things idea is that I would like to share the knowledge, and later some people are doing the research, and in future anytime you can contact. So idea is that always my personal opinion is that wherever I'll go for conference, at least 1 or 2 people have to motivate them. I think share my knowledge. I think that is my, I have to help them also. It's very important since Canada is a little bit far, and also here when I was in Singapore, it's a little bit easier. That's why I used to present in some conference. I think many people like you people, I know that some colleges did not facility. They used to come and contact me. We help many people. In fact, that way, I think 6 to 7 PhD, nearly 4 to 5 PhD from Indian University. They visited our lab. We help them. I think that way, I think they're very useful. Okay, that is my. So presently, I'm not able to help still. So this is the way I can tell that at least contribute to the society. That is the only thing. Just for explaining my knowledge, sharing the things. Okay, thank you very much, sir. Thank you.
Thank you. Thank you for your valuable suggestion, sir.
Okay.
If there is,
sir.
Yes, sir.
Yeah, sir. Jai Shankar, sir. Yeah, please,
Thank you very much, sir.
Sir, thank you very much, sir. Sir, thank you very much, sir.
Really, I am very happy to see you, and hope to see you at least not in webinar. The things will come back, and we will enjoy social interactions.
Yes, sir. In fact, I mean, keep in touch with Professor Rambabu Garu also. He used to mention your name, sir. Thank you, sir. Thank you, sir. Yeah.
Yeah, we are in touch with him, sir.
Okay, sir. Thank you very much, sir. Thank you. Thank you, sir.
Good day, sir. Good day, sir. Good day, sir.
Yeah.
Thank you, sir.
Yeah. Sorry, I know that sometimes slides are a little bit faster because hopefully it would have moved. Nowadays with Indians, we are able to follow our accent. I think although we are able to talk fast, also I think we are able to follow. I think that is very important. So with our Indian.
What is time, sir? Too early morning. Early morning for you. What is time now?
Yeah, no, it is okay, sir. No, it's okay. So because yesterday I was wake up little bit late, and then I'm not able to sleep. It's still okay. I think sometimes it's all right now. I think 6 o'clock now exactly.
6.
Yeah.
So you are really no sleep.
No, it's okay. It's okay.
Okay, sir. Kind of you, sir.
Thank you, sir.
A very good evening to one and all. A big thank you to all eminent professors, scholars, and the student participants. And I would also thank the management of ISPA members and the resource person who lent their valuable support for today's conference. With this, we conclude the first day session. We will freshly meet virtually tomorrow morning sharply at 9:45 a.m. Thank you. Once again, thank you one and all.
Okay, sir. I'll try to attend tomorrow's some talks. Okay, I'll try to attend. Thank you very much, sir.
Sure,
okay,
sure.
Really
thank you, sir. Thank you, sir. Thank you.
Okay, thank you, sir.
Thank you to
okay,
all.
Sir. Good health to all the people. In fact, you are senior people. I think you were all your your motivation and everything is very important. Take care of your health. Hopefully, everything will be all right. Thank you, sir. Thank you very much, sir. Thank you. Thank you very much, madam, and thank you for the management. In fact, already you've seen all different faces. Okay, thank you very much, sir. Thank you. Okay, thank you, Ambaresan. Also, I visited your talk, listened your talk. So, really interesting physicist talks it was there. So, thank you very much, sir. Thank you. Hello, sir. Yeah. Hello, sir. Ambaresan. Yeah. Please.
Sir. Very good, nice presentation, sir.
Okay, thank you, sir. Thank you. In fact, I also listen your laser physics is interesting also. In fact, although I'm not working in the area, I know that like we are physicists. I think depending on the facilities we can play, that's why I'm telling yeah, all the things we cannot do. One person we cannot do all the areas. Okay.
Yes.
So that's why, sir. Thank you very much.
Thank you very much, sir.
Thank you, sir. Okay, sir. So we'll see you. Okay. Now,
Shall we wind up, sir?
Yes,
Yeah.
yes, we
Yes,
can
sir.
close.
Thank you. Thank you, sir. Thank you. Thank you,
Okay, sir. Welcome to all, sir. Welcome to all, sir. Thank you. So I will exit. Okay. Thank you.